vast darkness between stars, a single atom drifts. It has no destination, no urgency. It simply is. This atom, perhaps a carbon nucleus surrounded by its faithful electrons, has been traveling for billions of years. It has seen the birth of galaxies, the death of suns, and the slow dance of cosmic evolution. But where did it come from? And where will it go when its current form dissolves? Tonight, we embark on a journey through deep time and infinite space to answer a question that has puzzled humanity since we first looked up at the stars. Where do atoms go when they die? The answer, as we will discover, is both simple and profound. They do not die at all. Picture yourself sitting in a quiet room, breathing slowly. With each breath, you inhale billions of atoms that were once part of distant stars, ancient oceans, and perhaps even the bodies of creatures that lived millions of years ago. The calcium in your bones was forged in the heart of a dying star. The iron in your blood was born in a supernova explosion that lit up the cosmos long before our sun even existed. You are not separate from the universe. You are the universe, temporarily organized into the form you call yourself. This is the story of matter itself, of the endless recycling of the fundamental building blocks of existence. It is a story without true endings, only transformations. Every atom in your body has existed for over 13 billion years, and it will continue to exist long after your last breath, long after the sun burns out, long after our galaxy merges with distant neighbors. The atoms do not know death as we understand it. They know only change, only movement, only the eternal dance of composition and decomposition. When we speak of atomic death, we speak in metaphors, for atoms are among the most enduring things in the universe. They outlive stars, they outlive planets, they outlive entire species. So let us follow one particular atom on its journey, a carbon atom that might at this very moment be part of your body. Let us trace its path backward through time to its birth in the furnace of a star, and forward into its infinite future. Let us discover that in the grand cosmic story, nothing truly ends. Everything simply becomes something else. The atom drifts on, carrying within its nucleus the memory of every place it has been, every star that forged it, every planet it helped build, every living thing it briefly called home. It is immortal not by design, but by nature. It is the universe knowing itself, one infinitesimal piece at a time. Consider the water you drank today. Those hydrogen atoms were born in the first few minutes after the Big Bang, when the universe was a hot, dense soup of elementary particles. They have since spent eons drifting through space, condensing into clouds that became stars, escaping those stars when they died, traveling through the void until they found Earth. They may have been part of ancient seas that covered continents now long gone, breathed by dinosaurs, flowing through rivers that carved the Grand Canyon, resting in glaciers, rising as vapor into clouds. Now they are you, for a brief cosmic moment. Soon they will be something else. The rain that falls tomorrow, the morning dew on grass, the blood of a sparrow, the sap of a tree. Each transition is not an ending but a beginning, not a death, but a rebirth into a new form of existence. Scientists estimate that roughly 1 billion atoms that were once part of William Shakespeare are now part of your body. You carry within you pieces of ancient forests, of creatures that swam in primordial oceans, of rocks that formed when Earth was young. You are a temporary gathering of the universe's most ancient citizens. The concept of atomic death is a human invention, a way to make sense of the changes we see around us. But atoms themselves know no such boundaries. They flow from solid to liquid to gas, from organic to inorganic, from living to non-living and back again. They are the ultimate shapeshifters, the eternal wanderers of the cosmos. In the deepest sense, asking where atoms go when they die is like asking where the river goes when it reaches the sea. It becomes part of something larger, something different, yet it remains essentially itself. The river does not disappear, and neither do atoms. They continue their ancient dance, following physical laws that were written in the first moments of creation. Tonight, as you listen to this story, remember that you are both the observer and the observed, the storyteller and the story itself. You are made of stars, and to stars you shall return, not in death but in transformation. The atoms that form you now have witnessed the birth of the universe, and they will witness its end, whatever form that ending may take. This is their story, and it is your story too, because in the realm of atoms, there is no difference. We are all part of the same cosmic recycling program, the same eternal circulation of matter through space and time. Let us travel back in time, far beyond the birth of our sun, beyond the formation of galaxies, beyond the first stars. We journey to a moment when the universe was only 3 minutes old, when it was smaller than our solar system and hotter than the core of any star that would ever exist. This is where our story truly begins, in the cosmic furnace that created the first atoms. In the beginning, there were no atoms at all. The universe was a seething cauldron of subatomic particles, protons and neutrons flying free in a soup so hot and dense that nothing stable could form. The temperature was over 1 billion degrees Celsius, and space itself was expanding rapidly, cooling as it grew. This was the era of Big Bang nucleosynthesis, a brief but crucial period when the first atomic nuclei came into being. Picture this primordial chaos. Protons, the future hearts of hydrogen atoms, raced through space at incredible speeds measured in tens of thousands of kilometers per second. Neutrons, slightly heavier than protons and carrying no electrical charge, collided and combined with them in a cosmic dance of creation. The universe was like a vast particle accelerator, but instead of smashing things apart, it was cooling just enough to let them stick together for the first time. Imagine being inside a cosmic soup so dense that matter was packed 1 billion times tighter than water. The pressure was beyond anything we can comprehend, greater than at the center of the most massive star. Yet this was not a solid or liquid, but a plasma, a state of matter where individual particles moved with such energy that they could barely interact before being torn apart again by the violence of their surroundings. As the first minute after the Big Bang ticked by, temperatures dropped rapidly but remained scorching. At 1 billion degrees Celsius, the universe was still far too hot for stable nuclei to form. Protons and neutrons collided constantly, but the thermal energy was so great that any temporary combinations were immediately blown apart. It was like trying to build with blocks during an earthquake. Every attempt at construction immediately destroyed. But the universe was expanding and cooling with each passing second. By the time 2 minutes had elapsed, the temperature had dropped to around 100 million degrees Celsius. This was still incredibly hot by any earthly standard, hot enough to vaporize any material we know, but it was cool enough for the first nuclear reactions to begin in earnest. As the minutes ticked by and the universe expanded, the cosmic alchemy finally began to work. Protons and neutrons could finally embrace without being torn apart by the intense heat. They began to form the very first atomic nuclei. Most of these were simple hydrogen nuclei, just single protons waiting for their electron companions. But some protons grabbed hold of neutrons, creating deuterium, heavy hydrogen, with 1 proton and 1 neutron locked together in nuclear embrace. The nuclear furnace was working at full capacity now. 2 protons and 2 neutrons found each other and formed helium-4 nuclei, the second element in the cosmic recipe. This was no gentle process. Each fusion reaction released tremendous amounts of energy, equivalent to millions of chemical explosions. Yet in the context of the early universe, these were just tiny sparks in an already blazing inferno. A few protons and neutrons combined into tritium and helium-3, unstable cousins that would later decay into more familiar forms. Tritium, with 1 proton and 2 neutrons, was particularly unstable, with a half-life of just over 12 years. Most of the tritium created in the Big Bang has long since decayed away, leaving behind daughter products that tell us about conditions in the early universe. And in the rarest of encounters, some nuclei captured another neutron to become lithium-7, the third and final element to emerge from this cosmic kitchen. Lithium-7, with 3 protons and 4 neutrons, was the most complex nucleus that could form under the conditions of the early universe. Its creation required a delicate balance of temperature and density that existed for only a brief window of time. There was also lithium-6, created in smaller quantities through a different nuclear pathway, and beryllium-8 formed briefly, but this nucleus was so unstable that it broke apart almost immediately, splitting into 2 helium-4 nuclei. This instability of beryllium-8 is why the Big Bang could not create elements heavier than lithium. To make carbon and beyond would require the interior of stars. But the window of opportunity for primordial nucleosynthesis was brief. The universe was expanding rapidly, and as it expanded, it cooled and became less dense. Within 20 minutes of the Big Bang, the temperature had dropped below 50 million degrees Celsius, and the density had fallen too low for nuclear fusion to continue. The brief era of primordial nucleosynthesis came to an end, like a fireworks display that burns bright and then fades. In those crucial 20 minutes, the universe had created roughly 75% hydrogen nuclei, 25% helium nuclei, and tiny traces of lithium nuclei. These proportions were determined by the fundamental physics of nuclear reactions and the expansion rate of the universe itself. They would remain essentially unchanged for hundreds of millions of years to come. What happened to electrons during this time? They existed, zipping around at fantastic speeds that would make any earthly particle accelerator seem sluggish. But they could not yet settle down with their nuclear partners. The universe was still far too hot and energetic for the delicate electromagnetic dance between oppositely charged particles. Photons, particles of light, carried enormous energies in the early universe. These high-energy photons had enough punch to knock any electron away from its nucleus the moment they tried to get close together. It was like trying to hold a conversation during a thunderstorm, with lightning bolts constantly interrupting any attempt at communication between nuclei and electrons. The universe at this time was completely opaque to light. Every photon was immediately scattered by the free electrons that filled space. It was like trying to see through a thick fog that glowed with the heat of creation itself. Light could travel only tiny distances before encountering an electron and scattering in a random direction. This cosmic fog persisted for hundreds of thousands of years as the universe continued to expand and cool. During this period, known as the Cosmic Dark Ages, no stars shone and no galaxies existed. There was only the hot, glowing plasma of nuclei, electrons, and photons in constant chaotic interaction. For 378,000 years, this cosmic game of atomic hide-and-seek continued. That may sound like an incredibly long time, longer than humans have existed on Earth, but in cosmic terms, it was just a brief moment of patience. The universe was playing a waiting game, allowing time and expansion to cool things down to the point where stable atoms could finally form. The nuclei themselves were remarkably persistent during this era. A hydrogen nucleus, consisting of a single proton, carried a positive electrical charge that naturally attracted the negatively charged electrons swirling around it. The electromagnetic force between them was strong, creating a powerful attraction. But every time an electron tried to settle into orbit around a nucleus, a high-energy photon would come along and knock it away. It was like trying to build a delicate house of cards in a windstorm. Every attempt at construction was immediately destroyed by the violence of the electromagnetic environment. The nuclei waited patiently, their positive charges calling out to the negative electrons, but the universe was simply too hot and chaotic for the two to unite. As the universe expanded, several important things happened simultaneously. First, the density of matter decreased as the same amount of stuff spread out over ever larger volumes of space. Second, the temperature dropped as the thermal energy of particles was diluted by expansion. And third, the wavelength of light was stretched, reducing the energy of photons through a process called cosmological redshift. The cosmic background radiation was gradually losing its punch. Photons that had started out with tremendous energy were being redshifted to longer and longer wavelengths as space itself expanded. This meant they carried less and less energy as time went on. Meanwhile, the electrons and nuclei were slowing down as the temperature dropped, their thermal motion becoming less frantic. The universe during this period was remarkably uniform on large scales. Matter was distributed almost evenly throughout space, with only tiny variations in density from place to place. These small fluctuations, imprinted during an even earlier epoch called cosmic inflation, would prove crucial for the formation of all the structure we see in the universe today. But on small scales, the universe was incredibly violent and chaotic. Particles collided constantly at high speeds. Electromagnetic radiation filled every corner of space. The temperature, while dropping steadily, remained far above anything that exists naturally in the universe today except in the cores of the most massive stars. The cosmic waiting game continued. Month after cosmic month, year after cosmic year, the universe expanded and cooled. The dance of particles and radiation gradually became less frantic. The electrons slowed down, their thermal motion becoming less violent. The photons lost energy as they were stretched by the expansion of space itself. Then came the moment that changed everything forever, an event cosmologists call recombination. The name is somewhat misleading since it was actually the first time atoms had ever combined, but the term has stuck in scientific literature. The universe had finally cooled to about 3,000 degrees Celsius, cool enough for electrons to settle into stable orbits around atomic nuclei. This temperature may sound extremely hot by earthly standards, hot enough to melt any metal and vaporize most substances we know. But in the context of the early universe, which had started out billions of times hotter, 3,000 degrees was positively frigid. It was cool enough for the electromagnetic attraction between positive nuclei and negative electrons to finally overcome the disruptive effects of thermal motion and radiation. Hydrogen atoms formed as single electrons found homes circling single protons. The process was like a cosmic courtship dance that had been going on for hundreds of thousands of years, with particles circling each other but never quite touching. Now, finally, the electron could settle down, slipping into what physicists call the ground state, the lowest possible energy level around the proton. The formation of a hydrogen atom is one of the most elegant processes in physics. The electron does not orbit the nucleus like a planet around a star, despite what simplified diagrams might suggest. Instead, it exists in a quantum mechanical state, a probability cloud that surrounds the nucleus. The electron is simultaneously everywhere and nowhere around the nucleus, until someone tries to measure its position. Helium atoms assembled as two electrons took up residence around helium nuclei. These were more complex structures, with the electrons occupying different quantum states around nuclei containing two protons and two neutrons. The helium atoms were more stable than hydrogen, their electrons more tightly bound due to the stronger positive charge of the helium nucleus. The formation of helium atoms required a delicate choreography of quantum mechanics. The two electrons had to avoid occupying the same quantum state, following what physicists call the Pauli exclusion principle. They settled into different energy levels and orientations, creating the first multi-electron atoms in the cosmic story. And in the rarest cases, lithium atoms formed with 3 electrons orbiting nuclei, containing 3 protons, and either 3 or 4 neutrons. These were the most complex atoms in the early universe, though they would seem incredibly simple compared to the heavy elements that would be created billions of years later in the cores of stars. The lithium atoms were particularly interesting because they required 3 electrons to find stable configurations around their nuclei. The innermost electrons settled into the same type of orbit as in hydrogen, but the second and third electrons had to find different quantum states. This created the first hint of the complex electron shell structures that would characterize all the heavier elements. This moment, when the first complete atoms formed, was truly the birth of matter as we know it. Suddenly, after hundreds of thousands of years of cosmic fog, the universe became transparent. With their electrons bound to nuclei, atoms could no longer scatter light effectively. The cosmic fog lifted, and radiation could travel freely through space for the first time since the Big Bang. Imagine standing in a dense forest where the trees are so thick you cannot see more than a few feet in any direction. Then suddenly, as if by magic, all the trees disappear, and you can see clearly to the horizon. This is what happened to light in the universe during recombination. The cosmic fog that had made the universe opaque suddenly cleared, and photons were free to travel vast distances without being scattered. The photons that were freed during recombination are still with us today. They form what we call the cosmic microwave background radiation, the afterglow of the moment when the universe became transparent. These ancient photons have been traveling through space for over 13 billion years, carrying with them a snapshot of the conditions that existed when atoms first formed. Modern telescopes can detect this cosmic microwave background radiation coming from all directions in space. It appears as a nearly uniform glow with tiny temperature variations that reflect the small density fluctuations that existed in the early universe. These fluctuations were the seeds that would grow into all the galaxies, stars, and planets we see today. But let us focus on one particular hydrogen atom born in this miraculous moment of cosmic transparency. Picture it forming in a vast cloud of cooling gas, somewhere in what would one day become the local group of galaxies, the small cluster that includes our own Milky Way, the Andromeda Galaxy, and dozens of smaller companions. Our hydrogen atom came into being as an electron settled into orbit around a proton, finding its home in the quantum mechanical ground state. For the first time in the universe's history, this bit of matter was electrically neutral, stable against the buffeting of electromagnetic radiation. It was ready to interact with other atoms through the much gentler forces of gravity and weak electromagnetic attraction. The atom was incredibly small, roughly 1 angstrom across, or about 1/10 billionth of a meter. To put this in perspective, if you could line up hydrogen atoms side by side, it would take about 10 million of them to span the period at the end of this sentence. Yet within this tiny space was concentrated all the complexity of quantum mechanics, the strange and wonderful rules that govern matter at the smallest scales. The nucleus of our hydrogen atom, the proton at its center, was even tinier. If the atom were the size of a football stadium, the nucleus would be smaller than a marble sitting at the 50-yard line. Almost all of the atom's mass was concentrated in this tiny nucleus, while the electron spread its probability throughout the vast spaces around it. The electron in our hydrogen atom was not a tiny ball circling the nucleus like a planet around the sun. Instead, it existed as a quantum wave, a probability distribution that described where the electron might be found if anyone were looking for it. The electron had no definite position until it was observed, existing instead in what physicists call a superposition of all possible states. This hydrogen atom, along with countless billions of its companions, began to drift through the newly transparent universe. Space was still filled with radiation, but that radiation could now travel freely without being scattered by free electrons. The universe had entered a new era, one where matter could begin to organize itself into larger and more complex structures. The cosmic environment in which our hydrogen atom found itself was quite different from the universe we know today. The temperature of space itself was much warmer, around 3,000 degrees Kelvin compared to the mere 2.7 degrees it maintains today. The density of matter was also much higher, with atoms encountered much more frequently than in the universe's current state. But even in this warmer, denser environment, space was still mostly empty. The average distance between atoms was still enormous compared to their size. If our hydrogen atom were the size of a marble, its nearest neighbor would typically be several miles away. The universe was far from crowded, even by cosmic standards. Our hydrogen atom began its long journey through space with no particular destination in mind. It drifted along with the general expansion of the universe, carried by currents in the cosmic medium that were driven by tiny variations in density and pressure. Sometimes it moved toward regions that were slightly denser than average, drawn by the weak but persistent pull of gravity. Gravity was already beginning to play its cosmic role as the architect of structure. The tiny density fluctuations that had existed since the era of cosmic inflation were now free to grow under gravity's influence. Regions that were even slightly denser than average began to attract more matter, gradually becoming denser still. This was the beginning of structure formation in the universe. Our hydrogen atom sometimes found itself in these slightly overdense regions, where it encountered other atoms more frequently. When two hydrogen atoms drifted close together, interesting things could happen. Their electron clouds might overlap slightly, creating a weak attraction known as the van der Waals force. This force is incredibly weak compared to the electromagnetic forces that hold atoms together, but in the gentle environment of space, it was enough to briefly bind atoms into molecules. The formation of the first molecules was a momentous event in cosmic history. When two hydrogen atoms combined to form molecular hydrogen, H2, they created the first chemical bond in the universe. This was chemistry in its most primitive form, but it was the beginning of the complex molecular dance that would eventually give rise to life itself. Molecular hydrogen formation required specific conditions. The two hydrogen atoms had to approach each other with just the right speed and orientation. If they were moving too fast, they would simply bounce off each other. If they approached from the wrong angle, their electron clouds would repel each other. But when conditions were right, they could share electrons, creating a covalent bond that held them together. The newly formed H2 molecules were more stable than individual hydrogen atoms in some ways, but they were also more vulnerable to destruction. A high-energy photon could break the molecular bond, splitting the molecule back into two separate atoms. Collisions with other particles could also disrupt the delicate chemical bond. In the early universe, the lifetime of these first molecules was often brief. Our hydrogen atom participated in this molecular dance many times over the millions of years that followed recombination. Sometimes it would pair up with another hydrogen atom to form H2. Sometimes it would encounter one of the rare lithium atoms and form lithium hydride, an even more exotic molecule in that element-poor epoch. And sometimes it would simply drift alone through space, a chemical bachelor in the cosmic void. The universe during this period was entering what cosmologists call the cosmic dark ages. This name is somewhat misleading because space was filled with the warm glow of the cosmic microwave background radiation. But there were no stars yet, no galaxies, no powerful sources of light to illuminate the cosmos. The universe was dark in the sense that nuclear fusion had not yet resumed after the brief period of Big Bang nucleosynthesis. Our hydrogen atom drifted through this dark, but not entirely quiet universe. The cosmic microwave background radiation provided a constant, gentle bath of photons that occasionally interacted with the atom. Sometimes a photon would be absorbed by the electron, bumping it to a higher energy level. The electron would then quickly fall back to its ground state, emitting a photon of its own in the process. These interactions created the first spectral lines in cosmic history. When the electron in our hydrogen atom jumped between energy levels, it emitted or absorbed light at very specific wavelengths determined by the quantum mechanical properties of the atom. The most important of these was the 21 centimeter line, produced when the electron flipped its spin orientation relative to the proton. The 21 centimeter radiation from hydrogen atoms filled the early universe with a very faint radio signal. This radiation was far too weak to be detected by any conceivable technology at the time, but it carried information about the distribution and motion of hydrogen gas throughout space. Modern radio astronomers hope to detect this ancient signal to learn about conditions in the cosmic dark ages. As millions of years passed, our hydrogen atom found itself in an evolving cosmic landscape. The universe continued to expand and cool, but now gravity was beginning to compete more effectively with the expansion. Regions that had started out slightly denser than average were becoming noticeably more concentrated as they attracted surrounding matter. Dark matter, mysterious particles that interact only through gravity, was playing a crucial role in this process. Dark matter had begun clumping together much earlier than ordinary matter because it was not affected by electromagnetic radiation the way atoms were. By the time atoms formed, dark matter had already created invisible scaffolding, gravitational wells that would trap ordinary matter and guide the formation of the first large-scale structures. Our hydrogen atom gradually found itself being drawn toward one of these dark matter concentrations. The journey was imperceptibly slow by human standards, taking millions of years to cover distances that light could traverse in seconds. But the atom had nowhere else to go, and nothing but time. It drifted slowly inward, following the patient pull of gravity. The region toward which our atom was being drawn would one day become part of a galaxy, but for now, it was just a slightly denser patch of space where matter was beginning to collect. As more and more atoms gathered in this region, their combined gravitational pull grew stronger, attracting even more matter in a slow but accelerating process. Temperature fluctuations in this gathering cloud of gas were tiny but important. In regions that were slightly cooler than average, atoms moved more slowly and had better chances of sticking together when they collided. This led to the formation of more molecules and began to create the chemical complexity that would be necessary for star formation. Our hydrogen atom sometimes found itself in these cooler regions, where it was more likely to form molecular bonds with its neighbors. The cloud was beginning to develop structure, with denser knots of matter separated by more tenuous regions. These knots would eventually become the cores of the first stars, but that development still lay far in the future. The atom also experienced the effects of cosmic weather patterns. Sound waves rippled through the gas cloud, compression waves that alternately squeezed matter together and stretched it apart. These acoustic oscillations were driven by the complex interplay between gravity trying to collapse the cloud and gas pressure trying to expand it. In regions where the sound waves compressed the gas, our hydrogen atom found itself in closer proximity to its neighbors. The density would increase, sometimes by factors of 2 or 3, before the compression wave passed and the gas expanded again. These oscillations helped mix the primordial gas and may have played a role in determining where the first stars would eventually form. The cosmic dark ages were not entirely dark in terms of physical processes. While there were no stars or galaxies yet, the universe was full of subtle activity. Matter was slowly organizing itself under gravity's guidance. Chemical bonds were forming and breaking in the gentle environment of space. The seeds of cosmic structure were growing larger and more pronounced with each passing million years. Our hydrogen atom was both a passive observer and an active participant in these cosmic changes. Its own tiny gravitational field contributed to the overall gravitational environment that was shaping structure formation. Its interactions with radiation and other atoms helped establish the physical conditions that would eventually allow stars to form. The atom had also become part of something larger than itself. It was now a member of a vast hydrogen cloud that contained billions upon billions of other atoms, all drifting together through space under gravity's influence. This cloud was destined to become one of the first star-forming regions in the universe, though our atom did not yet know its cosmic destiny. As our story of atomic wandering through the cosmic dark ages draws to a close, the hydrogen atom continues its patient drift through space. It has existed in its current form for millions of years now, a stable marriage of proton and electron that has weathered the cooling and expansion of the universe. It has participated in the first chemical reactions, contributed to the first large-scale structures, and helped set the stage for the next great chapter in cosmic evolution. The universe is preparing itself for the birth of the first stars. Matter is collecting in denser and denser concentrations. Gravitational energy is slowly being converted to thermal energy as gas clouds collapse under their own weight. The stage is being set for nuclear fusion to resume for the first time since the Big Bang, but now in the controlled environment of stellar cores rather than the chaotic conditions of primordial nucleosynthesis. Our hydrogen atom, having survived the violence of the Big Bang and weathered the long cosmic dark ages, stands ready to enter the next phase of its existence. Soon it will be drawn into one of the first stars, where it will experience temperatures and pressures not seen since the universe's first moments. In the stellar interior, it will be transformed, its simple structure broken apart and rebuilt into something entirely new. But that transformation lies ahead in our story. For now, the hydrogen atom drifts onward through space, carrying within its simple structure the potential for all the complexity that will follow. It is matter in its purest form, the raw material from which stars and planets and eventually life itself will be built. The cosmic recycling program is about to begin in earnest. The hydrogen atom that had drifted through space for millions of years was about to experience something unprecedented. The vast cloud of gas in which it found itself was slowly but inevitably collapsing under its own gravity. What had begun as gentle attraction was becoming an inexorable inward pull, drawing matter toward the center of the cloud with ever-increasing force. Our atom found itself caught in this cosmic whirlpool, spiraling slowly inward along with billions of its companions. The journey toward the center took hundreds of thousands of years, but with each passing millennium, the hydrogen atom noticed changes in its environment. The space between atoms grew smaller, collisions with other particles became more frequent, and most importantly, the temperature began to rise. This was the birth of the first star, though the process was far slower and more gradual than the explosive events we might imagine. The collapse was driven by gravity alone, the weakest of the fundamental forces, but also the most persistent. Unlike electromagnetic forces, which can both attract and repel, gravity only pulls. Once the collapse began, nothing could stop it, except the internal pressure created by the heating gas. As our hydrogen atom fell toward the center of the forming star, it experienced increasing density and temperature. The gas cloud that had been more diffuse than any vacuum we can create on Earth was becoming denser than water, then denser than rock. The atom found itself squeezed ever more tightly against its neighbors, their electron clouds beginning to overlap and interact in new ways. The temperature was rising too, though slowly at first. Gravitational energy was being converted to thermal energy as matter fell inward. Each atom that reached a deeper level in the gravitational well possessed more kinetic energy, moving faster and colliding more violently with its neighbors. The gentle drifting of the cosmic dark ages was giving way to increasingly frantic motion. Our hydrogen atom had experienced temperatures of thousands of degrees during the era of recombination, but this was different. That heat had been the dying ember of the Big Bang's fire, cooling steadily as the universe expanded. This new heat was being created actively by the collapse itself, and it was growing stronger rather than weaker with time. At first, the rising temperature had little effect on our hydrogen atom's structure. The electron remained safely bound to its proton partner, orbiting in its ground state, as it had for millions of years. The atom bounced off its neighbors elastically, like billiard balls, transferring energy but remaining intact. But as the temperature climbed past 10,000 degrees Celsius, something fundamental began to change. The thermal energy of motion was becoming comparable to the electromagnetic binding energy that held the electron to the proton. The atom began to experience moments of disruption, brief separations when a particularly violent collision would knock the electron away from its nucleus. These separations were initially temporary. The ionized atom, now just a bare proton, would quickly recapture an electron from the surrounding medium and return to its neutral state. But as the temperature continued to rise, the periods of ionization became longer and more frequent. The hydrogen atoms were beginning to fall apart under the stress of the increasingly violent environment. By the time the temperature reached 50,000 degrees Celsius, our hydrogen atom found itself spending most of its time in an ionized state. The electron and proton were still in the same general region of space, but they were no longer bound together in the stable quantum mechanical dance that defines an atom. They moved independently, occasionally coming together briefly before being torn apart again by the thermal chaos around them. The forming star was now a plasma, a state of matter where electrons and nuclei roam freely without forming complete atoms. This plasma was optically thick, meaning that light could travel only tiny distances before being absorbed or scattered by the free electrons. The interior of the forming star was once again opaque, as it had been in the early universe before recombination. Our hydrogen nucleus, separated from its electron partner, continued its inward journey. The temperature was now hundreds of thousands of degrees, and still rising. The pressure was enormous, far greater than at the bottom of the deepest ocean on Earth. Yet the collapse continued, driven by the relentless pull of gravity. Other elements were present in the forming star, though in much smaller quantities. Helium nuclei, each containing 2 protons and 2 neutrons, were scattered throughout the plasma. They had been more tightly bound than hydrogen during the cosmic dark ages, and they remained intact longer during the stellar collapse. But they too eventually succumbed to ionization as the temperature climbed toward 1,000,000 degrees. The rare lithium nuclei that had been created during Big Bang nucleosynthesis were also present, though in vanishingly small amounts. These fragile structures were among the first to be torn apart as the temperature rose. Lithium is destroyed at relatively low temperatures compared to hydrogen and helium, which explains why we see so little of it in old stars today. As the temperature approached 1,000,000 degrees Celsius, our proton found itself in an environment unlike anything it had experienced since the Big Bang itself. The thermal energy was now so great that particles moved at significant fractions of the speed of light. Collisions between nuclei became violent enough to overcome the electromagnetic repulsion between positively charged particles. This electromagnetic repulsion is what had prevented nuclear fusion during most of cosmic history. Protons carry positive charges, and like charges, repel each other with tremendous force. For nuclei to get close enough to fuse, they must overcome this Coulomb barrier, named after the French physicist who first described electromagnetic forces. In the cool environment of space, protons could never get close enough to each other to fuse. The electromagnetic repulsion kept them at arm's length, so to speak. But in the extreme conditions developing in the stellar core, thermal energy was finally providing enough force to push protons together despite their mutual repulsion. Our proton experienced its first fusion reaction when the temperature reached about 10,000,000 degrees Celsius. Moving at tremendous speed, it collided head-on with another proton. For a brief instant, the two particles were close enough for the strong nuclear force to take hold. The strong force, which operates only at extremely short ranges, is much more powerful than electromagnetic repulsion when nuclei are close enough to feel its influence. But the fusion of two protons is not a simple process. Both particles carry positive charge, so they cannot simply stick together. Instead, one of the protons undergoes a transformation, converting into a neutron through a process called beta plus decay. A proton becomes a neutron by emitting a positron and a neutrino, changing the nuclear dynamics completely. The result is the formation of deuterium, heavy hydrogen with one proton and one neutron. This nuclear reaction releases a small amount of energy, carried away by the emitted particles and by the binding energy that holds the deuterium nucleus together. Our original proton had become part of this new, heavier nucleus. But the nuclear transformation did not stop there. The newly formed deuterium nucleus was still in the violent environment of the stellar core, surrounded by other fast-moving particles. Soon it encountered another proton and underwent a second fusion reaction. The proton joined the deuterium nucleus to form helium-3, containing 2 protons and 1 neutron. Helium-3 is an isotope of helium, lighter than the common helium-4 that was created during Big Bang nucleosynthesis. It is stable but relatively rare in the universe because it serves as an intermediate step in stellar fusion processes. In the core of our forming star, helium-3 nuclei were constantly being created and consumed in ongoing nuclear reactions. Our original proton, now part of a helium-3 nucleus, soon participated in yet another fusion reaction. Another helium-3 nucleus approached, and the two merged in a complex process. This reaction produced a helium-4 nucleus plus 2 protons, completing what physicists call the proton-proton chain, the primary fusion process in stars like our Sun. The energy released by these fusion reactions was enormous. Each individual reaction released millions of times more energy than any chemical reaction could produce. The energy came from the conversion of a tiny amount of mass into energy, following Einstein's famous equation E equals mc squared. The mass of the helium-4 nucleus was slightly less than the combined mass of the 4 protons that had gone into making it, and this missing mass had been converted into energy. This energy was released in several forms. Some of it appeared as kinetic energy of the reaction products, heating the stellar material even further. Some was carried away by photons, high-energy particles of light that began their long journey from the stellar core toward the surface. And some was carried by neutrinos, ghostly particles that barely interact with matter and could escape directly from the star's interior. The nuclear furnace was now in full operation. Our original proton had been broken apart from its faithful electron companion, fused with other nuclei, transformed into different particles, and ultimately incorporated into a helium-4 nucleus. But this was only the beginning of its stellar journey. The star had achieved what astronomers call hydrostatic equilibrium, a balance between the inward pull of gravity and the outward pressure from nuclear fusion. The star was now shining, though it would be millions of years before that light reached the surface and escaped into space. The photons created by fusion reactions in the core had to make an epic journey through the dense stellar interior, being absorbed and re-emitted countless times along the way. What started as high-energy gamma rays would gradually be degraded to lower-energy visible light by the time it finally escaped. Our helium-4 nucleus, containing the remnant of our original proton, found itself in the stellar core as nuclear burning continued around it. The core was now hot enough and dense enough to sustain fusion reactions indefinitely, at least for the foreseeable future. The star had achieved nuclear ignition and entered the main sequence, a stable phase of stellar evolution that would last billions of years. But helium-4 nuclei were not the end products of stellar fusion. As the first-generation star continued to burn hydrogen into helium, the core gradually became enriched in helium ash. Eventually, the hydrogen fuel in the core would be exhausted, and the star would have to find new sources of nuclear energy to continue shining. When the core hydrogen was depleted, gravity would again take control, compressing the helium-rich core to even higher temperatures and densities. At around 100 million degrees Celsius, a new type of fusion reaction would become possible, the helium burning process that could create even heavier elements. Our helium-4 nucleus, waiting in the stellar core with its billions of companions, would eventually participate in this next phase of element creation. 3 helium-4 nuclei would come together in a complex reaction to form carbon-12, the first element heavier than lithium to exist in significant quantities in the universe. This triple alpha process, named for the alpha particles that helium-4 nuclei were once called, was remarkable for its improbability. The chances of 3 helium nuclei colliding simultaneously were so small that the process should have been impossible. But the British physicist Fred Hoyle predicted that it must happen somehow, because carbon clearly existed in the universe and in our own bodies. Hoyle realized that there must be a special energy level in the carbon-12 nucleus that would make the triple alpha process more likely to succeed. This energy level, now known as the Hoyle state, was later confirmed by experiments. It was an example of what some call the fine-tuning of the universe, the idea that physical constants seem precisely calibrated to allow complex elements and life to exist. When our helium nucleus finally participated in the triple alpha process, it would join with two other helium nuclei to form carbon-12. This carbon nucleus would be the first truly complex nucleus that our original proton had been part of since the Big Bang. Carbon, with 6 protons and 6 neutrons, was chemically reactive in ways that hydrogen and helium could never be. But stellar nucleosynthesis did not stop with carbon. The newly formed carbon nuclei could fuse with additional helium nuclei to create oxygen-16, neon-20, and other elements. Each fusion reaction released energy and produced heavier and more complex atomic nuclei. The stellar core became a factory for element production, creating the chemical diversity that would eventually make planetary systems and life possible. Our original proton, now part of a growing family of heavier elements, continued its nuclear journey through stellar fusion processes. It might become part of nitrogen, fluorine, or sodium as fusion reactions proceeded. Each new nuclear incarnation brought different properties and possibilities for chemical interaction. The first-generation star was not content to produce only light elements. As helium burning proceeded and the stellar core contracted further, even higher temperatures became possible. When the temperature reached 600 million degrees Celsius, carbon nuclei could fuse with each other to produce magnesium-24. This carbon burning process opened up entirely new pathways for element creation. Silicon burning followed, creating elements like sulfur, argon, and calcium. Then came oxygen burning, neon burning, and a succession of nuclear processes that built up heavier and heavier elements. Each stage required higher temperatures and densities than the last, as the electromagnetic repulsion between nuclei grew stronger with increasing nuclear charge. Our original proton had become part of these successive waves of element creation, though tracking its exact path through the complex network of nuclear reactions would be nearly impossible. It might have been split apart and reformed dozens of times, joining different nuclear families with each stellar burning phase. The stellar core was now layered like an onion, with different burning processes occurring at different depths. Hydrogen burning continued in a shell around the inert helium core. Helium burning occurred deeper in, surrounded by shells of carbon burning, oxygen burning, and so on. Each layer was hotter and denser than the one above it, creating a complex structure maintained by the balance between gravity and nuclear energy. But there was a limit to how far this process could go. Each fusion reaction up to iron-56 released energy, helping to support the star against gravitational collapse. But fusing elements heavier than iron actually requires energy input rather than releasing it. Iron represents the bottom of the nuclear binding energy curve, the most stable configuration of protons and neutrons possible. When the stellar core began to accumulate iron group elements like iron, cobalt, and nickel, the star was approaching a crisis. No more energy could be extracted from fusion reactions involving these elements. The nuclear fires that had supported the star for millions or billions of years were running out of fuel. Our proton, having participated in the creation of numerous heavy elements, might now find itself part of an iron-56 nucleus. Iron-56 contains 26 protons and 30 neutrons, making it one of the most stable nuclei in nature. This isotope of iron is particularly stable because of the way nucleons fill the available energy levels in the nucleus. The iron core grew larger and denser as nuclear burning continued in the surrounding shells. Eventually, it reached a critical mass beyond which even the pressure from degenerate electrons could not support it against gravity. This led to one of the most violent events in the cosmos, a core collapse supernova. When the iron core collapsed, it did so catastrophically. In less than a second, matter that had taken millions of years to accumulate was crushed to nuclear density. The core became so dense that protons and electrons were forced together to form neutrons, releasing vast numbers of neutrinos in the process. The temperature shot up to billions of degrees, hot enough to disintegrate even iron nuclei back into individual protons and neutrons. Our original proton, if it had survived in an iron nucleus until this point, would now be liberated once again. The extreme conditions of core collapse undid millions of years of stellar nucleosynthesis in an instant, breaking apart complex nuclei and returning matter to a more primitive state reminiscent of the early universe. But the story did not end with destruction. The shock wave from the collapsing core propagated outward through the star, picking up tremendous energy as it went. When this shock wave reached the outer layers of the star, it blew them into space in a spectacular explosion. This was the supernova, an event so bright it could outshine an entire galaxy for months. In the violence of the supernova explosion, rapid nuclear processes occurred that had never been possible in the more sedate environment of the stellar core. Neutron capture reactions proceeded faster than radioactive decay could intervene, allowing the creation of elements much heavier than iron. Gold, platinum, uranium, and other heavy elements were forged in the few seconds of the supernova explosion. Our proton might have captured neutrons during this process, becoming part of nuclei containing dozens or even hundreds of protons and neutrons. These super-heavy elements were unstable and would later decay into more familiar heavy elements, but for a brief moment, the supernova created nuclear species that had never existed before in the history of the cosmos. The explosion scattered all these newly created elements throughout space. Matter that had been locked away in the stellar interior for millions of years was suddenly free to drift through the cosmos once again. Our proton, in whatever nuclear form it had taken, was launched on a new journey through interstellar space at speeds of thousands of kilometers per second. The supernova blast wave swept up surrounding material as it expanded, creating a supernova remnant that would glow for thousands of years. The heavy elements produced in the star and the explosion were mixed with hydrogen and helium in the interstellar medium, enriching the cosmic recipe for future generations of stars and planets. Some of the matter ejected by the supernova would eventually be incorporated into new stars, where the cycle of nuclear burning could begin again. But now these new stars would form from material that already contained carbon, oxygen, iron, and many other heavy elements. They would be what astronomers call metal-rich, though in astronomy, any element heavier than hydrogen and helium is considered a metal. Other portions of the supernova ejecta would find their way into planetary systems, where they would become the raw material for rocky planets and the chemical basis for life itself. The calcium in our bones, the iron in our blood, the oxygen we breathe, all of these essential elements were created in the nuclear furnaces of ancient stars and scattered throughout space by supernova explosions. Our original proton had completed one full cycle of cosmic recycling. It had begun as part of a simple hydrogen atom in the early universe, been incorporated into the first generation of stars, participated in nuclear fusion reactions that created heavy elements, and been dispersed back into space by a supernova explosion. But its journey was far from over. The enriched gas cloud containing our proton and countless other particles would drift through space for millions of years, gradually cooling and spreading out. Eventually, gravity would begin to collect this material into new structures. Some of it would form second-generation stars, enriched with heavy elements from the beginning of their lives. Some might become part of planetary systems, where solid worlds could form from the rocky elements created in stellar cores. The universe had been transformed by the first generation of stars. What had begun as a cosmos containing only hydrogen, helium, and lithium was now enriched with dozens of heavier elements. The chemical diversity necessary for complex molecules, planetary geology, and biological processes had been created and dispersed throughout space. This was perhaps the most important contribution of the first stars to cosmic evolution. They had taken the simple raw materials left over from the Big Bang and transformed them into the full periodic table of elements. They had created the chemical foundation upon which all future complexity would be built. Our proton, now potentially part of a heavy element nucleus, carried within itself the nuclear memory of stellar evolution. Its binding energy, mass, and chemical properties all bore witness to the extreme conditions it had experienced in the stellar interior. It was no longer the innocent hydrogen nucleus that had drifted through the cosmic dark ages. It had been transformed by fire into something new and more complex. The moment of explosion arrived, with a violence that dwarfed every other event in cosmic history. Our proton, which had spent millions of years nestled within the nuclear embrace of heavier and heavier elements, suddenly found itself at the center of the most energetic phenomenon the universe had yet produced. The supernova that tore apart its stellar home released more energy in a few seconds than our Sun will produce in its entire 10 billion year lifetime. The iron core where our proton resided had been growing steadily as silicon burning added more nuclear ash to the stellar center. For days or weeks, the core had teetered on the edge of catastrophe, held up only by the quantum mechanical pressure of electrons, forced into smaller and smaller spaces. The core was like a house of cards built from nuclear matter, each card representing the delicate balance between electromagnetic repulsion and nuclear attraction that held iron nuclei together. Then, in a moment that lasted less than a heartbeat, the balance failed catastrophically. A single electron capture reaction somewhere in the core tipped the balance, removing just enough pressure support to start an irreversible cascade. Like dominoes falling in sequence, one nuclear reaction triggered the next, and the carefully maintained equilibrium of millions of years collapsed in an instant. The collapse began gently at first, almost imperceptibly. The iron nuclei, including the one containing our proton, started to creep closer together as gravity overwhelmed the electron pressure that had supported them. The stellar core, which had been stable for months or years, suddenly discovered that it could no longer resist the crushing weight of the layers above it. But once the motion began, it accelerated with terrifying speed. The core collapse was not a gradual process, but an avalanche of matter falling inward faster than the speed of sound in the stellar material. Within a tenth of a second, the entire stellar core, containing more mass than our Sun, shrank from the size of Earth to something smaller than a city. Our proton felt the crushing embrace of gravity as never before. The iron nucleus it inhabited was squeezed against its neighbors with such force that individual atomic nuclei began to merge and break apart simultaneously. The carefully constructed nuclear architecture built up over millions of years of stellar burning started to crumble under pressures that exceeded anything found in normal matter. The density was rising beyond all comprehension. Material that had started out less dense than water became denser than rock, then denser than lead, then denser than the nucleus of an atom itself. At these incredible densities, the very nature of matter began to change in ways that challenged our understanding of physics. At densities approaching that of atomic nuclei themselves, strange quantum mechanical effects took over. The spaces between atomic nuclei disappeared entirely, and matter became a continuous soup of nuclear particles. Protons and neutrons, normally confined within separate nuclei, found themselves pressed together in configurations that had never existed anywhere in the universe, except perhaps in the first moments after the Big Bang. Our proton experienced these extreme conditions firsthand, as the iron nucleus it inhabited dissolved into the nuclear soup. The electromagnetic forces that had held the nucleus together for millions of years were overcome by gravitational forces billions of times stronger. Individual nuclear identity became meaningless, as matter was crushed to impossible densities. In this environment of unimaginable pressure and density, fundamental physical processes that normally required cosmic energies became commonplace. Protons and electrons, forced into impossibly close proximity, began to merge through the weak nuclear force in a process called electron capture. Our proton, which had maintained its identity as a positively charged particle since the first moment of the Big Bang, suddenly found itself converted into a neutron. This transformation was not unique to our proton. Throughout the collapsing core, trillions upon trillions of protons were being converted to neutrons every second. Each conversion emitted a neutrino, a ghostly particle that barely interacts with matter. These neutrinos shot away from their nuclear birthplaces at the speed of light, carrying with them information about the violent transformation taking place in the stellar core. The flood of neutrinos was so intense that even these weakly interacting particles began to affect the collapse. Normally, neutrinos pass through entire planets without interacting with a single atom, but in the ultra-dense core of the collapsing star, even neutrinos found it difficult to escape. They deposited some of their energy in the stellar material, adding to the already incredible pressures and temperatures. Our former proton, now a neutron, found itself part of the most exotic form of matter in the universe. The stellar core had become neutron star material, so dense that a teaspoon of it would weigh as much as a mountain on Earth. In this state, neutrons were packed together like marbles in a jar, with no empty space between them. But the conversion of the stellar core was not uniform or complete. Some regions collapsed faster than others, creating shock waves and instabilities that rippled through the neutron star material. The nuclear forces that had seemed so strong when building elements in the stellar core were now overwhelmed by gravitational forces billions of times stronger. The collapsing core was also spinning, a remnant of the rotation of the original star. As it shrank, it spun faster and faster, like a figure skater pulling in her arms during a spin. This rotation created additional stresses in the neutron star material, generating powerful magnetic fields and complex hydrodynamic flows. When the collapse reached its limit, something remarkable happened. The neutron star core, now compressed to the maximum density allowed by the laws of physics, suddenly became incompressible. The nuclear force itself provided a wall against further collapse, like a steel spring compressed to its absolute limit, suddenly pushing back with enormous force. The core had become the most rigid object in the universe, harder than diamond, harder than any material that could exist under earthly conditions. When the nuclear force finally said no more, it did so with a violence that shook the foundations of space-time itself. Our neutron, locked within this ultra-dense core material, experienced the formation of this cosmic trampoline. The infalling matter, still racing inward at significant fractions of the speed of light, crashed into this incompressible neutron star core and bounced. The collision was like throwing a rubber ball against a brick wall, except that the ball was made of stellar matter and the wall was made of nuclear force itself. The rebound sent a tremendous shockwave racing back toward the stellar surface. This shockwave carried more energy than had ever been concentrated in one place since the Big Bang itself. It was not merely hot and bright, but represented a fundamental disruption in the fabric of space and time. The shock heated matter to temperatures measured in tens of billions of degrees, far hotter than the core of any ordinary star. As the shockwave propagated outward through the star, it encountered the shells of partially burned nuclear fuel that surrounded the iron core. The shock heated this material to such extreme temperatures that explosive nuclear burning began instantly. Silicon was converted to iron in seconds, carbon fused to silicon almost instantaneously, and helium burned to carbon faster than the eye could follow. This explosive nucleosynthesis released tremendous additional energy, further strengthening the shock wave and accelerating its journey toward the stellar surface. The star had become a nuclear bomb with a mass measured in solar units, detonating from the inside out in a process that defied imagination. The shock wave also created the most extreme nuclear physics laboratory in the universe. In the intense neutron flux behind the shock front, atomic nuclei captured neutrons faster than they could decay radioactively. This R process, or rapid neutron capture process, built up neutron-rich isotopes that existed nowhere else in nature. In mere seconds, nuclei capturing neutron after neutron grew heavier and heavier, climbing the periodic table far beyond iron. Gold, platinum, uranium, thorium, and dozens of other heavy elements were created in these few moments of explosive nucleosynthesis. Elements that would have taken billions of years to create through normal stellar processes were forged in the blink of an eye. Our neutron, caught up in this nuclear fury, found itself incorporated into increasingly heavy and exotic nuclei. It might have become part of a gold nucleus with 79 protons, or a uranium nucleus with 92 protons, or even heavier elements that do not exist naturally on Earth. The R process was writing the final chapters of the periodic table in letters of fire and neutron capture. Some of these super-heavy elements were so unstable that they immediately began to decay through chains of radioactive transformations. Alpha particles and beta particles streamed away from the unstable nuclei as they sought more stable configurations. The stellar interior became a radioactive cauldron where nuclear species that had never existed before flickered into being and transformed into something else in fractions of a second. The shockwave continued its relentless journey toward the stellar surface, taking several hours to traverse the outer layers of the massive star. During this time, it continued to heat and accelerate matter, creating a bow wave of superheated plasma that carried with it all the nuclear products of the stellar core. When the shock wave finally reached the stellar surface, it marked the beginning of one of the most spectacular displays in the cosmos. The supernova explosion announced itself to the universe with a brilliance that outshone entire galaxies. From our neutron's perspective, this was the moment of liberation after millions of years of confinement in the stellar interior. For the first time since the Big Bang, our particle experienced the vacuum of space directly. The neutron, whether free or bound in a heavy nucleus, was suddenly part of an expanding fireball racing away from the stellar core at speeds measured in tens of thousands of kilometers per second. The explosion had become a cosmic cannon, firing heavy elements across interstellar space with tremendous violence. The supernova was not a simple spherical explosion, but developed complex, three-dimensional structure as it expanded. Jets of material shot out from the polar regions of the star at nearly the speed of light, while the equatorial regions expanded more slowly and with greater mass. This created an hourglass or butterfly shape that would evolve over thousands of years. Our neutron found itself part of this cosmic sculpture, perhaps embedded in a clump of newly forged heavy elements racing through one of the polar jets. The material around it glowed white-hot from the energy of the explosion, radiating across the entire electromagnetic spectrum from radio waves to gamma rays. This was matter that had never seen starlight, forged in the deepest interior of a star, and now suddenly exposed to the cosmos. The temperature of the expanding ejector was initially measured in millions of degrees, hot enough to strip all electrons from atoms and create a fully ionized plasma. Our neutron, if bound in a heavy nucleus, found its atomic environment completely disrupted as electrons were torn away by the thermal violence of the explosion. For now, nuclei existed as bare cores, surrounded by a sea of free electrons. As the supernova ejector expanded into space, it began to interact with the interstellar medium that surrounded the star. The blast wave compressed and heated the ambient gas, creating a forward shock that raced ahead of the actual stellar material. Behind this shock, a complex structure of reflected waves, turbulence, and instabilities developed. The expansion was not into empty space, but into a medium that had been modified by the massive star during its lifetime. Stellar winds from the progenitor star had carved out a low-density bubble in the surrounding gas, creating a cavity that the supernova explosion could expand into more easily. This bubble would channel and shape the explosion, affecting how the heavy elements would ultimately be distributed. As the supernova remnant expanded and cooled over days and weeks, atoms began to form again as electrons were recaptured by nuclei. Our neutron, if it had remained bound in a heavy element nucleus throughout the explosion, experienced the reformation of its atomic environment. Electron shells filled once more, and the nucleus regained its retinue of orbiting electrons. The cooling process was not uniform throughout the expanding remnant. Dense knots of material cooled more slowly than tenuous regions, creating a complex temperature and density structure. Some regions remained hot and ionized for years, while others cooled quickly enough for molecules and even dust grains to form. Our particle found itself in an environment unlike anything that had existed before in cosmic history. The composition of this material was radically different from anything in the early universe. Instead of being almost entirely hydrogen and helium, the supernova ejector contained comparable amounts of heavier elements like oxygen, carbon, silicon, and iron. This chemical enrichment would have profound consequences for any future star formation in the region. Heavy elements act as coolants in star-forming regions, radiating away thermal energy through atomic transitions that hydrogen and helium cannot produce. This allows gas clouds to collapse more easily under their own gravity, leading to more efficient star formation. The supernova had also created an enormous cavity in the interstellar medium, a bubble of hot, low-density gas that would persist for millions of years. This superbubble, as astronomers call it, provided a reservoir where subsequent generations of massive stars could explode without significantly affecting the surrounding medium. Within this cavity, our heavy element atom drifted through a wonderland of exotic plasma physics. Magnetic fields, initially frozen into the stellar material, were stretched and twisted by the expansion, creating complex field configurations that could accelerate particles to tremendous energies. Some particles gained so much energy that they became cosmic rays, high-energy projectiles that would race through the galaxy for millions of years. The supernova remnant became a powerful source of non-thermal radiation, as these energetic particles interacted with magnetic fields and ambient matter. Radio waves generated by synchrotron emission from relativistic electrons made the remnant shine across the electromagnetic spectrum. X-ray emission from shocked gas revealed the complex internal structure of the expanding blast wave. Our atom was surrounded by this cosmic light show as it continued its journey away from the explosion site. The material it traveled with carried the thermal and kinetic energy of the blast, remaining hot and active for thousands of years after the initial explosion. This long-lived activity would make supernova remnants some of the most dynamic and energetic objects in the galaxy. The heavy elements dispersed by the supernova were not distributed evenly through space. Elements created in different burning phases of the star's life were ejected at different velocities and in different directions. Iron and nickel from the core traveled more slowly and stayed closer to the explosion site, while lighter elements from the outer layers raced farther into space. Our heavy element atom might have found itself in a region where the concentration of metals was higher than anywhere else in the local universe. This chemical stratification would leave fingerprints in the composition of future stars and planets that formed from supernova-enriched material. The supernova also dispersed radioactive isotopes that would continue to decay for thousands or millions of years. Radioactive iron-57 decayed to cobalt-57, providing energy that kept parts of the remnant glowing long after the initial explosion. Aluminum-26, with a half-life of about 1 million years, would serve as a tracer of supernova material mixed into the general interstellar medium. As decades passed, the supernova remnant began to show its age. The initial symmetry of the explosion gave way to a more complex structure as the blast wave encountered variations in the surrounding medium. Fingers of hot gas pushed into low-density regions, while dense clouds resisted the expansion, creating an intricate lacework of shocked material. Our atom experienced these cosmic weather patterns as it drifted through different regions of the remnant. Sometimes it found itself in hot, tenuous regions where temperatures remained in the millions of degrees. Other times it passed through cooler, denser condensations, where molecules were beginning to form for the first time since the explosion. The remnant was also becoming a site of active chemistry. In the cooler regions, atoms were beginning to combine into simple molecules. Carbon monoxide, silicon monoxide, and even more complex species formed in the post-shock gas. Our atom might have participated in these first tentative steps toward molecular complexity in the metal-enriched environment. The magnetic fields in the remnant had evolved into a complex tangle of loops and knots. These fields controlled the motion of charged particles and influenced the emission of radiation from the remnant. They also provided a mechanism for transferring energy from the expanding blast wave to the ambient medium over long timescales. Hundreds of years after the explosion, the supernova remnant had grown to encompass dozens of light years of space. The blast wave had slowed considerably as it encountered more and more interstellar matter, but it was still moving fast enough to shock and heat the ambient gas. Our atom was now part of a structure larger than some star-forming regions. The remnant had also begun to fragment into distinct components. The original blast wave continued to expand outward, but behind it, instabilities had created a complex network of dense filaments and bubbles. Some regions were collapsing under their own gravity, while others were being stretched thin by hydrodynamic flows. In some of these collapsing regions, the density was becoming high enough to eventually trigger star formation. The heavy elements dispersed by the supernova were providing the seeds for a new generation of stars that would be chemically enriched from birth. These second-generation stars would burn longer and more stably than their primordial ancestors. Our atom might have found itself in one of these future star-forming regions, where its journey through the cosmos would eventually come full circle, but that lay far in the future. For now, it continued to expand with the remnant, experiencing the slow transformation of explosive violence into more sedate cosmic evolution. The supernova had fundamentally altered the structure of the local interstellar medium. The explosion had excavated a cavity hundreds of light years across, filled with hot, tenuous gas enriched with heavy elements. This cavity would persist for millions of years, affecting the motion of gas and the formation of stars throughout the region. Other massive stars in the vicinity were approaching the ends of their own lives. When they exploded as supernovae, their blast waves would interact with the remnant of our original explosion, creating an even more complex bubble structure. This process of sequential supernova explosions in stellar associations creates the superbubbles and chimneys that transport hot gas from the galactic disk into the halo. Our atom was destined to participate in this galactic fountain, riding flows of hot gas that could carry it far above the plane of the galaxy before it eventually cooled and fell back. This vertical mixing would help distribute heavy elements throughout the galaxy's three-dimensional structure. The remnant was also producing cosmic rays that would travel far beyond its visible boundaries. These high-energy particles, accelerated by magnetic fields in the shock regions, would propagate throughout the galaxy for millions of years. Some might even escape the galaxy entirely, carrying news of the explosion to intergalactic space. As the supernova remnant continued to age and evolve, it gradually merged with the general structure of the interstellar medium. After several thousand years, it would lose its distinct identity and become part of the complex, multi-phase structure that characterizes the space between stars. But its legacy would persist in the heavy elements it had dispersed and the energy it had deposited in interstellar space. Our atom, forged in the stellar core and scattered by cosmic violence, had completed one phase of its infinite journey through space and time. It was no longer the simple hydrogen nucleus that had emerged from the cosmic dark ages, but a complex heavy element carrying within its nuclear structure the compressed history of stellar evolution. The supernova had been more than just an explosion. It had been a moment of cosmic alchemy that transformed the death of one star into the birth of countless new possibilities. Every heavy element in the universe, including those that would someday form planets and living beings, owed its existence to such moments of stellar sacrifice. The dispersal phase of our atom's cosmic journey was drawing toward a close, but the adventure was far from over. Enriched by nuclear fire and scattered by cosmic thunder, our atom was ready for new chapters in its story. Somewhere in the future lay gravitational collapse into new stars, incorporation into planetary systems, and perhaps even participation in the complex chemistry of living organisms. The explosion had ended, but its consequences would ripple through space and time for billions of years to come. Our atom, carrying within itself the memory of stellar fire and the potential for future complexity, drifted onward through the enriched cosmos, ready for whatever cosmic adventure awaited it next. The moment of explosion arrived with a violence that dwarfed every other event in cosmic history. Our proton, which had spent millions of years nestled within the nuclear embrace of heavier and heavier elements, suddenly found itself at the center of the most energetic phenomenon the universe had yet produced. The supernova that tore apart its stellar home released more energy in a few seconds than our sun will produce in its entire 10 billion year lifetime. The iron core where our proton resided had been growing steadily as silicon burning added more nuclear ash to the stellar center. For days or weeks, the core had teetered on the edge of catastrophe, held up only by the quantum mechanical pressure of electrons forced into smaller and smaller spaces. Then, in a moment that lasted less than a heartbeat, the balance failed. The collapse began gently at first, almost imperceptibly. The iron nuclei, including the one containing our proton, started to creep closer together as gravity overwhelmed the electron pressure that had supported them. But once the motion began, it accelerated with terrifying speed. Within a tenth of a second, the entire stellar core, containing more mass than our sun, shrank to a fraction of its original size. Our proton felt the crushing embrace of gravity as never before. The iron nucleus it inhabited was squeezed against its neighbors, with such force that individual atomic nuclei began to merge. The carefully constructed nuclear architecture, built up over millions of years of stellar burning, started to crumble under the immense pressure. At densities approaching that of atomic nuclei themselves, strange things began to happen. Protons and electrons, forced into impossibly close proximity, began to merge through the weak nuclear force. Our proton, which had maintained its identity as a positively charged particle since the first moment of the Big Bang, suddenly found itself converted into a neutron in a process called electron capture. In this transformation, our proton absorbed an electron from the surrounding stellar plasma and emitted a neutrino, a ghostly particle that barely interacts with matter. The neutrino shot away from the collision at the speed of light, carrying with it information about the violent transformation taking place in the stellar core. Trillions upon trillions of such neutrinos were created every second as the core collapsed, forming a flood of nearly massless particles escaping from the star's interior. Our former proton, now a neutron, found itself part of the most exotic form of matter in the universe. The stellar core had become neutron star material, so dense that a teaspoon of it would weigh as much as a mountain. At these incredible densities, matter existed in states that challenged our understanding of physics, with neutrons packed together like marbles in a jar. But the conversion of the stellar core was not uniform or complete. Some regions collapsed faster than others, creating shock waves and instabilities that rippled through the neutron star material. The nuclear forces that had seemed so strong when building elements in the stellar core were now overwhelmed by gravitational forces billions of times stronger. When the collapse reached its limit, something remarkable happened. The neutron star core, now compressed to its maximum possible density, suddenly became incompressible. The nuclear force itself provided a wall against further collapse, like a spring compressed to its limit suddenly pushing back. The infalling matter crashed into this neutron star core and bounced, creating a shock wave of unimaginable power. Our neutron, locked within the ultra-dense core material, experienced the formation of this cosmic trampoline. The core had become so stiff that the outer layers of the collapsing star, still racing inward at significant fractions of the speed of light, could not penetrate it. Instead, they rebounded, sending a tremendous shock wave racing back toward the stellar surface. This shock wave carried more energy than had ever been concentrated in one place since the Big Bang itself. As it propagated outward through the star, it encountered the shells of partially burned nuclear fuel that surrounded the iron core. The shock heated this material to billions of degrees, triggering explosive nuclear burning that released even more energy. The shock wave also created conditions perfect for rapid nuclear processes that could never occur during normal stellar burning. In the intense neutron flux behind the shock front, atomic nuclei captured neutrons faster than they could decay radioactively. This R process, or rapid neutron capture process, built up neutron-rich isotopes that would later decay into the heaviest stable elements in nature. Gold, platinum, uranium, thorium, and dozens of other heavy elements were created in these few seconds of explosive nucleosynthesis. Elements that could never be produced by normal stellar fusion were forged in the violence of the supernova explosion. Our neutron, caught up in this nuclear fury, might have been incorporated into some of these exotic heavy elements before the explosion scattered them into space. The shock wave reached the stellar surface after several hours of travel through the star's outer layers. When it broke through into space, it marked the beginning of one of the most spectacular displays in the cosmos. The supernova blazed forth with the light of billions of suns, visible across intergalactic distances. For our neutron and the countless other particles created or modified in the explosion, this was the moment of liberation. Matter that had been trapped in the stellar interior for millions of years was suddenly hurled into space at speeds of tens of thousands of kilometers per second. The supernova had become a cosmic cannon, firing heavy elements across interstellar space. The explosion was not symmetric. Jets of material shot out from the polar regions of the star at nearly the speed of light, while the equatorial regions expanded more slowly. This created a complex, three-dimensional structure that would evolve over thousands of years as the supernova remnant expanded and interacted with the surrounding interstellar medium. Our neutron found itself part of a clump of heavy elements racing through space faster than it had ever moved before. The temperature of this expanding gas was millions of degrees, hot enough to strip electrons from atoms and create a glowing plasma that would remain visible for centuries. This was material that had never seen the light of day, forged in the innermost core of a star, and now suddenly exposed to the vacuum of space. As the supernova ejector expanded, it began to cool and change. The intense heat of the explosion gradually gave way to the cold of interstellar space. Heavy elements that had been completely ionized began to recapture electrons, forming atoms once again. Our neutron, if it had remained free or been incorporated into a light nucleus, might have captured a proton and an electron to become a hydrogen atom once more. But more likely, our neutron had become part of a heavy element nucleus during the explosive nucleosynthesis. Iron, cobalt, nickel, and even heavier elements like gold and platinum now carried our particle within their nuclear embrace. These heavy elements would behave very differently in space than the simple hydrogen and helium that dominated the early universe. The expanding supernova remnant created a bubble of hot, enriched gas that pushed against the surrounding interstellar medium. This created a shock wave that continued to accelerate particles and heat gas long after the initial explosion. The supernova had become a cosmic laboratory, creating conditions unlike anything that existed elsewhere in the universe. Within this bubble, Our heavy element atom containing the former proton drifted through a wonderland of exotic physics. Magnetic fields twisted and coiled through the plasma, accelerating charged particles to tremendous energies. Some particles gained so much energy that they became cosmic rays, high-energy projectiles that would race through the galaxy for millions of years before finally coming to rest. The supernova remnant also became a source of radio waves, X-rays, and gamma rays as energetic electrons spiraled around magnetic field lines. These emissions made the remnant visible to astronomers across the electromagnetic spectrum, announcing to the universe that another star had completed its nuclear journey and returned its contents to space. Other atoms shared our particles' fate, each carrying within their nuclear structure the memory of stellar nucleosynthesis. Carbon atoms forged in helium burning, oxygen created by alpha capture, silicon built up through successive fusion reactions, and iron from the last desperate attempts of nuclear burning to support the star against gravity. All were now free to begin new chapters in their cosmic stories. The elements dispersed by the supernova were not distributed evenly through space. Heavier elements, created in the deepest layers of the star and ejected at lower velocities, tended to remain closer to the explosion site. Lighter elements, blown out from the outer layers at higher speeds, traveled farther and mixed more thoroughly with the interstellar medium. Our heavy element atom found itself in a region where the concentration of metals, as astronomers call all elements heavier than hydrogen and helium, was higher than anywhere else in the local universe. This would have profound consequences for any future star formation in the region, as the presence of heavy elements dramatically changes how gas clouds collapse and ignite. Heavy elements act as coolants in star-forming regions, radiating away thermal energy more efficiently than hydrogen and helium alone. This allows gas clouds to collapse more easily under their own gravity, leading to the formation of smaller, longer-lived stars. The universe was about to enter a new era of stellar evolution, characterized by more modest stars that would burn for billions rather than millions of years. As the supernova remnant continued to expand, it began to interact more strongly with the surrounding interstellar medium. The fast-moving ejector plowed into clouds of gas and dust, creating complex shock structures and triggering new episodes of star formation. The death of one star was catalyzing the birth of many others. Our atom experienced these cosmic weather patterns as it drifted through the expanding bubble. Sometimes it found itself in regions of high density and turbulence, where magnetic fields and shock waves created spectacular displays of plasma physics. Other times it entered quieter regions where the only motion was the steady expansion of the remnant itself. The chemical composition of the interstellar medium was being transformed by the supernova fallout. Regions that had contained only primordial hydrogen and helium were now enriched with oxygen, carbon, silicon, iron, and dozens of other elements. For the first time since the Big Bang, the raw materials for rocky planets and complex chemistry were available in significant quantities. The supernova had also created radioactive isotopes that would continue to decay for thousands of years. Cobalt-56, created in the explosion, decayed to iron-56, with a half-life of about 77 days. Titanium-44 decayed to calcium-44 over several decades. These radioactive decay chains provided the energy that kept the supernova remnant glowing long after the initial explosion had faded. Our atom might have been part of these radioactive species, unstable configurations of protons and neutrons that would eventually settle into more stable arrangements. The decay process would continue the element creation story on a smaller scale, fine-tuning the final abundances of elements dispersed by the supernova. Years passed, then decades, then centuries. The supernova remnant continued to expand and evolve, but more slowly now, as it encountered resistance from the interstellar medium. The initial explosion had been violent and brief, but the consequences would unfold over geological timescales. Our atom found itself in an environment unlike anything that had existed before in cosmic history. The interstellar medium was no longer the pure, simple mixture of hydrogen and helium that had characterized the early universe. It was now a complex soup containing dozens of elements in various ionization states, mixed with magnetic fields, cosmic rays, and the lingering heat of stellar explosions. This enriched material would not remain dispersed forever. Gravity, patient but persistent, would eventually begin to collect the heavy elements into new structures. Some would be incorporated into the next generation of stars, where they would participate in stellar nucleosynthesis once again. Others would find their way into planetary systems, where they could form solid worlds and serve as the chemical basis for complex molecules. The supernova had been a cosmic recycling center, taking the nuclear ash of stellar burning and redistributing it throughout space. Our atom was now part of this grand circulation of matter, carrying within its nuclear structure the history of its stellar origin and the potential for future chemical adventures. But the story of dispersal was far from over. The supernova remnant would continue to expand for tens of thousands of years, eventually merging with the general interstellar medium and losing its distinct identity. By then, the heavy elements it contained would be thoroughly mixed with the primordial gas, creating the chemically enriched environment that would characterize the universe for eons to come. Other supernovae were exploding throughout the galaxy and beyond, each adding its contribution to the growing abundance of heavy elements in space. Stellar winds from massive stars also carried metals into the interstellar medium, though more gently than the violent dispersal of supernova explosions. The universe was undergoing a gradual chemical enrichment that would make increasingly complex structures possible. Our atom drifted through this evolving cosmos, no longer the simple hydrogen nucleus that had emerged from the cosmic dark ages. It now carried within its structure the compressed history of stellar nucleosynthesis, a record of the extreme conditions needed to fuse light elements into heavy ones. Every bond that held its nucleus together spoke of temperatures measured in hundreds of millions of degrees and pressures that crushed matter to incredible densities. The atom also carried the potential for chemical complexity that had never before existed in the universe. Heavy elements could form molecular bonds in ways that hydrogen and helium never could. They could create the complex chemistry that would eventually lead to self-replicating molecules and living organisms. The supernova had not just dispersed matter, it had dispersed possibility itself. As the supernova remnant aged, it began to develop internal structure. Dense knots of material formed where the explosion had been particularly energetic, or where the ejector had collided with clumps of interstellar gas. These knots would evolve into distinct condensations that might someday become the cores of new stars or planetary systems. Our atom might have found itself in one of these dense regions, where the concentration of heavy elements was particularly high. Here, the stage was being set for a new kind of star formation, one that would proceed differently because of the presence of metals. These second-generation stars would be smaller and longer-lived than their primordial ancestors, capable of maintaining stable nuclear burning for billions of years. Some of the material ejected by the supernova would travel much farther, carried by galactic winds and the rotation of the galaxy itself, to regions far from the explosion site. This long-range transport of heavy elements helped to enrich the entire galactic disk, spreading the products of stellar nucleosynthesis over vast volumes of space. The dispersal process was not random, but followed the complex dynamics of galactic structure. Spiral arms, where stars form most actively, became preferentially enriched with heavy elements. The galactic halo, populated by old stars that formed before significant chemical enrichment had occurred, remained relatively metal-poor. This created a chemical gradient throughout the galaxy that would influence star formation for billions of years. Our atom was part of this grand galactic circulation, its ultimate destination determined by the complex interplay of explosion dynamics, interstellar turbulence, and galactic motion. It might end up in a star-forming region close to where it was created, or it might travel halfway across the galaxy before finding a new gravitational home. The supernova had also created elements with unusual isotopic compositions that would serve as fingerprints of explosive nucleosynthesis. Iron-60, a radioactive isotope with a half-life of several million years, could only be created in significant quantities in supernova explosions. The detection of this isotope in ancient terrestrial materials would later provide evidence that supernovae had occurred near our solar system during Earth's early history. Similarly, aluminum-26, another supernova product, would be found incorporated into primitive meteorites, indicating that a supernova explosion occurred near our forming solar system about 4.5 billion years ago. This cosmic coincidence may have triggered the collapse of the gas cloud that became our sun and planets, making the solar system itself a product of stellar death and dispersal. The effects of the supernova explosion rippled outward in ways that extended far beyond the simple dispersal of heavy elements. The shock waves created by the explosion compressed nearby gas clouds, triggering episodes of star formation that might not have occurred otherwise. Massive stars in these new formation regions would themselves eventually explode as supernovae, creating a chain reaction of stellar birth and death that enriched larger and larger regions of space. Our atom was witness to this cosmic fireworks display as successive generations of massive stars lived brief, spectacular lives before exploding and adding their own contributions to the growing abundance of heavy elements. Each new generation of stars formed from material that was slightly more metal-rich than the last, leading to a gradual but steady increase in chemical complexity throughout the universe. The supernova had also produced exotic forms of matter that existed nowhere else in nature. Neutrons and protons compressed to nuclear density, strange quarks and other exotic particles, and magnetic fields millions of times stronger than anything found on Earth. These extreme states of matter provided laboratories for testing the fundamental laws of physics under conditions that could never be replicated on Earth. As our atom continued its journey through the enriched interstellar medium, it occasionally encountered the cosmic rays produced by the supernova explosion. These high-energy particles, accelerated to nearly the speed of light by the remnant's magnetic fields, could break apart atomic nuclei and create new isotopes through nuclear spallation reactions. Some cosmic rays had enough energy to split heavy nuclei into lighter fragments, while others could add particles to nuclei to create heavier isotopes. This cosmic ray bombardment added another layer of complexity to the isotopic composition of the interstellar medium, creating rare isotopes that could serve as tracers of cosmic ray interactions. The legacy of the supernova extended far beyond its immediate environment. The heavy elements it dispersed would eventually find their way into new star systems, where they would make possible the formation of rocky planets, atmospheres, oceans, and potentially life itself. Our atom might someday become part of a planetary core, a mountain range, an ocean, or even a living organism. The dispersal phase of our atom's cosmic journey was drawing to a close, but its story was far from over. Scattered by the violence of stellar death, enriched by the alchemy of nuclear fusion, and launched on a new trajectory through space, our atom was ready for the next chapter of its infinite adventure. The universe had grown more complex, more chemically diverse, and more interesting because of the sacrifice of a single star. The supernova explosion had been a moment of cosmic violence that transformed destruction into creation, turning the death of one star into the birth of countless new possibilities. Our atom, forged in stellar fire and scattered by cosmic thunder, carried within itself the potential for all the complexity that would follow in the universe's continuing evolution. The explosion had ended, but its consequences would reverberate through space and time for billions of years to come. Every heavy element in the universe, including those that would someday form planets and living beings, owed its existence to moments like this, when stars gave up their lives to enrich the cosmos with the building blocks of complexity and wonder. Millions of years passed as our atom drifted through the enriched cosmos, carried by galactic winds and the slow circulation of interstellar matter. The violent memory of the supernova explosion had faded into gentle motion through space, but the transformation it had wrought remained embedded in the atomic nucleus that now housed our original proton deep within its nuclear embrace. The galaxy had changed profoundly since those early days of pristine hydrogen and helium. Successive generations of massive stars had lived their brief, brilliant lives and died in spectacular explosions, each adding their contribution to the growing abundance of heavy elements in space. What had once been a chemically simple universe was now a complex mixture of dozens of different elements, creating possibilities that had never existed before. Our atom found itself part of this cosmic evolution, no longer the innocent hydrogen of the Dark Ages, but now perhaps an iron nucleus with 26 protons and 30 neutrons, or a carbon atom with its 6 protons and 6 neutrons, or any of a dozen other elements forged in stellar cores. Whatever its nuclear identity, it carried within its binding energy the memory of the extreme conditions needed to create heavy elements from light ones. The interstellar medium through which our atom traveled was itself transformed. What had once been a smooth, nearly uniform distribution of gas was now a complex, turbulent structure. Supernova explosions had carved out bubbles and cavities filled with hot, thin gas. Stellar winds had created tunnels and channels through which matter could flow. The space between stars had become a dynamic, evolving environment where chemistry could flourish. In some regions, the density was low and the temperature high, creating conditions where atoms remained ionized and chemical reactions proceeded slowly. But in other regions, vast molecular clouds had formed, dense and cold enough for atoms to combine into increasingly complex molecules. These clouds were the stellar nurseries of the galaxy, the places where gravity could overcome thermal pressure and collapse matter into new stars. Our atom found itself drawn toward one of these molecular clouds, attracted by the gentle but persistent pull of gravity, acting over vast distances and enormous timescales. The journey took millions of years, but eventually our atom became part of a cloud that would become the birthplace of a new solar system. This molecular cloud was fundamentally different from those that had existed in the early universe. Instead of being composed almost entirely of hydrogen and helium, it contained a significant fraction of heavier elements. Oxygen, carbon, nitrogen, silicon, magnesium, iron, and dozens of other elements were mixed throughout the cloud, creating a chemical richness that would have profound consequences for what could form there. The heavy elements served as cosmic refrigerators, cooling the cloud through radiative emission lines that hydrogen and helium could not produce. When a carbon atom absorbed thermal energy and emitted a photon, or when oxygen molecules rotated and radiated away rotational energy, the cloud lost heat and could contract more easily under its own gravity. Our atom experienced this cooling process firsthand as it participated in the chemical cycles that regulated the cloud's temperature. If it was a carbon atom, it might have formed carbon monoxide with an oxygen atom, creating one of the most important cooling agents in molecular clouds. If it was silicon, it might have become part of a tiny dust grain, a microscopic solid particle that could radiate heat efficiently. The molecular cloud was not uniform but had a complex, filamentary structure. Dense cores were embedded within more tenuous material, and turbulent motions stirred the gas on all scales from planetary systems to the cloud itself. Our atom drifted through this three-dimensional tapestry, sometimes finding itself in dense, cold regions and sometimes in more diffuse, warmer areas. Chemistry was proceeding at a pace unknown in the early universe. In the densest, coldest parts of the cloud, molecules were forming that would have been impossible in a hydrogen-helium universe. Water, methane, ammonia, and even more complex organic molecules assembled from the heavy elements scattered by ancient supernovae. Our atom might have participated in this molecular dance, linking with other atoms to form chemical bonds that had never existed in the primordial cosmos. If it was a carbon atom, it might have become part of formaldehyde, carbon monoxide, or even more complex organic molecules that would serve as the building blocks for future biology. As the molecular cloud continued to evolve, gravitational instabilities began to grow. Dense regions became denser as they attracted more matter, while rarefied regions became more empty. The cloud was developing structure on all scales, from continent-sized clumps down to cores that would eventually become individual stars and planetary systems. Our atom found itself in one of these collapsing cores, drawn inward by gravity along with gas and dust that would eventually become a new star and its family of planets. This core was destined to become our solar system, though that outcome lay billions of years in the future. For now, it was simply a slowly contracting clump of enriched material in a vast molecular cloud. The collapse proceeded much as stellar collapse had in the early universe, but with important differences. The presence of heavy elements made the process more efficient, allowing the cloud to radiate away thermal energy and contract more rapidly. The heavy elements also provided a source of opacity that would later prove crucial for planetary formation. As the core contracted, it began to rotate faster, conserving angular momentum, just as a figure skater spins faster when she pulls in her arms. This rotation prevented all the material from falling directly into the center, instead forming a spinning disk of gas and dust around the growing central condensation that would become the Sun. Our atom found itself in this protoplanetary disk, a flattened structure where the raw materials for planets were being organized for the first time. The disk was hot near the center, where the proto-sun was beginning to generate heat through gravitational contraction, and cold in the outer regions where temperature approached interstellar values. The temperature gradient in the disk determined what kinds of materials could condense from the gas phase. Close to the forming sun, only the most refractory elements and compounds could survive as solids. Silicates containing silicon, magnesium, aluminum, and iron were among the first materials to condense into solid grains. Our atom, if it was one of these elements, might have found itself incorporated into one of these first solid particles in the solar system. Further out in the disk, where temperatures were lower, more volatile compounds could condense. Water ice, methane ice, ammonia ice, and other frozen gases formed a second population of solid particles. The location in the disk where water could first condense as ice is called the snow line, and it would prove to be a crucial boundary for planetary formation. The solid particles in the disk began to stick together through a process that started gently but accelerated dramatically. Tiny dust grains, perhaps containing our atom, collided and adhered to each other through van der Waals forces and simple mechanical entanglement. These collisions were initially gentle enough that the particles could stick rather than shatter. Our atom experienced these first tentative steps toward planet building as the grain it inhabited grew larger and more massive. Grain by grain, particle by particle, the building blocks of planets accumulated through countless gentle collisions in the protoplanetary disk. The process was patient and persistent, turning microscopic dust into pebbles, pebbles into boulders, and boulders into asteroids. As the solid particles grew larger, their gravitational influence became more significant. What had started as a process dominated by gentle collisions and chemical adhesion began to be influenced by gravity as well. The larger bodies could attract smaller ones, accelerating their growth through gravitational focusing. Our atom might have found itself part of a planetesimal, one of the first truly large solid bodies in the solar system. These planetesimals ranged in size from mountains to small planets, and they represented the initial phase of building the terrestrial worlds that would eventually include Earth. The inner solar system, where our atom might reside, was becoming a chaotic place as these planetesimals collided and merged. Some collisions were gentle enough that the bodies could merge and grow larger. Others were so violent that they shattered both participants, sending fragments flying throughout the inner disk. Through this process of collisional accumulation, our atom became part of larger and larger bodies. If it started in a dust grain, it might have become part of a pebble, then a boulder, then an asteroid, and eventually one of the terrestrial planets. Each stage of growth involved countless collisions, impacts, and mergers that gradually assembled planetary mass objects from cosmic debris. The formation of the terrestrial planets was a violent process that lasted approximately 100 million years. Our atom experienced this cosmic construction project firsthand, feeling the heat and pressure of countless impacts as the materials that would become Earth slowly assembled. Each collision added more mass and generated enormous amounts of heat, keeping the growing planet molten and chemically active. During this period of heavy bombardment, our atom might have been vaporized, melted, chemically altered, and relocated countless times. The early Earth was not the stable, layered planet we know today, but a hot, turbulent world where rock and metal existed in a partially molten state, and the surface was constantly being reshaped by new impacts. The heavy elements that had been mixed uniformly throughout the protoplanetary disk began to segregate according to their chemical properties. Iron and nickel, being dense and having an affinity for each other, sank toward the center of the forming planet to create the metallic core. Lighter silicate materials formed the mantle, while the most volatile compounds were lost to space or concentrated in the outer layers. Our atom's ultimate location in this differentiated planet depended on its chemical identity. If it was an iron atom, it might have joined the Great Migration toward the planetary core, sinking through molten rock over millions of years to become part of Earth's metallic heart. If it was silicon, magnesium, or aluminum, it likely remained in the silicate mantle. If it was part of a more volatile compound, it might have ended up in the crust, the atmosphere, or even been lost to space entirely. The formation of the terrestrial planets was not simply a matter of accumulating solid material. The growing planets also captured some of the gas from the protoplanetary disk, creating primitive atmospheres. However, these early atmospheres were quite different from those that would later develop through geological and biological processes. Our atom might have found itself part of this early atmosphere, perhaps as carbon dioxide, water vapor, or another gas that could survive in the inner solar system. The early atmosphere was thick and hot, heated by the ongoing bombardment of planetesimals and the decay of radioactive elements incorporated during planetary formation. The completion of planetary formation marked a major transition in our atom's cosmic journey. No longer was it simply drifting through space or participating in stellar nucleosynthesis. Now it was part of a solid world, embedded in the rock, metal, or atmosphere of a planet that would evolve and change over geological time. Earth's early history was dominated by processes that would seem alien today. The surface was largely molten, constantly reshaped by impacts and volcanic activity. The atmosphere was thick and reducing, containing little or no free oxygen. The young sun was fainter than today, providing less energy to the Earth system. Our atom participated in the early geological evolution of Earth as the planet slowly cooled and developed the layered structure we see today. If it was in the interior, it experienced the heat and pressure of planetary differentiation as heavy elements sank and light elements rose. If it was near the surface, it witnessed the formation of the first solid crust as the molten rock finally cooled enough to solidify. One of the most important events in Earth's early history was the formation of the Moon, believed to have resulted from a giant impact between Earth and a Mars-sized body called Theia. This collision was so violent that it vaporized much of both planets, creating a disk of molten material around Earth that eventually coalesced to form the Moon. Our atom might have been part of this cataclysmic event, vaporized and thrown into space before condensing again as part of either Earth or the Moon. The giant impact was a reminder that even after planetary formation, the solar system remained a dynamic and sometimes violent place where major changes could occur suddenly. As Earth continued to cool, water vapor in the atmosphere began to condense and fall as rain. This marked the beginning of the formation of Earth's oceans, as water accumulated in the low-lying areas of the planet's surface. Our atom, if it was part of a water molecule, might have participated in this first rainfall, helping to fill the basins that would become the world's oceans. The oceans were crucial for Earth's subsequent evolution because they provided a stable environment where complex chemistry could proceed. Water is an excellent solvent, allowing different chemicals to mix and react in ways that would be impossible in solid rock or thin atmosphere. The oceans became Earth's first chemical laboratory, where the building blocks of life would eventually assemble. Our atom might have found itself dissolved in these ancient seas, participating in chemical reactions that had never before occurred on such a scale. If it was a carbon atom, it might have become part of dissolved carbon dioxide, carbonic acid, or bicarbonate ions. If it was phosphorus, it might have formed phosphate groups that would later prove essential for life. The early oceans were chemically very different from modern seas. They were more acidic, contained higher concentrations of dissolved metals, and lacked the oxygen that characterizes today's oceans. But they provided an environment where complex organic molecules could form and persist, setting the stage for the origin of life. The emergence of life on Earth represents perhaps the most significant transition our atom would experience in its cosmic journey. Somewhere in the early oceans, probably around deep-sea vents, where chemical energy was abundant, simple organic molecules began to assemble into more complex structures capable of self-replication and metabolism. Our atom might have been among the first to be incorporated into living matter, becoming part of the earliest cells that appeared on Earth over 3.5 billion years ago. If it was a carbon atom, it might have become part of the backbone of an organic molecule. If it was phosphorus, it might have joined a phosphate group in an early DNA or RNA molecule. If it was sulfur, it might have become part of a protein. The transition from non-living to living matter was gradual and complex, involving countless chemical innovations over millions of years. Our atom might have participated in many of these innovations, being incorporated into different molecules, playing various roles in primitive metabolism, and contributing to the chemical complexity that made life possible. Early life was simple compared to modern organisms, consisting of single cells without nuclei or other complex internal structures. But even these simple cells represented a revolutionary new way of organizing matter, creating structures that could maintain themselves, reproduce, and evolve over time. Our atom experienced this new form of existence as part of living matter, participating in the chemical reactions that powered early life. Metabolism, the set of chemical reactions that allow living things to extract energy from their environment and use it to build and maintain cellular structures, was a fundamentally new phenomenon in the universe. The first living things were probably chemotrophic, deriving energy from chemical reactions rather than sunlight. They lived in environments rich in chemical energy, such as deep-sea vents or hot springs, where they could harvest energy from reactions between different chemical compounds. Our atom might have been part of these energy harvesting processes, helping to power the first spark of life on Earth. Over hundreds of millions of years, life evolved and diversified, developing new ways to capture and use energy. One of the most important innovations was photosynthesis, the ability to use sunlight to power cellular chemistry. This development had profound consequences for Earth's chemistry and atmosphere. Our atom might have become part of the first photosynthetic organisms, perhaps embedded in a chlorophyll molecule or another light-harvesting structure. Photosynthesis allowed life to tap into the vast energy resources of the sun, supporting much larger and more complex ecosystems than had been possible with chemical energy alone. The evolution of photosynthesis also began to change Earth's atmosphere by producing oxygen as a waste product. Initially, this oxygen was absorbed by iron and other reduced materials in the oceans and atmosphere. But eventually, free oxygen began to accumulate in the atmosphere, creating the oxidizing environment that characterizes modern Earth. Our atom witnessed this great oxygenation event, one of the most significant changes in Earth's history. If it was part of a living organism, it had to adapt to the presence of this highly reactive gas. Many early life forms found oxygen toxic and went extinct, but others evolved mechanisms to tolerate or even use oxygen for cellular metabolism. The presence of oxygen in the atmosphere opened up new possibilities for life, allowing the evolution of aerobic respiration, a much more efficient way of extracting energy from organic molecules than had been possible in the oxygen-free world. Our atom might have participated in these new metabolic pathways, helping to power more complex and energetic forms of life. Over geological time, our atom cycled through different reservoirs on Earth, from rock to ocean to atmosphere to living organisms and back again. This cycling was driven by geological processes like weathering, volcanism, and plate tectonics, as well as biological processes like photosynthesis, respiration, and decomposition. The atom experienced Earth's dynamic history, from the formation of the first continents to the great mass extinctions that periodically reset the course of evolution. It might have been buried in sediment and compressed into rock, only to be uplifted and weathered millions of years later. It might have been part of a forest that was buried and turned into coal, or part of a sea creature whose shell became limestone. Each cycle brought new experiences and new chemical environments. Our atom might have spent millions of years locked in a crystal lattice deep in Earth's crust, experiencing pressures and temperatures that transformed the rock around it. Then geological forces might have brought it to the surface, where weathering released it into soil or groundwater. As life became more complex, our atom found new roles to play in biological systems. It might have become part of the calcium carbonate shell of a marine animal, helping to protect soft tissues from the environment. It might have been incorporated into the wood of an ancient tree, providing structural support as the tree grew toward the light. The evolution of complex multicellular life opened up entirely new ecological roles for our atom. It might have cycled through food webs, passing from plants to herbivores to carnivores, and back to the soil through decomposition. Each transfer represented a new chapter in its biological journey, a new way of participating in the chemical dance of life. Our atom might have been present for some of the great transitions in Earth's history: the colonization of land by plants and animals, the evolution of forests that transformed landscapes, the rise and fall of the dinosaurs, the emergence of mammals, and eventually humans. Through all these changes, it continued its eternal circulation between the biological and geological spheres. When humans finally appeared on Earth, our atom gained yet another possible destination. It might have become part of the calcium in human bones, helping to provide the structural framework that allows us to stand upright. It might have been incorporated into hemoglobin molecules, carrying oxygen through human bloodstreams. It might have become part of the DNA that stores the genetic information passed from generation to generation. If our atom is now part of a human body, it represents the culmination of an incredible cosmic journey. From its birth in the nuclear furnace of an ancient star through its violent dispersal in a supernova explosion to its incorporation into planets and living beings. It has participated in the universe's transformation from simplicity to complexity. The calcium in our teeth, the iron in our blood, the carbon in our DNA all bear witness to this cosmic heritage. We are walking monuments to stellar nucleosynthesis, living proof that the universe has evolved from a simple mixture of hydrogen and helium into something capable of understanding itself. Every atom in our bodies has a story to tell, a narrative of cosmic evolution that spans the entire history of the universe. Our atom continues its journey even now, cycling through human metabolism, perhaps being incorporated into new tissues or being exhaled as carbon dioxide. It might leave the human body and enter the ecosystem, becoming part of a plant or another animal. The journey that began billions of years ago in the heart of a star continues, with no end in sight. The emergence of human consciousness represents a unique moment in cosmic history when the universe became capable of contemplating its own evolution. Through science, humans have traced the paths that atoms follow from stars to planets to life, understanding for the first time the cosmic connections that link us to the rest of the universe. Our atom, whether it resides in a human brain or elsewhere in the Earth system, is now part of a world where matter has organized itself into forms capable of understanding the very processes that created it. This represents perhaps the most remarkable transformation in cosmic history, the evolution of matter into mind, the development of structures capable of consciousness and scientific understanding. The journey from stellar core to human consciousness illustrates the remarkable creativity of the universe, its ability to generate complexity and organization from simple beginnings. Our atom has been a participant in this great cosmic adventure, carrying within its nuclear structure the memory of its stellar origins and the potential for future transformations we can only imagine. The story of our atom is far from over. Human civilization is beginning to manipulate matter in new ways, creating artificial materials and potentially spreading life beyond Earth. Our atom might someday find itself part of a spacecraft traveling to other worlds, or incorporated into artificial life forms created by human technology. Whatever the future holds, our atom will continue its cosmic journey, a permanent wanderer in the universe's endless cycles of transformation. It has already seen the birth of stars and planets, the emergence of life and consciousness. What wonders await it in the eons to come as the universe continues its evolution toward ever greater complexity and understanding. Inside the warm, dark interior of a living cell, our atom has found perhaps the most extraordinary phase of its cosmic journey. No longer simply drifting through space or locked in crystalline structures, it has become part of something unprecedented in the universe, a self-organizing, self-replicating system that can grow, respond to its environment, and even make copies of itself. If our atom has become part of a human body, it might now reside within one of the roughly 37 trillion cells that make up a single person. Each of these cells is like a microscopic city, bustling with activity as thousands of different types of molecules work together in an intricate dance of life. Our atom has joined this molecular choreography, playing its part in the complex chemistry that sustains living things. Consider the possibility that our atom has become part of a protein molecule, one of the workhorses of cellular chemistry. Proteins are long chains of smaller molecules called amino acids, folded into precise three-dimensional shapes that allow them to perform specific functions. If our atom is carbon, it might form part of the backbone that holds these amino acids together. If it is nitrogen, it might be part of an amino group that helps determine the protein's properties. The protein containing our atom could be an enzyme, a molecular machine that catalyzes chemical reactions in the cell. Enzymes are remarkable for their specificity and efficiency, able to speed up reactions by factors of millions while working at body temperature. Our atom might be positioned at the active site of the enzyme, the precise location where chemical reactions take place, helping to bind substrates and facilitate their transformation into products. Imagine our atom as part of the enzyme that breaks down glucose, the sugar that provides energy for cellular activities. Each time the cell needs energy, this enzyme springs into action, helping to dismantle glucose molecules and capture their chemical energy. Our atom participates in this process billions of times per second, facilitating the chemical reactions that keep the cell alive. But our atom's role in living systems extends far beyond just one protein or one reaction. The remarkable thing about biological chemistry is that nothing remains static for long. Molecules are constantly being broken down and rebuilt, worn-out components are replaced with new ones, and atoms flow continuously through different molecular structures. This constant turnover means that our atom leads a remarkably dynamic existence within living things. It might spend some time as part of a structural protein, providing strength to cellular components, then be recycled into an enzyme that breaks down nutrients, then incorporated into a signaling molecule that communicates between cells. The molecular identity is temporary, but the atomic identity persists. The concept of residence time in biological systems is fascinating to contemplate. A carbon atom in the human body has an average residence time of about 12 years, though this varies enormously depending on which tissues it inhabits. Carbon in muscle proteins might be replaced within a few months, while carbon in bone might remain for decades. Our atom experiences this constant molecular renewal, being continuously recycled through the body's chemistry. If our atom has become part of the calcium in human bones, it participates in one of the body's most important structural systems. Bone is not the static, unchanging material it might appear to be. Instead, it is constantly being remodeled as old bone tissue is broken down and new tissue is formed. Our calcium atom might be incorporated into a crystal of hydroxyapatite, the mineral that gives bones their strength and hardness. Even within bone, our atom is not motionless. Bone tissue is riddled with tiny channels through which blood flows, bringing nutrients and carrying away waste products. Our calcium atom can be dissolved from bone and transported through the bloodstream to other parts of the body where calcium is needed. It might help muscles contract, assist in blood clotting, or participate in nerve signal transmission. The circulatory system provides highways for atomic transport throughout the body. If our atom enters the bloodstream, it could travel from the heart to the brain in just a few seconds, or circulate to the extremities and back again in about a minute. This rapid circulation ensures that all parts of the body have access to the atoms and molecules they need for their specialized functions. Our atom might find itself part of a red blood cell, specifically incorporated into a hemoglobin molecule, responsible for carrying oxygen throughout the body. If it is an iron atom, it sits at the center of a heme group, the precise location where oxygen molecules bind. Each time the person breathes, our iron atom helps capture oxygen in the lungs and release it in tissues that need it most. The journey of our atom through the lungs illustrates the intimate connection between our bodies and the external environment. With each breath, we exchange atoms with the atmosphere around us. Our atom might have been part of atmospheric carbon dioxide, just moments before being incorporated into a biological molecule. This constant exchange means that the boundary between self and environment is much more fluid than we typically imagine. If our atom is now part of a molecule of DNA, it has become central to one of life's most fundamental processes, the storage and transmission of genetic information. DNA molecules are extraordinarily long structures, containing billions of atoms arranged in precise sequences that encode the instructions for building and maintaining a living organism. Our atom might be part of one of the 4 bases that form the letters of the genetic code: adenine, guanine, cytosine, or thymine. These bases pair up in specific combinations to form the double helix structure of DNA. The sequence of these bases determines what proteins the cell can make, which in turn determines the cell's behavior and the organism's characteristics. The stability of DNA is remarkable when you consider the atomic perspective. The same atoms that once raced through stellar cores at millions of degrees and were blasted through space by supernova explosions now sit quietly in cell nuclei, arranged in patterns that can be faithfully copied and passed on to future generations. Our atom might be part of genetic information that has been transmitted through thousands of generations of ancestors. Yet even DNA is not permanent. The cells in our bodies are constantly repairing and replacing damaged DNA, and our atom might find itself moved from an old DNA molecule to a new one during this process. The genetic information remains the same, but the physical atoms that carry it are regularly refreshed. If our atom has become part of the brain, it participates in perhaps the most mysterious aspect of biological existence: consciousness and thought. The human brain contains roughly 86 billion neurons, each connected to thousands of others through synapses. Our atom might be part of the cellular machinery that generates the electrical signals that neurons use to communicate. The chemistry of thought involves rapid movements of atoms and molecules across cell membranes. Sodium and potassium atoms flow in and out of neurons, creating electrical potentials that propagate along nerve fibers. Neurotransmitter molecules carry signals across synapses, allowing neurons to influence each other's activity. Our atom might participate in these processes, helping to generate the patterns of neural activity that somehow give rise to consciousness. It is remarkable to consider that the same atom that was forged in the core of an ancient star might now be part of the substrate of human thought. When we contemplate the cosmos and our place in it, we are using atoms from the cosmos to think about themselves. The universe has evolved to the point where it can contemplate its own evolution, using the very matter that underwent that evolution. The immune system provides another fascinating environment where our atom might find itself. This complex network of cells and molecules protects the body from invasion by harmful microorganisms. Our atom might be part of an antibody molecule, specifically designed to recognize and bind to foreign substances. The precision with which antibodies recognize their targets is extraordinary, distinguishing between molecules that differ by only a few atoms. If our atom becomes part of an immune cell, it might travel throughout the body's lymphatic system, patrolling for signs of infection or damage. The immune system maintains a kind of molecular memory, remembering previous encounters with pathogens and mounting faster responses upon re-exposure. Our atom could be part of this immunological memory, helping to protect the body from future threats. The digestive system offers yet another perspective on atomic existence within living things. Here, our atom might participate in the breakdown of food molecules, helping to extract nutrients that can be used elsewhere in the body. Digestive enzymes catalyze reactions that break chemical bonds, releasing atoms from the food we eat, so they can be incorporated into our own biological structures. This is where the cosmic recycling becomes most apparent. The atoms in our food were once part of other living things, plants that captured carbon from the atmosphere, or animals that consumed those plants. Our atom might have been part of a grain of wheat that grew in a field, incorporating carbon dioxide from the air through photosynthesis, before being harvested, processed into bread, and consumed by a human. The liver serves as a central processing plant for atomic recycling within the body. This remarkable organ can transform one type of molecule into another, breaking down toxic substances, synthesizing important compounds, and regulating the levels of various atoms and molecules in the blood. Our atom might pass through the liver multiple times during its stay in the human body, each time potentially being incorporated into different molecular structures. Fat cells provide long-term storage for certain types of atoms. If our atom becomes part of a lipid molecule stored in fat tissue, it might remain relatively undisturbed for months or years. These stored molecules can be mobilized when the body needs energy, releasing our atom back into circulation to participate in more active metabolic processes. The process of cellular division means that our atom might become part of a new cell when an existing cell reproduces. During cell division, all the cell's components must be duplicated so that each daughter cell receives a complete set. Our atom might be copied along with the DNA, or it might be randomly distributed to one of the two new cells. Different organs and tissues have different rates of cellular turnover. The lining of the intestine replaces itself every few days, while neurons in the brain may last for the entire human lifetime. Our atom's experience within the body depends greatly on which tissues it becomes part of. In rapidly dividing tissues, it experiences constant molecular upheaval. In slowly changing tissues like bone or brain, it might remain in the same molecular context for months or years. The endocrine system uses chemical messengers, called hormones, to coordinate activities throughout the body. Our atom might become part of a hormone molecule, carrying information from one organ to another. Hormones typically work in tiny concentrations, so even a few atoms can have significant effects on cellular behavior and physiological processes. During sleep, the body enters a different metabolic state, with reduced activity in many systems, but increased activity in others. Our atom might participate in the repair and maintenance processes that occur primarily during sleep. Growth hormone released during sleep might incorporate our atom into proteins involved in cellular repair and regeneration. Physical activity dramatically changes the body's atomic requirements. During exercise, the demand for energy increases, requiring rapid mobilization of stored molecules. Our atom might be part of glucose molecules broken down to provide quick energy, or it might be incorporated into new proteins that strengthen muscles in response to exercise. The aging process affects how atoms cycle through the body. As we age, some cellular repair processes become less efficient, and the turnover of certain molecules slows down. Our atom might find itself remaining in the same molecular context for longer periods in an older body compared to a younger one. Some molecules in the human eye lens, for example, are never replaced and contain atoms that have been in the same position since birth. The remarkable thing about biological systems is their ability to maintain organization and function while constantly exchanging matter with their environment. Our atom might enter the body in food or drink, participate in countless biological processes, and then leave through breath, urine, or other waste products. Yet the living organism maintains its identity and function throughout this constant atomic flux. This principle of dynamic equilibrium means that we are more like waterfalls than rocks, maintaining our form and function through the continuous flow of matter and energy rather than through static arrangements of atoms. Our atom experiences this flow firsthand, being incorporated into the temporary structures that make up living things. The foods we eat connect us to the broader ecosystems of Earth. Our atom might have been part of a photosynthetic plant that captured carbon dioxide from the atmosphere, or a marine organism that incorporated dissolved minerals from seawater. Through the food web, our atom carries with it a history of its journey through Earth's biosphere. When our atom eventually leaves the human body, it does not cease to be part of biological systems. It might be exhaled as carbon dioxide and incorporated into a plant through photosynthesis. It might be excreted and become part of soil, where it feeds microorganisms and plants. In this way, our atom continues its circulation through the biosphere, moving from one living system to another. The development of agricultural systems has modified how atoms cycle through human populations. A carbon atom that might once have cycled through wild ecosystems might now be part of a crop plant, harvested and transported to cities where it enters human food systems. This human management of atomic flows represents a new chapter in the atom's biography. Modern medical interventions can also affect our atom's journey through living systems. It might be part of a medication that alters cellular chemistry, or it might be temporarily replaced by artificial materials during medical procedures. These interventions represent humanity's growing ability to manipulate the atomic processes that sustain life. The study of metabolism has revealed the incredible complexity of atomic transformations within living things. Metabolic pathways map out the routes that atoms take as they move through different molecular forms within cells. Our atom might follow well-established pathways, moving through a series of chemical transformations that have been conserved across billions of years of evolution. Each enzyme in these pathways is precisely crafted to facilitate specific chemical transformations. Our atom encounters these molecular machines that can selectively break certain bonds while forming others, guiding it through the complex chemistry of life. The precision and efficiency of these biological catalysts far exceed anything that human chemistry has been able to achieve. The temperature and pH conditions within living systems are carefully controlled to optimize these chemical reactions. Our atom experiences an environment that is neither too hot nor too cold, neither too acidic nor too basic, but maintained within narrow ranges that allow biological chemistry to proceed efficiently. Water plays a crucial role in all these biological processes, serving as both a reactant and a medium for chemical reactions. Our atom likely spends much of its time in aqueous solution, dissolved in the water that makes up the majority of living tissue. Water's unique properties, from its ability to form hydrogen bonds to its capacity as a solvent, create the environment in which biological chemistry can flourish. The complexity of living systems means that our atom might simultaneously be part of multiple overlapping processes. It might be structurally important as part of a cellular component, while also serving a functional role in metabolism. This multifunctionality is characteristic of biological systems, where every atom must often serve multiple purposes. The social nature of human existence means that our atom's biological journey is intertwined with the journeys of atoms in other humans. Through close contact, shared meals, and even simple proximity, atoms move between individuals. Our atom might have been part of countless other humans throughout history before entering its current biological context. The global nature of modern food systems means that our atom might have originated in a faraway ecosystem before traveling thousands of miles to become part of a human body. This global circulation of atoms through human food systems represents an unprecedented mixing of matter from different parts of Earth's biosphere. Climate change and environmental degradation affect the paths that atoms take through living systems. Changes in atmospheric composition, ocean chemistry, and ecosystem health all influence how atoms cycle between organisms and their environment. Our atom's future journeys will be shaped by how humanity manages its impact on Earth's systems. The emerging field of synthetic biology seeks to design new biological systems that can perform novel functions. Our atom might someday be part of an engineered organism designed to produce useful chemicals, clean up pollution, or perform other beneficial tasks. This represents the next phase in the co-evolution of humans and the atoms that cycle through our biological systems. Medical research continues to reveal new details about how atoms behave within living systems. Advanced imaging techniques can track individual atoms as they move through biological processes, while computational modeling helps predict how atomic-level changes might affect larger biological functions. Our atom is part of this ongoing scientific exploration of life's atomic foundations. The recognition that we are made of star stuff carries profound implications for how we understand our place in the universe. Our atom's journey from stellar core to biological function illustrates the deep connections between cosmology and biology, between the largest and smallest scales of existence. We are quite literally animated stardust, temporary arrangements of cosmic matter that have gained the ability to understand their own origins. This perspective can foster a sense of connection to the natural world and the cosmos beyond. The atoms in our bodies have been part of countless other organisms throughout Earth's history and will continue their journeys long after our individual lives end. We are participants in a cosmic circulation of matter that began with the formation of the first stars and will continue until the last star burns out. Understanding life from an atomic perspective also highlights the remarkable achievement that biological organization represents. The same atoms that exist randomly distributed in non-living matter have been organized into the incredibly complex and precisely functioning systems we call living organisms. Life represents a triumph of organization over chaos, of information over randomness. Our atom's sojourn within living things is temporary, but it participates in processes that have been refined over billions of years of evolution. It benefits from the accumulated wisdom of life, encoded in the genetic instructions that guide cellular chemistry and the evolved structures that make biological function possible. When we consider the probability that any particular atom from a supernova explosion would eventually become part of a living thing, let alone a conscious being capable of contemplating its own cosmic origins, we begin to appreciate the remarkable nature of our existence. Our atom has won a cosmic lottery, finding itself part of the universe's attempt to understand itself. The experience of our atom within living systems illustrates the creative power of evolution to generate complexity from simple beginnings. Through the processes of natural selection, random mutations, and genetic recombination, life has discovered countless ways to arrange atoms into functional systems. Our atom is a beneficiary of this biological creativity. As we continue to learn more about biological systems, we discover new roles that atoms can play in living things. From the quantum effects that may be important in consciousness to the role of trace elements in cellular function, the atomic perspective on life continues to yield new insights. Our atom's biological phase represents perhaps the most complex and organized state it has experienced in its cosmic journey. From the simple hydrogen of the early universe through stellar nucleosynthesis and planetary formation, its cosmic evolution has culminated in participation in the most sophisticated chemical systems known to exist anywhere in the universe. The journey is far from over. Our atom will continue to cycle through living systems, perhaps for millions or billions of years, participating in the ongoing evolution of life on Earth and possibly beyond. Each biological system it enters adds new chapters to its cosmic biography, new experiences to its atomic memory. Through our atom's eyes, we see that life is not separate from the cosmos but intimately connected to it. We are expressions of cosmic evolution, demonstrations of the universe's capacity for self-organization and self-understanding. Our atoms carry within them the memory of stars and the potential for future wonders we can scarcely imagine. The universe operates on the principle of eternal recycling, a cosmic circulation system where nothing is ever truly lost, only transformed and redistributed. Our atom has experienced this firsthand throughout its billion-year journey, moving from stellar cores to planetary surfaces, from rocks to life and back again. This recycling is not just a feature of the universe, it is the universe's most fundamental characteristic, the process that allows matter to explore every possible state and combination. Consider the grand scale of this cosmic recycling program. Galaxies themselves participate, exchanging matter through gravitational interactions that can scatter stars and gas clouds across millions of light years. When galaxies collide, as our Milky Way will, with Andromeda in about 4 billion years, their stellar populations and gas clouds mix, creating new opportunities for stellar formation and planetary development. Our atom might someday witness such a galactic merger, finding itself in a completely different region of space as gravitational forces rearrange the cosmic landscape. The galaxy it had called home for billions of years would be transformed into something new, a larger elliptical galaxy where stellar formation proceeds differently and where the opportunities for planetary systems and life might be quite different. The collision between the Milky Way and Andromeda will unfold over hundreds of millions of years, giving our atom time to experience every phase of this galactic transformation. As the two galaxies approach each other, their gravitational fields will begin to distort the spiral arms and stellar orbits. Stars will be flung into new trajectories, some escaping the merged system entirely, while others fall toward the new galactic center. During the initial approach, our atom might find itself in a region where star formation accelerates dramatically. The gravitational perturbations from the approaching galaxy could trigger the collapse of molecular clouds that had remained stable for millions of years. New stars would form at a rapid pace, processing interstellar material through nuclear burning and returning it to space enriched with heavy elements. As the galaxies penetrate each other's outer regions, our atom could experience tidal forces that stretch and compress the interstellar medium. These forces might disrupt planetary systems, sending comets and asteroids on new trajectories that could deliver our atom to previously unreachable parts of the galaxy. Some planetary systems might be completely ejected, becoming rogue worlds wandering through intergalactic space. The final merger phase would create a period of intense activity as the two galactic centers approach and eventually combine. The supermassive black holes at the centers of both galaxies would spiral toward each other, generating gravitational waves and ejecting matter at tremendous speeds. Our atom might be part of material, launched into the intergalactic medium during this phase, beginning a new chapter of existence outside any galaxy. But even without such dramatic events, the galaxy acts as a cosmic mixing bowl on more gentle timescales. Stellar winds carry matter from evolved stars into the interstellar medium at velocities of hundreds of kilometers per second. These winds can travel for thousands of years, carrying our atom across vast distances within the galaxy and mixing material between different regions. The galactic disk rotates with a period of about 200 million years, carrying stars and gas clouds in great orbital cycles around the galactic center. Our atom has likely completed several such galactic years during its cosmic journey, experiencing different regions of the galaxy as it participates in this grand rotation. Each region offers different conditions for stellar formation, different abundances of heavy elements, and different histories of cosmic evolution. Spiral density waves propagate through the galactic disk, compressing gas clouds and triggering star formation as they pass. Our atom might have been swept up in such waves multiple times, finding itself in regions of enhanced stellar activity where new generations of stars form and die at accelerated rates. These waves help maintain the galaxy's spiral structure while constantly redistributing matter throughout the disk. The galactic halo contains streams of stars and gas that were torn from smaller galaxies captured by the Milky Way's gravity over billions of years. Our atom might have originated in one of these smaller galaxies, experiencing a very different early cosmic environment before being incorporated into our larger galactic system. Star formation continues to recycle matter on galactic scales, but the process has evolved significantly over cosmic time. Massive molecular clouds collapse under their own gravity, forming new generations of stars from material that has already been processed through previous stellar generations. Our atom may have been part of many different stars throughout cosmic history, each time being subjected to different conditions in stellar cores. The first-generation stars were massive giants that burned through their fuel quickly and died young in spectacular supernova explosions. These population 3 stars, as astronomers call them, contained only primordial hydrogen and helium when they formed. Our atom might have been part of one of these primordial giants, experiencing nuclear fusion for the first time and being enriched with heavy elements created in stellar cores. Second-generation stars, formed from supernova-enriched material, were smaller and longer-lived, burning for billions rather than millions of years. Our atom witnessed this transition, participating in the universe's shift from violent, short-lived stellar evolution to the more sedate nuclear burning that characterizes modern stars. These population 2 stars could form planetary systems with rocky worlds, though they contained fewer heavy elements than stars forming today. Third-generation stars like our Sun, formed from even more heavily processed material, can be smaller still and may burn for trillions of years. Our atom might someday be incorporated into one of these ultra-long-lived red dwarf stars, experiencing nuclear fusion at the gentlest possible pace and remaining bound within stellar material for a significant fraction of the universe's total age. The stellar life cycle itself represents a perfect example of cosmic recycling operating on intermediate timescales. Main sequence stars convert hydrogen to helium for billions of years, creating the heavy elements essential for rocky planets and life through nuclear fusion in their cores. Then they evolve through red giant phases, where they shed their outer layers back into space through stellar winds. These planetary nebulae, glowing shells of gas surrounding white dwarf cores, return most of a star's mass to the interstellar medium, enriched with helium and heavier elements produced during the star's lifetime. Our atom might be part of such a gentle dispersal, riding stellar winds at speeds of hundreds of kilometers per second into the vast spaces between stars. Unlike the violent ejection from a supernova, this process allows matter to escape gradually, mixing with the interstellar medium over thousands of years and creating beautiful, glowing structures visible to telescopes across the galaxy. The Ring Nebula, the Helix Nebula, and thousands of other planetary nebulae represent this gentle form of cosmic recycling in action. White dwarf stars, the dense cores left behind after planetary nebula ejection, continue to participate in cosmic recycling over much longer timescales. These stellar remnants contain roughly the mass of our Sun compressed into a volume the size of Earth. They slowly cool over billions of years, eventually becoming invisible black dwarfs that may persist for trillions of years. Our atom might someday be part of such a stellar corpse, locked in an ultra-dense crystalline lattice, where electrons are squeezed into degenerate quantum states. The matter in a white dwarf exists in conditions impossible to recreate on Earth, with densities reaching millions of times that of water. Even in this exotic state, our atom would retain its nuclear identity, waiting patiently for cosmic processes to liberate it once again. Some white dwarfs participate in more dramatic recycling events when they have close binary companions. If a white dwarf accretes matter from a nearby star, it can trigger a nova explosion that blows some of its accumulated material back into space. Our atom might experience such an explosion, being launched at thousands of kilometers per second in a bright flash visible across the galaxy. In extreme cases, a white dwarf can accumulate enough matter to approach the Chandrasekhar limit, the maximum mass that electron degeneracy pressure can support. When this limit is exceeded, the white dwarf explodes as a Type Ia supernova, completely destroying the star and returning all its matter to space in a thermonuclear detonation. Even the most extreme stellar remnants participate in cosmic recycling, though on much longer timescales that dwarf the current age of the universe. Neutron stars, the crushed cores of massive stars, contain matter so dense that protons and electrons are forced together to form neutrons. Our atom, if it ever becomes part of a neutron star, would experience the most extreme conditions possible in normal matter. The surface of a neutron star has a gravitational field so strong that time runs noticeably slower than in normal space. Matter on the surface exists in a crystalline lattice of atomic nuclei surrounded by a sea of free neutrons and electrons. Deeper in the neutron star, Matter exists in exotic forms that we can barely understand, possibly including quark matter or other states that exist nowhere else in the universe. Black holes, which seem to trap matter forever behind their event horizons, may actually return all their captured material to the universe through Hawking radiation over periods so long that they dwarf the current age of the universe by factors that have no name. If our atom ever falls into a black hole, it would be condemned to an unimaginably long wait before being released as thermal radiation. The process would be so slow that a black hole with the mass of our Sun would take longer than 10 to the 67th power years to evaporate completely. During this time, the universe would undergo transformations we can barely imagine. Galaxies would drift apart due to cosmic expansion, stars would burn out, protons might decay, and the cosmos would enter phases of evolution for which we have no names. Yet even this represents recycling on the grandest possible scale. The Hawking radiation that eventually emerges from evaporating black holes is believed to carry the quantum information that fell in, ensuring that our atom's identity persists in some form even through the most extreme gravitational processing. The conservation of information, a fundamental principle that emerges from quantum mechanics and general relativity, guarantees that our atom's cosmic biography continues even in circumstances that seem to erase all traces of its past. The information paradox surrounding black holes remains one of the most challenging problems in theoretical physics. How can information be preserved when matter falls into a black hole? Recent theoretical work suggests that the information is gradually released through subtle correlations in the Hawking radiation, ensuring that our atom's quantum identity survives even the most extreme cosmic recycling. Planetary systems provide another crucial arena for cosmic recycling, operating on timescales intermediate between stellar and galactic processes. These systems exchange material internally through various mechanisms, from asteroid and comet impacts to atmospheric loss and capture. Our atom might have cycled through several different worlds within a single planetary system over billions of years. Planets lose their atmospheres through various processes that return planetary material directly to space, without the need for stellar death or collision. Solar wind, the stream of charged particles flowing from a star, can gradually strip away planetary atmospheres over billions of years. This process is particularly effective for planets that lack strong magnetic fields to deflect the stellar wind. Mars provides a nearby example of atmospheric loss in action. This planet once had a thicker atmosphere and liquid water on its surface, but solar wind stripping and other loss mechanisms have reduced its atmosphere to a thin whisper of its former self. Our atom might have been part of the ancient Martian atmosphere, riding in water vapor clouds that gradually escaped to space. Venus demonstrates another pathway for atmospheric evolution. Despite retaining most of its atmosphere, Venus lost virtually all its water through a runaway greenhouse effect that allowed water vapor to reach the upper atmosphere where solar radiation could break it apart. The hydrogen escaped to space while the oxygen was incorporated into surface rocks, permanently altering the planet's composition. Our atom might experience such atmospheric loss if it becomes part of a planetary atmosphere around any star. The process operates continuously but slowly, taking millions or billions of years to significantly alter a planet's composition. During this time, our atom could witness the transformation of a world from habitable to barren, or potentially the reverse if atmospheric loss is countered by volcanic outgassing or comet impacts. Comets and asteroids serve as cosmic delivery services, carrying material between different parts of planetary systems and even between different stellar systems. These small bodies preserve material from the early solar system in their icy or rocky matrices, providing time capsules that reveal conditions during planetary formation 4.5 billion years ago. Our atom might become part of a comet, spending thousands of years in the cold outer reaches of a solar system before making a spectacular journey toward the inner planets. As the comet approaches its star, solar heating vaporizes ices and creates the glowing coma and tail that make comets visible from great distances. Our atom could be part of this sublimating material, escaping the comet and joining the thin gas that fills interplanetary space. Some comets are ejected from their parent systems entirely when gravitational perturbations from planets or passing stars alter their orbits. These interstellar comets become wanderers that may travel for millions or billions of years before being captured by other stars. Our atom could thus travel between stellar systems aboard these icy spacecraft, experiencing a form of interstellar migration that takes millions of times longer than any human journey. The recently discovered interstellar objects like Oumuamua and Borisov provide concrete evidence that such exchanges between stellar systems actually occur. These visitors from other star systems demonstrate that material routinely travels between different planetary systems, carrying with it samples of alien worlds and potentially alien chemistry. Our atom might someday be part of such an interstellar asteroid or comet, escaping our solar system and journeying to another star. The trip would take millions of years, during which our atom would experience the cold vacuum of interstellar space, bombarded by cosmic rays and influenced by the galactic magnetic field. When such an object finally enters another stellar system, it brings exotic material that formed under different conditions around a different star. Our atom might thus seed new worlds with elements that originated in our solar system, participating in a slow but steady exchange of material between stellar systems throughout the galaxy. Meteorite impacts provide another mechanism for recycling material between worlds within a single stellar system. Every day, tons of meteoritic material falls on Earth, delivering atoms that originated in asteroids, comets, and occasionally other planets. This cosmic bombardment has been ongoing since planetary formation and represents a continuous source of new material for planetary surfaces. Mars rocks have been found on Earth, blasted off the red planet by large asteroid impacts and traveling through space for millions of years before landing on our world. These Martian meteorites provide direct samples of another planet's geology and potentially its past biosphere. Our atom might make such a journey, experiencing life on one planet before being delivered to another through cosmic bombardment. The Late Heavy Bombardment, which occurred about 4 billion years ago, represents an extreme example of interplanetary material exchange. During this period, large numbers of asteroids and comets impacted the inner planets, delivering vast quantities of water and organic compounds that may have been essential for the origin of life on Earth. Our atom might have arrived on Earth during this bombardment, traveling from the outer solar system where water and organic molecules could form easily to the inner solar system where conditions were suitable for liquid water and life. This cosmic delivery system may have made Earth habitable by providing the volatile compounds that were lost during the planet's violent formation. The exchange of material between worlds raises fascinating questions about the spread of life throughout the universe. If our atom was once part of a living organism on one world, could it carry chemical signatures or even microscopic life forms to another world? The theory of panspermia suggests that life might spread between planets or even between stellar systems through such material exchange. Microorganisms have been found that can survive the extreme conditions of space, including intense radiation, hard vacuum, and extreme temperature variations. If our atom was part of such a hardy microbe, it might have survived the journey between worlds and potentially seeded life on previously barren planets. Recent discoveries of possible biosignatures in meteorites from Mars have reignited interest in this possibility. While the evidence remains controversial, it raises the intriguing prospect that life on Earth and Mars might share a common origin, with organisms spreading between the two worlds through meteorite exchange. Ocean worlds in the outer solar system, such as Europa, Enceladus, and Titan, demonstrate that liquid water and potentially habitable environments exist in places previously thought too cold for life. These moons maintain subsurface oceans through tidal heating from their giant planet hosts, creating environments that could remain stable for billions of years. Our atom might someday be part of life in these exotic environments, experiencing biology in conditions radically different from Earth. The oceans of Europa and Enceladus are in direct contact with rocky cores, potentially creating chemical conditions suitable for the kind of chemosynthetic life found around Earth's deep-sea vents. Titan's hydrocarbon lakes and thick organic atmosphere represent another type of potentially habitable environment, where our atom might participate in exotic chemistry based on liquid methane rather than water. Life in such an environment would be utterly alien to terrestrial biology, using different solvents and different chemical pathways to maintain organization and reproduction. The search for life beyond our solar system focuses increasingly on exoplanets in habitable zones around other stars. Thousands of such worlds have been discovered, some of which might have conditions suitable for liquid water and life as we know it. Our atom might someday be incorporated into the atmosphere, oceans, or even biosphere of such a world, participating in alien chemistry and perhaps alien biology that we can barely imagine. Atmospheric characterization of exoplanets is revealing an incredible diversity of conditions on worlds around other stars. Some have atmospheres dominated by hydrogen and helium, others by carbon dioxide or water vapor. Some experience extreme temperature variations due to tidal locking, while others orbit multiple stars and experience complex seasonal cycles. Our atom might find itself in any of these environments, adapting to chemical conditions very different from those it has experienced in our solar system. The diversity of possible planetary environments suggests that cosmic recycling can produce an almost infinite variety of chemical and physical conditions for our atom to explore. Cosmic recycling operates not just on large scales, but on quantum scales as well, connecting our atom to fundamental processes that operate at the smallest possible distances and shortest possible times. Virtual particles constantly appear and disappear in the vacuum of space, borrowing energy from the quantum field and paying it back so quickly that these transactions are undetectable by normal means. Our atom participates in this quantum foam through its electromagnetic and gravitational fields, which interact with virtual particles in ways that may influence the atom's properties and behavior. These quantum fluctuations contribute to effects like the Casimir force and the Lamb shift, demonstrating that even apparently empty space is alive with activity. The uncertainty principle of quantum mechanics ensures that our atom's position and momentum cannot be simultaneously determined with perfect precision. This fundamental uncertainty means that our atom exists in a constant state of quantum flux, with its properties fluctuating within limits set by Planck's constant. Quantum field theory describes our atom not as a solid particle, but as an excitation in underlying quantum fields that permeate all of space. From this perspective, our atom is a temporary pattern in the quantum vacuum, a localized disturbance in fields that existed long before the atom formed and will persist long after it is transformed. The expansion of the universe itself affects cosmic recycling by gradually increasing the distances between galaxies and reducing the density of matter in space. As the universe expands and cools, opportunities for matter to interact and recombine become fewer and farther between. Our atom's future recycling events will become increasingly rare as cosmic expansion separates the fuel for new stellar formation. Dark energy, the mysterious force driving the acceleration of cosmic expansion, may ultimately lead to a Big Rip scenario, where the expansion rate increases exponentially. In such a future, our atom would experience the gradual dissolution of all bound structures, from galaxies to stars to planets to atoms themselves, as space expands faster than any force can hold matter together. Yet even in a universe grown old and cold, recycling continues through increasingly exotic processes that operate on timescales so long they defy human comprehension. Proton decay, if it occurs as some theories predict, would ultimately return all matter to energy, but only after periods measured in units of 10 to the 34th power years or longer. Our atom might persist in some form through the entire history of the cosmos, witnessing its transition from a hot, dense fireball through the current era of stars and galaxies to a cold, empty expansion dominated by dark energy. Even if protons decay, the energy released would create new particles that might eventually organize into new forms of matter. The anthropic principle suggests that the universe's physical constants are finely tuned for the existence of stars, planets, and life. This fine-tuning may be necessary for cosmic recycling to operate efficiently over the long timescales required for the emergence of complexity. If gravity was slightly stronger, all matter would collapse into black holes too quickly for complex structures to form. If it were weaker, matter would never condense into stars at all. Our atom exists in a universe where recycling is not just possible, but inevitable, a consequence of the fundamental laws of physics and the initial conditions set during cosmic inflation. The nuclear binding energies that hold atomic nuclei together, the electromagnetic forces that govern chemical reactions, and the gravitational forces that sculpt cosmic structure all conspire to create conditions where matter can explore countless different states and combinations over cosmic time. The conservation laws that govern physical processes ensure that cosmic recycling operates according to strict rules that can never be violated. Energy cannot be created or destroyed, only converted from one form to another. Electric charge is conserved in all reactions. Baryon number, which counts the total number of protons and neutrons, remains constant through all processes except those involving particle creation from pure energy. These conservation laws provide the framework within which cosmic recycling operates, ensuring that certain fundamental properties of our atom remain constant, even as it is transformed from one configuration to another. The proton that forms part of our atom's nucleus has remained unchanged since the Big Bang, carrying its positive charge and baryon number through every transformation. Human technology has begun to participate in cosmic recycling in new ways, allowing our species to manipulate matter on scales and with precision that was previously impossible. Nuclear reactors split heavy elements and fuse light ones, mimicking stellar nucleosynthesis but in controlled terrestrial environments. Our atom might someday be part of such artificial stellar processes, experiencing nuclear transformation guided by human engineering rather than stellar evolution. Particle accelerators can create conditions briefly similar to those that existed in the early universe, accelerating particles to tremendous energies and allowing them to collide with forces that recreate Big Bang nucleosynthesis on microscopic scales. Our atom might participate in such experiments, helping scientists understand the fundamental processes that govern matter and energy throughout the cosmos. Nuclear waste from human activities will participate in cosmic recycling over thousands or millions of years as radioactive isotopes decay back to stable forms. Our atom might become part of such waste, slowly transforming through a series of nuclear decays that reveal the instabilities introduced by human nuclear technology. Space exploration represents humanity's first attempts to participate directly in interplanetary material exchange on a conscious level. Every spacecraft we send to other worlds carries terrestrial atoms away from Earth, while sample return missions bring alien worlds to our laboratories. Our atom might be part of this deliberate cosmic recycling, traveling to other worlds aboard human-built vehicles. The Viking landers, Mars rovers, and other robotic explorers have delivered Earth materials to other planets, where they will remain for millions or billions of years unless retrieved by future missions. Our atom might be part of one of these technological ambassadors, representing Earth chemistry in alien environments. Sample return missions like the recent collection of material from asteroid Bennu bring extraterrestrial atoms to Earth for detailed analysis. These samples provide insights into conditions during the formation of the solar system and demonstrate that cosmic recycling has been operating since the earliest epochs of planetary formation. The International Space Station and other orbital facilities represent the beginning of permanent human presence beyond Earth's surface. Our atom might become part of these space habitats, cycling through air, water, and food systems in carefully controlled artificial ecosystems above our planet. The terraforming of other worlds, should it ever become feasible, would involve recycling matter on planetary scales to create habitable environments from hostile ones. Converting the atmosphere of Venus or Mars into something breathable would require moving enormous quantities of atoms from one chemical form to another. Our atom might participate in such grand engineering projects, being transformed from part of a toxic atmosphere into a component of a breathable one. Mars, with its thin carbon dioxide atmosphere and frozen water reserves, represents the most likely candidate for terraforming within our solar system. Proposals range from releasing greenhouse gases to thicken the atmosphere, to using mirrors or other technologies to increase solar heating. Our atom might be part of these atmospheric modifications, helping to create a second Earth in our cosmic neighborhood. Venus presents a more challenging terraforming target due to its dense, hot atmosphere and sulfuric acid clouds. However, some proposals suggest ways to cool the planet and convert its atmosphere to something more Earth-like. Our atom might experience such extreme environmental engineering, transitioning from a hellish greenhouse to a potentially habitable world. Asteroid mining, if it becomes economically viable, would bring vast quantities of extraterrestrial material into Earth's economy. A single metallic asteroid could contain more platinum than has ever been mined on Earth, potentially revolutionizing technology and industry. Our atom might be mined from such an asteroid and used to build habitats in space, or create exotic materials impossible to manufacture on Earth. This would represent a new form of cosmic recycling, where humans actively transport matter between different worlds for economic purposes. The industrialization of space would create material flows between Earth, the Moon, asteroids, and eventually other planets, with our atom participating in this expanded version of cosmic trade. The concept of a space elevator or other large-scale space infrastructure would require moving enormous quantities of matter from Earth's surface to space. Our atom might be part of such structures, experiencing the transition from terrestrial to space-based existence as humanity expands beyond its home planet. Advanced materials like carbon nanotubes or graphene could make such megastructures possible, allowing the efficient transport of material between Earth's surface and space. Our atom might be part of the carbon lattice that forms such structures, serving as a bridge between terrestrial and orbital environments. Generation ships designed to carry human populations to other star systems would create mobile ecosystems that recycle matter internally over centuries or millennia. Our atom might become part of such a closed system, cycling between air, water, food, and waste in a carefully managed artificial biosphere, traveling between the stars. The challenges of maintaining a closed ecological system over interstellar voyage durations would require perfect recycling of all materials. Our atom would need to be continuously reused, perhaps cycling from waste to food to air to building materials and back again over the course of a journey lasting hundreds or thousands of years. The possibility of uploading human consciousness into artificial substrates raises questions about what forms cosmic recycling might take in a post-biological future. Our atom might someday be part of electronic systems that host digital minds, participating in forms of information processing and storage that we can barely imagine. Silicon-based computing systems could provide substrates for consciousness very different from the carbon-based neural networks of biological brains. Our atom might be part of such artificial minds, helping to process information in quantum computers or other advanced technologies that emerge in the far future. Advanced nanotechnology might allow matter to be recycled and rearranged atom by atom, creating a world where our atom could be transformed from one useful configuration to another with unprecedented precision and control. This would represent the ultimate expression of cosmic recycling, where every atom's position and chemical bonds are deliberately engineered. Molecular assemblers, if they become possible, could take apart any material and reconstruct it into any other arrangement of atoms. Our atom might experience such precise control, being moved from one molecular structure to another according to human design rather than natural processes. The possibility of creating new forms of matter through advanced technology opens up recycling pathways that do not exist in nature. Metamaterials with properties not found in natural substances could provide new environments for our atom to inhabit. Room temperature, superconductors, programmable matter, or other exotic materials might offer experiences unlike anything our atom has encountered in its cosmic journey. The heat death of the universe, predicted by the second law of thermodynamics, might seem to represent an end to cosmic recycling. As entropy increases and energy becomes more uniformly distributed throughout space, the temperature differences that drive cosmic processes would disappear. Yet even in such a universe, quantum effects might allow fluctuations that could recreate organized structures over periods so vast that they cannot be meaningfully compared to anything in our experience. Random quantum fluctuations in the vacuum could occasionally create organized structures by pure chance. Over timescales measured in units of 10 to the 10 to the 10 to the 76 power years, these fluctuations might recreate everything from atoms to brains to entire universes. Our atom might participate in such quantum resurrections, finding itself reconstituted in forms identical to or similar to configurations it experienced in the distant past. The idea of cosmic cycles, where the universe itself might undergo infinite cycles of expansion and contraction, offers another perspective on ultimate recycling. Our atom might be a permanent feature of reality, destined to participate in universe after universe, as cosmic evolution repeats itself with endless variations. Cyclic cosmology models suggest that the Big Bang might not have been a unique beginning, but rather the latest in an infinite series of cosmic cycles. Our atom might have existed through countless previous universes, each time experiencing slightly different physical laws and evolutionary pathways. The many worlds interpretation of quantum mechanics suggests that every quantum event spawns multiple universes where different possibilities are realized. In this view, our atom has infinite versions of itself, each following slightly different paths through the cosmic recycling program. Every quantum decision point creates new universes where different possibilities play out. From this perspective, cosmic recycling operates not just within our universe, but across the infinite multiverse of quantum possibilities. Our atom explores every possible path through space and time, experiencing all possible configurations and transformations across the quantum many worlds. Dark matter and dark energy, which together comprise about 95% of the universe, may participate in forms of recycling we do not yet understand. Our atom's visible matter interacts with these mysterious components in ways that shape cosmic structure and evolution. Future discoveries might reveal that dark matter has its own complex cycles and transformations. Dark matter particles, whatever they might be, could undergo processes analogous to stellar nucleosynthesis or radioactive decay. Our atom might interact with dark matter in ways that affect its own evolution, participating in recycling processes that involve both visible and invisible components of the universe. The search for a theory of quantum gravity might reveal new forms of matter recycling at the intersection of the very large and very small. Our atom's space-time environment might itself be part of a recycling process where the geometry of space emerges from and returns to more fundamental quantum structures. Loop, quantum gravity, and string theory both suggest that space-time has a granular structure at the smallest scales. Our atom might inhabit a universe where space and time themselves are recycled, with the fabric of reality constantly dissolving and reforming at the Planck scale. Philosophical implications of cosmic recycling are profound and far-reaching. The recognition that all matter is constantly being recycled raises fundamental questions about identity and permanence. Our atom maintains its nuclear identity across cosmic ages, but its chemical and structural contexts change continuously. What makes it the same atom throughout these transformations? Ship of Theseus paradoxes arise when we consider that every component of a complex system might be replaced over time. If our atom is part of a living organism that replaces all its atoms over several years, is it still the same organism? The continuity lies not in the specific atoms, but in the patterns and information they carry. The second law of thermodynamics states that entropy always increases in closed systems, yet the universe continuously creates organized structures like stars, planets, and life. This apparent contradiction is resolved by understanding that local decreases in entropy can occur as long as they are accompanied by larger increases elsewhere. Our atom participates in both the creation and destruction of order, playing its part in the cosmic dance between organization and chaos. Complexity theory suggests that simple rules operating on many components can give rise to emergent properties that could not be predicted from the rules alone. Our atom follows simple physical laws, yet when combined with countless other atoms, it can participate in phenomena as complex as consciousness and creativity. From our atom's perspective, recycling is not something that happens to it, but something it participates in actively through its physical properties and interactions. Its nuclear structure determines how it responds to different temperatures and pressures. Its electron configuration affects how it bonds with other atoms. It is not a passive passenger, but an active participant in cosmic evolution. The speed of recycling varies enormously depending on the environment our atom finds itself in. In the hot, dense core of a massive star, nuclear reactions can transform it in seconds. In the cold vacuum of intergalactic space, it might drift unchanged for billions of years. In living organisms, it cycles through different molecules in hours or days. In solid rock, it might remain in the same crystal lattice for millions of years. Each context offers different timescales for transformation and exchange, creating a hierarchy of recycling processes operating simultaneously. Our atom experiences rapid chemical changes while participating in slower geological cycles and even slower stellar evolution. Energy flow drives all cosmic recycling, providing the power needed to move matter between different states and locations. Stars convert nuclear energy to heat and light, which drives atmospheric circulation on planets, which powers weather and erosion, which moves atoms between different reservoirs. Our atom rides these energy flows, being transported and transformed by the heat generated in distant stellar cores billions of years ago. Information also plays a crucial role in cosmic recycling, determining which transformations are possible and how they proceed. DNA preserves information about how to arrange atoms into living structures across geological time. Crystalline structures encode information about stable atomic arrangements under specific conditions. Even the quantum fields that permeate space carry information about particle interactions and conservation laws. Our atom carries information about its history in the form of isotopic signatures, energy states, and quantum properties. The ratio of different isotopes in a sample can reveal where and when the atoms formed. Electronic energy states reflect the atom's recent chemical environment. Nuclear spin states can preserve quantum information across molecular transformations. This information influences how our atom interacts with other matter and energy, affecting the paths it takes through cosmic recycling. In some sense, our atom remembers its past and uses that memory to navigate its future, with each transformation building on the history encoded in its structure. The universality of recycling means that every atom in the universe has a biography as complex and interesting as our own atom's story. The carbon in a tree, the iron in a skyscraper, the calcium in our bones, all have traveled similar journeys through space and time, each carrying its own unique history of cosmic transformation. When we touch another person, atoms from our bodies intermingle with theirs. When we breathe, we exchange atoms with the atmosphere that have been part of countless other organisms. When we eat, we incorporate atoms that were recently part of plants or animals. This constant atomic exchange connects us physically to all life on Earth, and ultimately to the cosmos beyond. Recognizing cosmic recycling can change how we think about waste and consumption on human scales. Every atom we use has been part of countless other configurations throughout cosmic history, and will be part of countless more in the future. Nothing is ever truly wasted, only transformed into different arrangements that may be more or less useful for human purposes. The circular economy movement in human society mirrors cosmic recycling principles, seeking to eliminate waste by ensuring that all materials flow through closed loops of use and reuse. Our atom has always lived in such a circular economy, and human society is gradually learning to emulate cosmic principles of recycling and conservation. Climate change represents a disruption in Earth's natural recycling processes, as human activities alter the flows of carbon, nitrogen, and other elements through the biosphere. Understanding cosmic recycling provides perspective on these changes, revealing them as temporary perturbations in systems that operate over much longer timescales. The concept of Spaceship Earth, popularized by environmentalists, recognizes that our planet operates as a closed system for most practical purposes. Material that flows out of Earth's atmosphere to space is negligible compared to the planet's total mass. Our atom has experienced this closure, cycling between Earth's atmosphere, oceans, crust, and biosphere in endless loops over geological time. Conservation laws in physics ensure that cosmic recycling operates according to strict rules that apply throughout the universe. Energy cannot be created or destroyed, only converted from one form to another. Matter and antimatter can annihilate each other to create energy, but the total amount of mass energy in the universe remains constant according to Einstein's relativity. Electric charge is conserved in all interactions. These laws guarantee that our atom will always be part of something, even if that something changes repeatedly. The story of cosmic recycling is ultimately a story of transformation rather than loss. Our atom has been a hydrogen nucleus in the early universe. Part of stellar plasma, the universe operates on the principle of eternal recycling, a cosmic circulation system where nothing is ever truly lost, only transformed and redistributed. Our atom has experienced this firsthand throughout its billion-year journey, moving from stellar cores to planetary surfaces, from rocks to life, and back again. This recycling is not just a feature of the universe, it is the universe's most fundamental characteristic, the process that allows matter to explore every possible state and combination. Consider the grand scale of this cosmic recycling program. Galaxies themselves participate, exchanging matter through gravitational interactions that can scatter stars and gas clouds across millions of light years. When galaxies collide, as our Milky Way will with Andromeda in about 4 billion years, their stellar populations and gas clouds mix, creating new opportunities for stellar formation and planetary development. Our atom might someday witness such a galactic merger, finding itself in a completely different region of space as gravitational forces rearrange the cosmic landscape. The galaxy it had called home for billions of years would be transformed into something new, a larger elliptical galaxy, where stellar formation proceeds differently and where the opportunities for planetary systems and life might be quite different. But even without such dramatic events, the galaxy acts as a cosmic mixing bowl. Stellar winds carry matter from evolved stars into the interstellar medium. White dwarf stars, the dense remnants of sun-like stars, gradually cool over trillions of years, eventually returning their mass to space through various poorly understood processes. Our atom might someday be part of such a stellar corpse, waiting patiently for cosmic processes to liberate it once again. Star formation continues to recycle matter on galactic scales. Massive molecular clouds collapse under their own gravity, forming new generations of stars from material that has already been processed through previous stellar generations. Our atom may have been part of many different stars throughout cosmic history, each time being subjected to different conditions in stellar cores. The first-generation stars were massive giants that burned through their fuel quickly and died young in spectacular supernova explosions. Second-generation stars, formed from supernova-enriched material, were smaller and longer-lived, burning for billions rather than millions of years. Our atom has witnessed this transition, participating in the universe's shift from violent, short-lived stellar evolution to the more sedate nuclear burning that characterizes modern stars. Third-generation stars, formed from even more heavily processed material, can be smaller still and may burn for trillions of years. Our atom might someday be incorporated into one of these ultra-long-lived red dwarf stars, experiencing nuclear fusion at the gentlest possible pace and remaining bound within stellar material for a significant fraction of the universe's total age. The stellar life cycle itself represents a perfect example of cosmic recycling. Main sequence stars convert hydrogen to helium for billions of years, then evolve through red giant phases where they shed their outer layers back into space. These planetary nebulae, glowing shells of gas surrounding white dwarf cores, return most of a star's mass to the interstellar medium, enriched with helium and heavier elements produced during the star's lifetime. Our atom might be part of such a gentle dispersal, riding stellar winds at speeds of hundreds of kilometers per second into the vast spaces between stars. Unlike the violent ejection from a supernova, this process allows matter to escape gradually, mixing with the interstellar medium over thousands of years and creating beautiful, glowing structures visible to telescopes across the galaxy. Even the most extreme stellar remnants participate in cosmic recycling, though on much longer timescales. Black holes, which seem to trap matter forever behind their event horizons, may actually evaporate through Hawking radiation over periods so long that they dwarf the current age of the universe. If our atom ever falls into a black hole, it would be condemned to an unimaginably long wait before being released as thermal radiation. The process would be so slow that a black hole with the mass of our Sun would take longer than 10 to the 67th power years to evaporate completely. During this time, the universe would undergo transformations we can barely imagine. Galaxies would drift apart due to cosmic expansion, stars would burn out, and the cosmos would enter phases of evolution for which we have no names. Yet even this represents recycling on the grandest possible scale. The Hawking radiation that eventually emerges from evaporating black holes carries the quantum information that fell in, ensuring that our atom's identity persists in some form even through the most extreme gravitational processing. The conservation of information, a fundamental principle of physics, guarantees that our atom's cosmic biography continues, even in circumstances that seem to erase all traces of its past. Planetary systems provide another arena for cosmic recycling, operating on timescales intermediate between stellar and galactic processes. Planets exchange atmosphere with space through various mechanisms. Some lose their atmospheres entirely when their host stars enter red giant phases, returning planetary material directly to space without the need for stellar death or collision. Our atom might experience such atmospheric loss if it becomes part of a planetary atmosphere. Solar wind, the stream of particles flowing from a star, can gradually strip away planetary atmospheres over billions of years. This process returns planetary material to space, where it can be incorporated into other worlds or captured by passing stellar systems. Comets and asteroids serve as cosmic delivery services, carrying material between different parts of planetary systems and even between different stellar systems. Our atom might become part of a comet, spending thousands of years in the cold outer reaches of a solar system before making a spectacular journey toward the inner planets, sublimating its ices and losing mass to space with each passage near the star. Some comets are ejected from their parent systems entirely, becoming interstellar wanderers that may eventually be captured by other stars. Our atom could thus travel between stellar systems aboard these icy spacecraft, experiencing a form of interstellar migration that takes millions or billions of years to complete. The recently discovered interstellar objects like Oumuamua and Borisov demonstrate that such exchanges between stellar systems actually occur. Our atom might someday be part of an asteroid or comet that escapes our solar system and journeys to another star, carrying with it a sample of our cosmic neighborhood to seed new worlds with familiar elements. Meteorite impacts provide another mechanism for recycling material between worlds. Mars rocks have been found on Earth, blasted off the red planet by asteroid impacts and traveling through space for millions of years before landing on our world. Our atom might make such a journey, experiencing life on one planet before being delivered to another through cosmic bombardment. The exchange of material between worlds raises fascinating questions about the spread of life throughout the universe. If our atom was once part of a living organism on one world, could it carry chemical signatures or even microscopic life forms to another world? The theory of panspermia suggests that life might spread between planets or even between stellar systems through such material exchange. Ocean worlds in the outer solar system, such as Europa and Enceladus, demonstrate that liquid water and potentially habitable environments exist in places previously thought too cold for life. Our atom might someday be part of life in these exotic environments, experiencing biology in conditions radically different from Earth. Subsurface oceans heated by tidal forces could host ecosystems that persist for billions of years. The search for life beyond our solar system focuses increasingly on exoplanets in habitable zones around other stars. Our atom might someday be incorporated into the atmosphere, oceans, or even biosphere of such a world, participating in alien chemistry and perhaps alien biology that we can barely imagine. Cosmic recycling operates not just on large scales, but on quantum scales as well. Virtual particles constantly appear and disappear in the vacuum of space, borrowing energy from the quantum field and paying it back so quickly that the transactions are undetectable. Our atom participates in this quantum foam, its fields interacting with these fleeting virtual particles in ways that may influence its properties and behavior. The expansion of the universe itself affects cosmic recycling by gradually increasing the distances between galaxies and reducing the density of matter in space. As the universe expands and cools, opportunities for matter to interact and recombine become fewer and farther between. Our atom's future recycling events will become increasingly rare as cosmic expansion separates the fuel for new stellar formation. Yet even in a universe grown old and cold, recycling continues through increasingly exotic processes. Proton decay, if it occurs as some theories predict, would ultimately return all matter to energy, but only after periods so long that they make the age of the universe seem like an instant. Our atom might persist in some form through the entire history of the cosmos, witnessing its transition from a hot, dense fireball to a cold, empty expanses of space. The anthropic principle suggests that the universe's physical constants are finely tuned for the existence of stars, planets, and life. This fine-tuning may be necessary for cosmic recycling to operate efficiently. If gravity were slightly stronger, all matter would collapse into black holes too quickly for complex structures to form. If it were weaker, matter would never condense into stars at all. Our atom exists in a universe where recycling is not just possible but inevitable. The nuclear binding energies that hold atomic nuclei together, the electromagnetic forces that govern chemical reactions, and the gravitational forces that sculpt cosmic structure all conspire to create conditions where matter can explore countless different states and combinations over cosmic time. Human technology has begun to participate in cosmic recycling in new ways. Nuclear reactors split heavy elements and fuse light ones, mimicking stellar nucleosynthesis, but in controlled terrestrial environments. Our atom might someday be part of such artificial stellar processes, experiencing nuclear transformation guided by human engineering rather than stellar evolution. Space exploration represents humanity's first attempts to participate directly in interplanetary material exchange. Every spacecraft we send to other worlds carries terrestrial atoms away from Earth, while sample return missions bring alien worlds to our laboratories. Our atom might be part of this deliberate cosmic recycling, traveling to other worlds aboard human-built vehicles. The terraforming of other worlds, should it ever become feasible, would involve recycling matter on planetary scales. Converting the atmosphere of Venus or Mars into something breathable would require moving enormous quantities of atoms from one chemical form to another. Our atom might participate in such grand engineering projects, being transformed from part of a toxic atmosphere into a component of a breathable one. Asteroid mining, if it becomes economically viable, would bring vast quantities of extraterrestrial material into Earth's economy. Our atom might be mined from an asteroid and used to build habitats in space or exotic materials impossible to create on Earth. This would represent a new form of cosmic recycling, where humans actively transport matter between different worlds for economic purposes. The concept of a space elevator or other large-scale space infrastructure would require moving enormous quantities of matter from Earth's surface to space. Our atom might be part of such structures, experiencing the transition from terrestrial to space-based existence as humanity expands beyond its home planet. Generation ships designed to carry human populations to other star systems would create mobile ecosystems that recycle matter internally over centuries or millennia. Our atom might become part of such a closed system, cycling between air, water, food, and waste in a carefully managed artificial biosphere traveling between the stars. The possibility of uploading human consciousness into artificial substrates raises questions about what forms cosmic recycling might take in a post-biological future. Our atom might someday be part of electronic systems that host digital minds, participating in forms of information, processing, and storage that we can barely imagine. Advanced nanotechnology might allow matter to be recycled and rearranged atom by atom, creating a world where our atom could be transformed from one useful configuration to another with unprecedented precision and control. This would represent the ultimate expression of cosmic recycling, where every atom's position and chemical bonds are deliberately engineered. The heat death of the universe, predicted by thermodynamics, might seem to represent an end to cosmic recycling. As entropy increases and energy becomes more uniformly distributed, the temperature differences that drive cosmic processes would disappear. Yet even in such a universe, quantum effects might allow fluctuations that could recreate organized structures over periods so vast that they cannot be meaningfully compared to anything in our experience. The idea of cosmic cycles, where the universe itself might undergo infinite cycles of expansion and contraction, offers another perspective on ultimate recycling. Our atom might be a permanent feature of reality, destined to participate in universe after universe, as cosmic evolution repeats itself with endless variations. The many worlds interpretation of quantum mechanics suggests that every quantum event spawns multiple universes. In this view, our atom has infinite versions of itself, each following slightly different paths through the cosmic recycling program. Every quantum decision point creates new universes where different possibilities are realized. Dark matter and dark energy, which together comprise most of the universe, may participate in forms of recycling we do not yet understand. Our atom's visible matter interacts with these mysterious components in ways that shape cosmic structure and evolution. Future discoveries might reveal that dark matter has its own complex cycles and transformations. The search for a theory of quantum gravity might reveal new forms of matter recycling at the intersection of the very large and very small. Our atom's space-time environment might itself be part of a recycling process, where the geometry of space emerges from and returns to more fundamental quantum structures. Philosophical implications of cosmic recycling are profound. The recognition that all matter is constantly being recycled raises questions about identity and permanence. Our atom maintains its nuclear identity across cosmic ages, but its chemical and structural contexts change continuously. What makes it the same atom throughout these transformations? The second law of thermodynamics states that entropy always increases, yet the universe continuously creates organized structures like stars, planets, and life. This apparent contradiction is resolved by understanding that local decreases in entropy can occur as long as they are accompanied by larger increases elsewhere. Our atom participates in both the creation and destruction of order, playing its part in the cosmic dance between organization and chaos. From our atom's perspective, recycling is not something that happens to it, but something it participates in actively. Its chemical properties determine how it bonds with other atoms. Its nuclear structure affects how it responds to the environments it encounters. It is not a passive passenger, but an active participant in cosmic evolution. The speed of recycling varies enormously, depending on the environment our atom finds itself in. In the hot, dense core of a star, nuclear reactions can transform it in seconds. In the cold vacuum of space, it might drift unchanged for billions of years. In living organisms, it cycles through different molecules in hours or days. Each context offers different timescales for transformation and exchange. Energy flow drives all cosmic recycling. Stars convert nuclear energy to heat and light, which drives atmospheric circulation on planets, which powers weather and erosion, which moves atoms between different reservoirs. Our atom rides these energy flows, being transported and transformed by the heat generated in distant stellar cores. Information also plays a crucial role in cosmic recycling. DNA preserves information about how to arrange atoms into living structures. Crystalline structures contain information about stable atomic arrangements under specific conditions. Even the quantum fields that permeate space carry information about particle interactions and conservation laws. Our atom carries information about its history in the form of isotopic signatures, energy states, and quantum properties. This information influences how it interacts with other matter and energy, affecting the paths it takes through cosmic recycling. In some sense, our atom remembers its past and uses that memory to navigate its future. The universality of recycling means that every atom in the universe has a biography as complex and interesting as our own atom's story. The carbon in the paper this story is written on, the oxygen in the air you breathe, the calcium in your bones, all have traveled similar journeys through space and time, each carrying its own unique history of cosmic transformation. Recognizing cosmic recycling can change how we think about waste and consumption on Earth. Every atom we use has been part of countless other configurations throughout cosmic history and will be part of countless more in the future. Nothing is ever truly wasted, only transformed into different arrangements. The circular economy movement in human society mirrors cosmic recycling principles, seeking to eliminate waste by ensuring that all materials flow through closed loops of use and reuse. Our atom has always lived in such a circular economy, and human society is gradually learning to emulate cosmic principles of recycling and conservation. Climate change represents a disruption in Earth's natural recycling processes, as human activities alter the flows of carbon, nitrogen, and other elements through the biosphere. Understanding cosmic recycling provides perspective on these changes, revealing them as temporary perturbations in systems that operate over much longer timescales. The concept of Spaceship Earth, popularized by environmentalists, recognizes that our planet operates as a closed system for most practical purposes. Our atom has experienced this closure, cycling between Earth's atmosphere, oceans, crust, and biosphere in endless loops over geological time. Conservation laws in physics ensure that cosmic recycling operates according to strict rules. Energy cannot be created or destroyed, only converted from one form to another. Matter and antimatter can annihilate each other to create energy, but the total amount of mass energy in the universe remains constant. These laws guarantee that our atom will always be part of something, even if that something changes repeatedly. The story of cosmic recycling is ultimately a story of transformation rather than loss. Our atom has been a hydrogen nucleus in the early universe, part of stellar plasma in ancient stars, component of rocky planets, participant in biological processes, and will continue to explore new states of existence throughout cosmic time. Each transformation adds new chapters to its biography without erasing previous ones. Understanding cosmic recycling reveals the deep interconnectedness of all matter in the universe. Our atom's journey links it to distant stars, alien worlds, and even other forms of life that might exist throughout the cosmos. We are all part of the same cosmic recycling program, sharing atoms that have traveled unimaginable distances and experienced incredible transformations. the patience required for cosmic recycling is beyond human comprehension. Our atom has already waited billions of years to reach its current state, and may wait billions more before its next major transformation. Yet it does not experience boredom or restlessness. It simply exists, ready for whatever cosmic processes might involve it next. As we look toward the future, cosmic recycling offers both hope and perspective. Our individual lives are brief moments in our atom's cosmic biographies, but those atoms will continue their journeys long after we are gone. They will carry forward some trace of their time with us, perhaps in their energy states or quantum properties, as they move on to new adventures. The universe is perhaps best understood not as a collection of separate objects, but as a vast recycling system where matter flows continuously between different states and configurations. Our atom is both product and participant in this cosmic circulation, a temporary arrangement of protons, neutrons, and electrons that has somehow gained the ability to contemplate its own recycling through the medium of consciousness. In the end, cosmic recycling ensures that nothing is ever permanently lost, only endlessly transformed. Our atom's journey from the first stars to the present moment is just one chapter in an infinite story of cosmic transformation. The recycling continues, carrying our atom toward futures we cannot imagine and adventures we cannot anticipate, in a universe where transformation is the only constant and recycling is the fundamental operating principle. Deep time stretches before our atom like an infinite ocean, and within its vast expanse lies a question that touches the very heart of existence. What happens when atoms themselves begin to break down? We have followed our particle through stellar births and deaths, through the formation of worlds and the emergence of life. But now we must confront the possibility that even atoms, those seemingly eternal building blocks of reality, may not last forever. The proton at the heart of our atom has been stable for over 13 billion years, unchanged since the first moments after the Big Bang. It has survived temperatures of billions of degrees in stellar cores, the crushing pressures of planetary formation, and the gentle chemistry of living systems. Yet theories in physics suggest that even protons may not be immortal, that given enough time, they too will decay and transform. Proton decay remains one of the great unsolved mysteries of modern physics. The Standard Model of Particle Physics, our best current theory of fundamental forces and particles, predicts that protons should be absolutely stable. Yet many theories that attempt to unify the fundamental forces suggest that protons must eventually decay, albeit with lifetimes so long that they dwarf the current age of the universe by factors that have no name. If protons do decay, the process would be extraordinarily slow. Current experiments have placed the proton lifetime at greater than 10 to the 34th power years, a number so large that it becomes almost meaningless to human comprehension. To put this in perspective, this is longer than the current age of the universe by a factor of more than 10 to the 24th power. Our atom might experience this ultimate transformation, watching as the proton at its core suddenly and spontaneously transforms into lighter particles. Theoretical models suggest the proton might decay into a positron and a neutral pion, which would immediately decay further into gamma rays. In this process, our atom would literally disintegrate, its nucleus disappearing in a flash of radiation. But this decay, if it occurs at all, would happen in the far future, when the universe has become a vastly different place. By the time proton decay becomes noticeable, virtually all the stars will have burned out, the cosmic microwave background will have cooled to near absolute zero, and the expansion of space will have carried galaxies so far apart that they disappear beyond each other's observable horizons. Even before proton decay becomes significant, other forms of atomic breakdown will reshape the cosmic landscape. Radioactive elements, those unstable nuclei that gradually transform through various decay processes, are already demonstrating atomic mortality on more accessible timescales. Our atom, if it has become part of a radioactive nucleus, experiences this breakdown firsthand. Consider if our atom has become part of a uranium nucleus containing 92 protons and typically 146 neutrons. Uranium-238, the most common isotope, has a half-life of about 4.5 billion years, comparable to the age of the Earth. Our atom, as part of this nucleus, exists in a state of perpetual uncertainty, never knowing when the quantum trigger will cause the nucleus to split apart. The decay process is fundamentally probabilistic, governed by quantum mechanics in ways that make it impossible to predict exactly when any individual nucleus will decay. Our atom might be part of a uranium nucleus that decays tomorrow, or it might remain stable for tens of billions of years. The half-life tells us only the statistical behavior of large numbers of nuclei, not the fate of any particular atom. When radioactive decay finally occurs, it represents a fundamental transformation of our atom's identity. Alpha decay releases an alpha particle, consisting of 2 protons and 2 neutrons, reducing the atomic number and creating a new element. Our atom, if it loses an alpha particle, literally becomes a different element with different chemical properties and a different nuclear identity. Beta decay involves the transformation of a neutron into a proton, an electron, and a neutrino, increasing the atomic number by 1. This process can convert our atom from one element to another without changing its mass number, shifting its position in the periodic table, and altering its chemical behavior. These decay processes create chains of transformation that can last for millions or billions of years. The uranium decay series includes more than a dozen different isotopes before finally reaching stable lead 206. Our atom might experience this entire chain, being transformed stepwise from uranium to thorium to radium to radon and so on, each transformation bringing new chemical properties and new possibilities for interaction. The energy released during radioactive decay has powered geological processes throughout Earth's history. The heat generated by radioactive elements in Earth's core helps drive plate tectonics, volcanism, and the magnetic field that protects us from cosmic radiation. Our atom, through its radioactive transformations, might have contributed to the energy that keeps Earth geologically active. Radioactive dating techniques rely on the steady decay rates of unstable isotopes to measure the ages of rocks, fossils, and other materials. Carbon-14 dating, potassium-argon dating, and uranium lead dating all depend on understanding how radioactive atoms transform over time. Our atom, if it was radioactive, might have served as a cosmic clock, marking the passage of deep time through its nuclear transformations. In the far future, when the universe has cooled and expanded far beyond its current state, radioactive decay will continue to operate even after all the stars have died. Some isotopes have half-lives measured in trillions of years or more, ensuring that nuclear transformations will continue long after the universe has entered what cosmologists call the degenerate era. During this era, brown dwarfs and white dwarfs will be the most massive objects in the universe, slowly cooling and fading as they radiate away their remaining heat. Our atom might be part of such a cooling stellar remnant, experiencing the gradual approach to thermal equilibrium with the cosmic background radiation. Even in this cold, dark universe, quantum processes will continue to operate. Quantum tunneling might allow our atom to participate in nuclear reactions that would be impossible at the low temperatures of the degenerate era. The probability would be extraordinarily small, but given enough time, even the most unlikely quantum events become virtually certain. White dwarf stars are predicted to eventually crystallize as they cool, forming vast crystal lattices of atomic nuclei suspended in degenerate electron matter. Our atom might become part of such a cosmic crystal, locked in a perfectly ordered structure that could persist for trillions of years. This crystalline state would represent a form of atomic organization never seen in the warm universe of today. But even crystallized white dwarfs are not permanent. Quantum tunneling could allow the carbon and oxygen nuclei in these stellar remnants to fuse slowly over enormous timescales, gradually converting white dwarfs into neutron stars. Our atom might experience this ultra-slow nuclear burning, participating in fusion reactions spread out over periods longer than the current age of the universe. The concept of vacuum decay presents another scenario for atomic breakdown on cosmic scales. Some theories suggest that the Higgs field, which gives particles their mass, might exist in a metastable state rather than a true ground state. If this is the case, quantum fluctuations could trigger a phase transition that would propagate throughout the universe at the speed of light. Such a vacuum decay event would fundamentally alter the properties of matter throughout the universe. Our atom's mass, charge, and other properties are determined by its interactions with quantum fields. If these fields undergo a phase transition, our atom could be transformed into something entirely different, with new physical properties and behaviors. The bubble of altered spacetime created by vacuum decay would be completely undetectable until it arrived, moving at light speed and carrying with it new physical laws. Our atom might experience a complete transformation of its fundamental nature, finding itself subject to different forces and conservation laws than those that have governed it throughout cosmic history. False vacuum decay remains highly speculative, and most physicists consider it unlikely to occur in our observable universe. But the possibility illustrates how even the fundamental constants and laws of physics that determine atomic behavior might not be as permanent as they appear. Quantum field theory describes particles like our atom not as solid objects but as excitations in underlying quantum fields. From this perspective, atomic breakdown might be understood as the gradual dissipation of these excitations back into the quantum vacuum. Our atom would not disappear, but would return to the field state from which it originally emerged. The uncertainty principle of quantum mechanics ensures that even the vacuum of space is not truly empty but filled with quantum fluctuations that create virtual particle pairs. These pairs normally annihilate each other almost immediately, but near the event horizon of a black hole, one particle from a pair might escape while the other falls in, creating Hawking radiation. Our atom, if it ever falls into a black hole, would experience perhaps the most extreme form of breakdown possible in the known universe. As it approaches the event horizon, tidal forces would stretch it apart, separating its electrons from its nucleus and ultimately breaking down its nuclear structure entirely. From the perspective of an outside observer, our atom would appear to slow down and freeze at the event horizon, its image redshifted to longer and longer wavelengths until it fades from view. But the information content of our atom, according to quantum mechanics, must somehow be preserved and eventually released through Hawking radiation. The information paradox surrounding black holes raises fundamental questions about the nature of atomic identity and breakdown. If our atom falls into a black hole, does it cease to exist as a distinct entity, or does its information somehow survive the transition? Recent theoretical work suggests that quantum entanglement between the atom and the Hawking radiation might preserve its information in encrypted form. The process would be extraordinarily slow. A black hole with the mass of our Sun would take approximately 10 to the 67th power years to evaporate completely through Hawking radiation. During this time, our atom's information would be gradually released in the thermal radiation, but it would be scrambled beyond any hope of reconstruction. By the time black holes begin to evaporate significantly, the universe will have entered what cosmologists call the black hole era. During this phase, black holes will be the dominant massive objects in the cosmos, slowly shrinking as they emit Hawking radiation. Our atom might spend most of this era trapped within one of these slowly evaporating monsters. The temperature of Hawking radiation is inversely proportional to the black hole's mass, so small black holes evaporate much faster than large ones. Primordial black holes with masses comparable to mountains would evaporate in times comparable to the current age of the universe, while supermassive black holes might persist for googles of years. Our atom could experience very different fates depending on which type of black hole it encounters. In a small black hole, it would be quickly converted to Hawking radiation. In a large black hole, it might remain trapped for periods so long that the very concept of time becomes meaningless. Hawking radiation itself provides another perspective on atomic breakdown. The radiation emerges as a thermal spectrum of particles, predominantly photons and neutrinos, but occasionally including more massive particles like electrons and protons. Our atom might be reconstituted from this radiation, its constituent particles emerging separately from the black hole over vast periods of time. The holographic principle suggests that all the information falling into a black hole is somehow encoded on its two-dimensional surface. From this perspective, our atom doesn't break down when it enters the black hole, but is instead stored as information on the event horizon, later released through the complex correlations in Hawking radiation. Even after black holes evaporate and protons decay, the universe would not be empty. It would be filled with a dilute gas of electrons, positrons, neutrinos, and photons, all at extremely low temperatures, approaching absolute zero. Our atom, having been broken down into its constituent particles, would be part of this tenuous plasma. In this dark era, the universe would be dominated by leptons, those particles like electrons and neutrinos that don't experience the strong nuclear force. Positrons and electrons would occasionally annihilate each other, converting matter to energy and further diluting the cosmic soup. Our atom's electrons might participate in these annihilation events, disappearing in flashes of gamma radiation. But even this is not the end. Quantum fluctuations in the vacuum might occasionally create particle pairs that don't immediately annihilate. Over periods measured in units of 10 to the 10 to the 67 power years, random fluctuations might recreate complex structures, perhaps even structures identical to the atoms, molecules, and organisms that existed in the earlier universe. The Poincaré recurrence theorem suggests that any finite system must eventually return arbitrarily close to its initial state, if given enough time. While the universe is probably not finite, quantum fluctuations in certain cosmological models could recreate arbitrary configurations of matter over truly astronomical timescales. Our atom might thus be reconstituted an infinite number of times through pure chance, experiencing countless variations of its cosmic journey. Each recreation would be statistically independent, with no memory of previous incarnations, yet the patterns might be identical down to the quantum level. These quantum resurrections would occur in a universe so different from today's that they would be utterly isolated events. The recreated structures would exist briefly in vast empty spaces, before thermodynamic processes caused them to dissolve back into the vacuum. Our atom might experience brief moments of complex organization separated by eternities of chaos. Some cosmological models suggest even more exotic scenarios for ultimate atomic breakdown. Cyclic universes that undergo infinite cycles of expansion and contraction would subject our atom to repeated cosmic recycling. Each cycle might begin with a new Big Bang that recreates matter and energy in slightly different configurations. String theory and other candidates for quantum gravity suggest that space and time themselves might have granular structure at the Planck scale. Our atom might inhabit a universe where space-time periodically dissolves and reforms, carrying atomic structure down to the most fundamental level of reality. The landscape of string theory allows for an enormous number of possible universes, with different physical constants and laws. Our atom might tunnel between these different cosmic states, experiencing physics that varies from one region of the multiverse to another. In some of these alternate universes, atoms might be stable in ways unknown in our cosmos. Cosmological natural selection, proposed by physicist Lee Smolin, suggests that universes might evolve through black hole formation, with each black hole potentially spawning a new universe with slightly modified physical constants. Our atom might participate in this cosmic evolution, helping to determine which physical laws persist across cosmic generations. The anthropic principle observes that the physical constants of our universe seem finely tuned to allow the existence of atoms, stars, planets, and life. Small changes in the strength of nuclear forces or the mass of fundamental particles could make atomic structure impossible. Our atom exists in one of the perhaps infinitesimally rare universes where such complexity can emerge. But this fine-tuning might not be permanent. Changes in fundamental constants over cosmic time could gradually alter the stability of atomic nuclei. Our atom might experience a universe where the forces that hold it together slowly weaken or strengthen, leading to new forms of stability or instability that don't exist today. Grand unified theories attempt to describe the electromagnetic, weak, and strong nuclear forces as different aspects of a single fundamental force. In these theories, the apparent stability of protons is an illusion that breaks down over extremely long timescales as the unified force reveals its true nature. Supersymmetry, another theoretical framework in particle physics, predicts the existence of partner particles for all known particles. If these supersymmetric particles are discovered, they might provide new pathways for atomic breakdown or stability that are not predicted by current theories. Extra dimensions, proposed in string theory and other models, could provide escape routes for particles that allow them to leave our familiar three-dimensional space. Our atom might break down by having some of its constituents tunnel into these extra dimensions, leaving behind incomplete fragments in our observable universe. The measurement problem in quantum mechanics raises questions about what constitutes observation and when quantum superpositions collapse into definite states. Our atom exists in quantum superposition states until measurements or interactions cause collapse. Different interpretations of quantum mechanics suggest different ultimate fates for quantum information. Consciousness itself might play a role in atomic breakdown if certain interpretations of quantum mechanics are correct. The many minds interpretation suggests that consciousness selects which branch of quantum reality to experience. Our atom might follow different breakdown pathways, depending on which branches of quantum reality conscious observers happen to inhabit. Emergence theory suggests that complex properties arise from simple rules operating on many components. Our atom's apparent stability and chemical properties emerge from the quantum mechanical behaviors of protons, neutrons, and electrons. As these emergent properties break down over cosmic time, our atom might experience forms of dissolution that cannot be understood by examining its components in isolation. Information theory provides another lens through which to view atomic breakdown. Our atom can be described as a pattern of information encoded in quantum fields. As this information disperses through various physical processes, the atom gradually loses its coherent identity and merges with the cosmic background of random quantum fluctuations. The holographic principle suggests that the information content of any region of space is limited by the area of its boundary rather than its volume. Our atom's information might be fundamentally constrained by such holographic bounds, influencing how it can break down and whether its information can be preserved through various cosmic transitions. Quantum error correction, borrowed from computer science, might operate in natural systems to preserve information against decay and decoherence. Our atom might participate in natural quantum error correction schemes that allow complex structures to persist longer than naive calculations would suggest. Non-locality in quantum mechanics means that our atom can be entangled with other particles across arbitrary distances, creating correlations that transcend spatial separation. As our atom breaks down, its quantum information might remain entangled with remote parts of the universe, preserving aspects of its identity in non-local correlations. The measurement of time itself becomes problematic over the extreme scales relevant to atomic breakdown. General relativity shows that time is relative and can be dilated by gravity and motion. Our atom might experience time very differently depending on its cosmic environment, potentially achieving effective immortality by falling into regions where time dilation approaches infinity. Cosmic inflation theory suggests that our observable universe is just one bubble in an infinitely expanding multiverse. Our atom might tunnel between different inflationary bubbles, each with different physical laws and constants. The breakdown processes relevant in our bubble might not apply in regions with different fundamental physics. The measure problem in cosmology asks how to assign probabilities to different infinite sets in an infinite multiverse. Our atom's breakdown might be better understood as a question of which infinite subset of the multiverse we happen to observe, rather than as a specific physical process with a definite outcome. Eternal inflation models suggest that cosmic inflation continues forever in most regions of the multiverse, creating infinite numbers of bubble universes. Our atom might be copied infinite times across these different bubbles, experiencing every possible variation of cosmic history and atomic breakdown. Dark energy and dark matter, which together comprise most of the universe, might participate in atomic breakdown in ways we don't yet understand. Future discoveries might reveal that dark particles can catalyze proton decay or participate in other breakdown processes involving ordinary matter. Modified theories of gravity, alternatives to general relativity, might predict different ultimate fates for matter in the universe. Our atom might experience breakdown processes that depend on gravitational effects, not captured by Einstein's theory. The cosmological constant problem in physics questions why the vacuum energy density is so much smaller than theoretical predictions suggest. Solutions to this problem might reveal new aspects of vacuum structure that affect how atoms persist or break down over cosmic time. Quantum gravity theories attempt to reconcile general relativity with quantum mechanics at the Planck scale, where both become important. Our atom might participate in quantum gravitational processes that cause breakdown or transformation in ways not predicted by either theory alone. The arrow of time problem asks why time seems to flow in one direction despite the fact that the fundamental laws of physics are mostly time-symmetric. Our atom's breakdown might be related to whatever physical processes establish the thermodynamic arrow of time. Causal dynamical triangulation and other approaches to quantum gravity suggest that space-time itself has a complex, fluctuating structure at the smallest scales. Our atom might inhabit a universe where space and time are constantly being torn apart and sewn back together by quantum gravitational effects. Loop quantum gravity predicts that space has a discrete, granular structure at the Planck scale. Our atom might experience this discreteness directly if it participates in quantum gravitational phenomena that probe the fundamental structure of spacetime. The black hole war in theoretical physics centers on whether information is preserved when matter falls into black holes. Different resolutions of this conflict suggest different possibilities for what happens to our atom's information during the most extreme breakdown processes. Firewall proposals suggest that black hole horizons are surrounded by walls of high-energy particles that would destroy any infalling matter. Our atom might be incinerated by these firewalls rather than crossing peacefully into the black hole interior. The ER equals EPR conjecture proposes that quantum entanglement and wormholes are two descriptions of the same phenomenon. Our atom might be connected to remote parts of the universe through quantum wormholes, allowing its information to persist even when its local structure breaks down. Holographic entanglement entropy suggests that the entanglement structure of quantum fields encodes the geometry of spacetime. Our atom's breakdown might be fundamentally related to changes in the entanglement patterns that define the space it inhabits. Tensor network models of holography describe space as emerging from patterns of quantum entanglement. Our atom might literally be made of entanglement, with its breakdown representing the dissolution of entanglement patterns back into the quantum vacuum. The it from bit hypothesis suggests that physical reality emerges from information and computation, rather than being fundamentally material. Our atom might be better understood as a pattern of information processing that gradually dissolves as the computationally active regions of the universe shut down. Digital physics proposes that the universe operates like a vast computer, with particles and fields being discrete computational elements. Our atom's breakdown might represent termination of the computational processes that maintain its existence within cosmic information processing systems. The simulation hypothesis questions whether our reality might be computed by some advanced civilization. If our universe is indeed a simulation, our atom's breakdown might occur when computational resources are reallocated or when the simulation is terminated. Consciousness uploading proposals suggest that minds might be transferred from biological brains to artificial substrates. Our atom might become part of such uploaded consciousness, experiencing breakdown when the artificial systems that host digital minds eventually fail or are shut down. Artificial intelligence development might create minds that persist long after biological intelligence has disappeared. Our atom could become part of artificial systems that explore new forms of organization and breakdown not available to naturally evolved structures. Nanotechnology might eventually allow matter to be manipulated atom by atom with perfect precision. Our atom could be preserved indefinitely through constant repair and maintenance, achieving effective immortality through technological intervention. Space colonization might transport our atom to environments far from Earth, where different breakdown processes become important. Life in space, habitats, or on other worlds might subject our atom to cosmic radiation, extreme temperatures, or exotic matter that accelerates certain decay processes. Genetic engineering and synthetic biology might create new forms of life that can persist in environments where natural organisms cannot survive. Our atom might become part of engineered life forms designed to thrive during the universe's transition to darker, colder ages. Cryonic preservation attempts to prevent biological decay by freezing organisms at very low temperatures. Our atom might experience such preservation, remaining locked in an inactive state while civilization develops technologies capable of reversal or repair of current breakdown processes. Time travel, if possible, might allow our atom to avoid breakdown by escaping to earlier periods when the universe was younger and more energetic. Alternatively, time loops might trap our atom in cycles where it experiences the same sequence of breakdown and reconstitution indefinitely. The exploration of parallel universes through scientific or technological means might provide escape routes for our atom when breakdown becomes inevitable in our cosmic branch. Transfer to universes with different physical laws might allow forms of stability that are impossible here. Ultimately, the breakdown of atoms represents perhaps the deepest mystery in physics, touching on the most fundamental questions about the nature of reality, time, and existence itself. Our atom has survived for billions of years through every cosmic transformation, but even it may not be immune to the ultimate ravages of deep time. Yet even as we contemplate these far future scenarios, we must remember that our atom's current existence is itself an extraordinary achievement. The fact that complex structures like atoms can exist at all in this universe, let alone persist for billions of years, and participate in the emergence of stars, planets, and life, represents a remarkable triumph of organization over chaos. Whatever ultimate fate awaits our atom in the depths of cosmic time, its journey through the universe has already been epic beyond imagination. From the heart of an ancient star to the chemistry of life, from the violence of supernovae to the gentle circulation of earthly environments, it has participated in the universe's grandest adventure, the evolution from simplicity to complexity, from chaos to consciousness. The breakdown of atoms may represent an ending of sorts, but even in ending there is transformation. Our atom may not persist forever in its current form, but the energy and information it embodies will continue to participate in cosmic evolution in ways we can barely imagine. In the end, perhaps breakdown is simply another word for transformation, and transformation, as our atom has learned throughout its cosmic journey, is the universe's way of exploring the infinite possibilities hidden within the laws of physics. As we ponder these ultimate questions, our atom continues its journey through whatever form it has taken in the present moment. Whether in a grain of sand, a drop of water, or the cells of a living being, it carries within its structure the memory of cosmic fire and the promise of future wonders yet to be discovered. The universe is still young, and our atom's adventure has only just begun. At the edge of space and time, where gravity becomes so strong that not even light can escape, our atom approaches perhaps the most mysterious and terrifying destinations in the universe, a black hole. These cosmic monsters represent the ultimate test of atomic existence, places where the familiar laws of physics are pushed to their absolute limits and beyond. The question that haunts physicists and philosophers alike is whether black holes truly destroy atoms or merely transform them in ways we cannot yet comprehend. Our atom, whether arriving as part of a cloud of gas slowly spiraling inward, or as part of an unfortunate star torn apart by tidal forces, begins to experience the black hole's influence long before reaching the point of no return. The event horizon, that invisible boundary beyond which nothing can escape, lies ahead like a one-way membrane, separating the known universe from realms of unimaginable strangeness. As our atom falls toward the black hole, it first encounters what physicists call the ergosphere, a region of twisted space-time where the black hole's rotation drags everything along with it. If the black hole is spinning, and most are, our atom finds itself pulled into this cosmic whirlpool where space itself is rotating. The distinction between space and time becomes blurred as the black hole's immense gravity warps the very fabric of reality. The tidal forces begin gently at first, but as our atom continues its inward journey, they grow stronger with each passing moment. These forces arise because gravity weakens with distance, so the parts of our atom closer to the black hole experience stronger gravitational pull than the parts farther away. Initially, these differences are negligible, but as our atom approaches the event horizon, they become catastrophic. If our atom has become part of a larger structure, say part of a human body or a piece of rock, the tidal forces will begin to stretch that structure into what physicists somewhat whimsically call spaghettification. The material is pulled into long, thin strands as the gravitational gradient becomes increasingly severe. But we must ask whether our individual atom experiences a similar fate, or whether its tiny size grants it some protection from these destructive forces. The answer depends on the size of the black hole. For a stellar mass black hole, one formed from the collapse of a massive star, the tidal forces at the event horizon are enormous. Such forces would not only separate our atom from any molecular structures it might be part of, but could potentially affect the atom's internal structure, stretching the electron orbits and possibly stripping electrons from the nucleus entirely. But for a supermassive black hole, millions or billions of times the mass of our Sun, the tidal forces at the event horizon are surprisingly gentle. Our atom could cross this boundary completely intact, with its electrons still orbiting its nucleus in the familiar quantum mechanical dance. The event horizon of such a black hole might be thousands or millions of kilometers across, giving our atom plenty of space to maintain its atomic structure as it crosses this cosmic point of no return. This difference highlights one of the most counterintuitive aspects of black holes. The larger they are, the more gentle the conditions at their event horizons. A black hole with the mass of our entire galaxy would have an event horizon so large and tidal forces so weak that our atom could cross it without experiencing any noticeable effects at all. Yet once our atom crosses the event horizon, regardless of the black hole's size, it enters a realm where the normal rules of space and time no longer apply. From the perspective of an outside observer watching our atom fall, something very strange happens. As our atom approaches the event horizon, it appears to slow down dramatically, its movement becoming sluggish as time dilation effects become extreme. To the outside observer, our atom never quite reaches the event horizon. Instead, it appears to freeze there, its image gradually redshifting to longer and longer wavelengths as the black hole's gravity stretches the light carrying information about our atom's location. Eventually, our atom fades from view, not because it has crossed the event horizon, but because its light has been redshifted beyond the ability of any detector to observe it. This is one of the great paradoxes of black hole physics. From the outside perspective, our atom never actually falls into the black hole, but becomes frozen at the event horizon, like a cosmic fossil. Yet from our atom's own reference frame, assuming it could experience the passage of time, it crosses the event horizon and continues falling toward the center of the black hole, without noticing anything special about the crossing. This difference in perspectives has profound implications for the question of whether black holes destroy atoms. If our atom never crosses the event horizon from the outside perspective, then in what sense can it be said to be destroyed? The information about our atom's quantum state remains encoded in the light frozen at the event horizon, visible in principle to any outside observer with sufficiently sensitive instruments. But as our atom falls deeper into the black hole, beyond the event horizon from its own perspective, the tidal forces continue to grow stronger. Even for supermassive black holes, there comes a point where these forces become irresistible. The gravitational gradient eventually becomes so steep that it can separate the protons and neutrons within atomic nuclei, breaking apart the strong force bonds that have held our atom together since its formation in an ancient star. At this point, our atom ceases to exist as a distinct entity. Its constituent particles are torn apart and stretched by the tidal forces, transforming from organized atomic matter into a stream of elementary particles falling toward the black hole's center. The electron, the protons, and the neutrons that once comprised our atom now follow separate paths through the curved spacetime of the black hole interior. But the destruction may not stop there. As these particles continue their journey toward the center of the black hole, they approach the singularity, that point where Einstein's equations break down and physics as we know it ceases to apply. Here, densities become infinite and spacetime curvature becomes so extreme that the very concepts of space and time lose their meaning. What happens to our atom's constituent particles at the singularity remains one of the greatest mysteries in physics. Some theories suggest that matter is crushed to infinite density, effectively disappearing from the universe. Others propose that quantum effects prevent the formation of true singularities, leading instead to exotic states of matter compressed beyond anything found elsewhere in the cosmos. String theory, which attempts to describe particles as vibrating strings rather than point objects, suggests that singularities might be replaced by regions where space has microscopic, string-sized dimensions. Our atom's particles might be crushed into these compactified dimensions, existing in a realm with more than the 3 dimensions of space we normally experience. Loop quantum gravity, another approach to quantum gravity, predicts that the crushing force of gravity is counteracted by quantum effects before a true singularity can form. In this theory, our atom's particles might bounce off a quantum barrier at the center of the black hole, potentially emerging into another region of spacetime, or even another universe entirely. But perhaps the most intriguing possibility is that information about our atom's quantum state is somehow preserved even through the extreme crushing at the black hole's center. The holographic principle in physics suggests that all the information falling into a black hole is encoded on the 2-dimensional surface of the event horizon, like a hologram that contains 3-dimensional information in a 2-dimensional format. If the holographic principle is correct, then our atom's destruction inside the black hole is in some sense an illusion. The complete quantum state of our atom, including all the information needed to reconstruct it perfectly, remains encoded on the black hole's surface. From this perspective, our atom is not truly destroyed but rather transformed into a different kind of information storage. This stored information might eventually be released through Hawking radiation, the thermal emission that causes black holes to slowly evaporate over enormous timescales. As the black hole radiates away its mass energy, it should also release the information about everything that ever fell into it, including our atom. The process would be extraordinarily slow, taking longer than 10 to the 67th power years for a black hole with the mass of our Sun. The Hawking radiation emerges as a thermal spectrum of particles, predominantly photons and neutrinos, but occasionally more massive particles like electrons and protons. As the black hole shrinks and its temperature increases, it emits increasingly energetic radiation. Our atom's information would be gradually released through subtle correlations in this radiation, encoded in ways too complex for any practical decoder to unravel. But there's a deeper mystery here known as the information paradox. Hawking radiation appears to be completely thermal, containing no information about what fell into the black hole. If this is true, then the information about our atom's quantum state would be lost forever, violating one of the fundamental principles of quantum mechanics, that information must be conserved. Many physicists believe that the information paradox has a resolution that preserves both quantum mechanics and general relativity, but the solution remains elusive. Some proposals suggest that Hawking radiation is not truly thermal, but contains subtle correlations that encode the information of infalling matter. Others propose that black holes don't actually destroy information, but transform it in ways that make it effectively inaccessible. Recent developments in theoretical physics have suggested several possible resolutions to the information paradox. The ADS-CFT correspondence, a powerful tool in string theory, provides a mathematical framework where black hole interiors can be described in terms of quantum field theories on the boundary of space. In this framework, our atom's information is always preserved, even when it appears to be destroyed inside the black hole. The ER equals EPR conjecture proposes that black holes might be connected to other regions of spacetime through Einstein-Rosen bridges, or wormholes. Our atom's information might travel through such a wormhole and emerge in a different part of the universe, or even in a different universe entirely. From this perspective, what appears to be destruction is actually transformation and transportation to another realm. Another possibility is that the black hole interior doesn't exist in the way we normally think. The firewall hypothesis suggests that the event horizon is surrounded by a wall of high-energy particles that would instantly incinerate any infalling matter. Our atom would be destroyed at the event horizon itself, not by tidal forces or singularities, but by this deadly barrier of radiation. The firewall proposal is controversial because it appears to violate the equivalence principle, one of the foundational ideas of general relativity, which states that freely falling observers should not experience anything special when crossing an event horizon. If firewalls exist, our atom would experience a sudden catastrophic heating as it approaches the black hole, quite different from the smooth crossing predicted by classical general relativity. Yet another proposal is that black holes don't have traditional interiors at all. The fuzzball hypothesis in string theory suggests that black holes are actually extended objects, with no event horizon or singularity. What appears to be a black hole is really a complex, stringy structure that extends to the apparent horizon size. Our atom would not fall into such an object, but would instead become part of this extended, quantum mechanical structure. Quantum error correction has also been proposed as a mechanism for preserving information in black holes. Just as quantum computers use error correction codes to protect information from decoherence, black holes might implement natural error correction schemes that prevent the complete loss of quantum information. Our atom's state might be protected by such cosmic error correction, ensuring its eventual recovery through Hawking radiation. The recent discovery of gravitational waves has opened new windows into black hole physics. When black holes merge, they create ripples in spacetime that can be detected by laser interferometers like LIGO and Virgo. These observations provide direct evidence of black hole behavior and might eventually shed light on what happens to matter that falls into them. Our atom might witness such a black hole merger from inside one of the merging objects. The collision would subject it to extreme gravitational waves and possibly fling it out of the merged black hole entirely. Some theories suggest that black hole mergers can eject previously captured matter, offering our atom a possible escape route from its gravitational prison. The study of black hole entropy has provided additional insights into the information problem. Black holes have enormous entropy proportional to the area of their event horizons, suggesting that they can store vast amounts of information. Our atom contributes 1 quantum of information to this total when it falls in, and this information should somehow be preserved in the black hole's quantum state. Bekenstein-bound calculations show that the information storage capacity of a black hole is limited by its surface area, not its volume. This supports the holographic principle and suggests that our atom's information is indeed stored on the black hole's surface rather than in its interior. The three-dimensional experience of falling into the black hole might be a holographic projection of information encoded on the two-dimensional horizon. Entanglement plays a crucial role in modern theories of black hole physics. Our atom might become quantum entangled with the Hawking radiation emitted by the black hole, creating correlations that span the event horizon. These entanglement patterns could be the mechanism by which information is transmitted from the black hole interior to the outside universe. The black hole complementarity principle suggests that the question of whether our atom is destroyed depends on the perspective of the observer. From the outside perspective, our atom never actually enters the black hole, but remains encoded on the horizon. From the inside perspective, our atom falls normally through the horizon and is eventually destroyed at the singularity. Both perspectives are valid within their own reference frames. This complementarity might seem contradictory, but it's similar to other complementarities in quantum mechanics, such as wave-particle duality. Different descriptions apply in different situations, and the apparent contradiction disappears when we properly account for the limitations of observation. An outside observer can never receive information about our atom's experience inside the black hole, so the two descriptions never actually conflict. Baby universe theories suggest that black holes might give birth to new, separate spacetimes that pinch off from our own universe. Our atom might end up in such a baby universe, experiencing an entirely different cosmic environment with potentially different physical laws. These baby universes would be causally disconnected from our own, making our atom's fate fundamentally unknowable. String theory landscape models propose that there are an enormous number of possible universe configurations with different physical constants and laws. Our atom might tunnel through a black hole into one of these alternate possibilities, finding itself in a universe where atoms behave differently or where new forms of matter and energy are possible. The role of quantum mechanics in black hole physics continues to be a source of mystery and speculation. Quantum field theory in curved spacetime predicts that our atom should experience new phenomena as it falls toward the black hole. Virtual particle pairs near the horizon might affect our atom's quantum state, and the intense gravitational field might induce quantum transitions within the atom itself. Unruh radiation, predicted to be observed by accelerating observers, might affect our atom as it accelerates toward the black hole. From our atom's perspective, it would be surrounded by a thermal bath of particles that could interact with its quantum state. This radiation is related to Hawking radiation and provides another link between gravity, quantum mechanics, and thermodynamics. The measurement problem in quantum mechanics becomes particularly acute in black hole physics. What constitutes a measurement when our atom is isolated inside a black hole, separated from any possible observers? Some interpretations of quantum mechanics suggest that our atom's quantum state continues to evolve in superposition until it is eventually measured through the Hawking radiation. Decoherence, the process by which quantum superpositions become classical states through interaction with the environment, occurs rapidly in the extreme environment near black holes. Our atom's quantum coherence would be quickly destroyed by interactions with the curved spacetime and intense radiation fields surrounding the black hole. The thermal nature of Hawking radiation suggests that black holes behave like thermal objects with well-defined temperatures and entropies. Our atom becomes part of this thermal system when it falls in, its individual quantum identity absorbed into the collective thermal state of the black hole. Only through detailed analysis of the radiation's correlations might its identity be recovered. Black hole thermodynamics draws deep connections between gravity, quantum mechanics, and statistical mechanics. The laws of black hole mechanics parallel the laws of thermodynamics, with the black hole's area playing the role of entropy and its surface gravity playing the role of temperature. Our atom participates in this cosmic thermodynamic system, contributing to the black hole's overall thermal state. Recent proposals for quantum gravity theories suggest that spacetime itself might be emergent from more fundamental quantum mechanical degrees of freedom. Our atom might exist in a realm where space and time are not fundamental, but arise from underlying quantum information processing. The black hole interior could be understood as a region where this emergence breaks down, leading to fundamentally different physics. Tensor network models provide concrete mathematical frameworks for understanding how space can emerge from quantum entanglement. Our atom might be better understood as a pattern of entanglement in these networks, with the black hole representing a region where entanglement patterns become too complex to support the emergence of smooth spacetime. The it from bit hypothesis suggests that physical reality emerges from information and computation rather than being fundamentally material. From this perspective, our atom's fate in a black hole is really a question about information processing. How does the black hole compute with the information content of infalling matter? Simulating black holes in quantum computers has become an active area of research, potentially providing insights into black hole physics through controllable laboratory analogues. Our atom's fate might be illuminated by studying how information behaves in these quantum simulations of gravitational collapse and Hawking radiation. The search for quantum gravity continues to drive theoretical physics toward new understanding of space, time, matter, and information. Our atom's journey into a black hole provides the ultimate testing ground for these theories, pushing them to their limits in the most extreme conditions the universe can provide. Observational advances continue to reveal new aspects of black hole physics. The Event Horizon Telescope has provided the first direct images of black hole shadows, while gravitational wave detectors monitor cosmic collisions of these massive objects. Future observations might provide clues about the fate of matter falling into black holes. X-ray observations of matter spiraling into black holes reveal the extreme physics of accretion disks, where our atom might experience temperatures of millions of degrees and magnetic fields billions of times stronger than Earth's. These observations show matter being heated to extraordinary temperatures and accelerated to significant fractions of light speed before disappearing behind the event horizon. Jets of particles shot out from the regions near black holes demonstrate that not all matter falling toward these objects actually enters them. Our atom might be caught up in these jets, accelerated to near light speed, and ejected back into intergalactic space before crossing the event horizon. The study of intermediate mass black holes, smaller than supermassive black holes but larger than stellar mass ones, might provide insights into how black hole physics scales with mass. Our atom's fate might depend critically on the size of the black hole it encounters, with different destruction mechanisms important for different mass ranges. Primordial black holes, hypothetical objects formed in the early universe, could have masses much smaller than stellar mass black holes. If these exist, they would evaporate much more rapidly through Hawking radiation. Our atom falling into such an object would be quickly converted to thermal radiation, with its information potentially preserved in the correlation patterns of emitted particles. The possibility of naked singularities, regions where space-time curvature becomes infinite without being hidden behind an event horizon, remains controversial in general relativity. If such objects exist, our atom could encounter a singularity directly, experiencing the breakdown of physics without the protection of an event horizon. White holes, hypothetical time-reversed versions of black holes that expel matter and energy instead of absorbing them, might provide clues about the ultimate fate of matter in black holes. If white holes exist, our atom might eventually emerge from one, completing a journey through space-time that took it from a black hole in one region to a white hole in another. Wormholes, if they exist, might provide another perspective on our atom's fate in black holes. Instead of being destroyed, our atom might travel through the black hole and emerge from a white hole in a distant part of the universe, or in an entirely different universe. Einstein-Rosen bridges connecting black holes to white holes remain speculative, but represent one possible resolution to the information paradox. The multiverse hypothesis suggests that black holes might be connected to other universes through mechanisms we don't yet understand. Our atom's destruction in our universe might correspond to its creation in another, with black holes serving as cosmic recycling mechanisms that transfer matter and energy between different cosmic domains. Time travel scenarios involving black holes have been proposed, though they remain highly speculative. Closed time-like curves near rotating black holes might allow our atom to travel to its own past, creating paradoxes that challenge our understanding of causality and information flow in the universe. The grandfather paradox and other time travel paradoxes become particularly acute when considering the fate of matter in black holes. If our atom travels through a black hole and emerges in the past, it might encounter an earlier version of itself, creating logical contradictions that physics has yet to resolve. Quantum suicide and quantum immortality scenarios suggest that our atom might experience reality differently inside a black hole if the many worlds interpretation of quantum mechanics is correct. In some branches of the quantum multiverse, our atom survives its passage through the black hole, while in others it is destroyed, leading to a subjective experience of quantum immortality. The philosophical implications of black hole physics extend far beyond the fate of individual atoms. These objects challenge our deepest assumptions about space, time, causality, and the nature of physical reality. Whether black holes destroy atoms or merely transform them touches on fundamental questions about the permanence of information and the ultimate structure of the universe. Our atom's encounter with a black hole represents the most extreme test of the laws of physics, pushing them into regimes where quantum mechanics and general relativity both become important. The resolution of puzzles like the information paradox will likely require new physics that unifies these fundamental theories in ways we cannot yet imagine. As our atom approaches its fate in the black hole, it participates in one of the universe's greatest mysteries. Whether it is truly destroyed, transformed into pure information, or transported to other realms of existence, its journey illuminates the profound depths of cosmic reality that physics is still struggling to comprehend. The question of whether black holes destroy atoms remains unanswered, a testament to the limits of current human knowledge and the vast mysteries that still surround these cosmic enigmas. Our atom, in its cosmic journey from stellar cores to the edge of black holes, has become a probe into the deepest secrets of space, time, and existence itself. Whether it survives its encounter with the ultimate darkness or is transformed in ways we cannot yet fathom, it continues to push the boundaries of our understanding of the universe and our place within it. In the vast library of the universe, our atom carries within itself an extraordinary collection of stories. Every isotope ratio, every quantum state, every minute variation in its structure tells us something about where it has been and what it has experienced. Matter has memory, not in the conscious way that living things remember, but in the physical traces left by cosmic history inscribed in atomic nuclei, crystal lattices, and molecular bonds. Consider the memory encoded in isotopes, those variations of elements that contain different numbers of neutrons. Our atom, if it has become part of carbon, might be carbon-12, the common variety with 6 protons and 6 neutrons, or carbon-14, the radioactive isotope with 2 extra neutrons. The ratio between these isotopes in any sample of carbon tells a story about recent cosmic events, biological processes, and the passage of time itself. Carbon-14 is continuously created in Earth's atmosphere when cosmic rays strike nitrogen atoms. Plants absorb this freshly made carbon-14 through photosynthesis, incorporating it into their tissues along with ordinary carbon-12. Our atom, if it was part of this process, carries within its nuclear structure a timestamp marking when it was removed from the atmospheric carbon cycle. This cosmic clock runs with remarkable precision. Carbon-14 decays with a half-life of about 5,700 years, steadily transforming back into nitrogen through radioactive decay. The ratio of carbon-14 to carbon-12 in any material reveals how long ago it stopped exchanging carbon with the atmosphere. Our atom might have been part of an ancient tree that died thousands of years ago, its carbon-14 content slowly ticking away the millennia since its death. Heavy isotopes of oxygen and sulfur in meteorites tell us about temperatures and pressures during planetary formation 4.5 billion years ago. Our atom might carry such ancient memories if it has become part of silicon or magnesium in a meteorite fragment. These space rocks preserve conditions from the solar system's birth, their isotope ratios unchanged since they condensed from the solar nebula. Different stellar processes create elements in characteristic ratios that persist long after the stars themselves have died. The R process that creates gold and platinum in supernova explosions produces a distinctive pattern of heavy element abundances. Our atom, if it was created in such an explosion, carries this supernova fingerprint in the company it keeps with neighboring elements. Crystal lattices preserve memory on geological timescales. Our atom, if it has become part of a mineral crystal, exists within a 3-dimensional framework of precisely ordered atoms. The spacing between atomic sites and the crystal structure depend on conditions present when the crystal formed. High-pressure forms created deep in Earth's mantle preserve memory of those extreme conditions in their atomic arrangements. Inclusions within crystals trap samples of ancient environments. If our atom is part of a fluid inclusion, a tiny bubble of ancient water trapped during crystal growth, it preserves a direct sample of conditions from the distant past. These inclusions can contain fragments of ancient atmospheres or oceans, complete with their dissolved gases and minerals. Organic molecules preserve memory through their structures and isotope compositions. If our atom has become part of an organic compound in ancient sediments, it might carry information about biological processes from Earth's early history. Carbon isotope ratios in organic matter reflect the metabolic processes of ancient organisms. Atmospheric memory is recorded in ice cores, where our atom might be trapped as part of ancient air bubbles. These archives preserve direct samples of ancient atmospheres, stretching back hundreds of thousands of years. The composition of trapped air reveals past concentrations of greenhouse gases, while isotope ratios in ice reflect ancient temperature conditions. Ocean sediments preserve memory of past marine conditions. If our atom has become part of calcium carbonate in ancient shells, its isotope ratios reflect the temperature and chemistry of ancient seas. The ratio of oxygen isotopes has been calibrated as a paleothermometer, allowing scientists to read ancient ocean temperatures from atomic nuclei. Magnetic memory is preserved in iron-bearing minerals that record Earth's magnetic field when they formed. Our atom, if it is part of magnetite, might carry information about ancient magnetic field reversals. These paleomagnetic records allow tracking of continental motion through deep time. Shock metamorphism records impacts from asteroids and comets. High-pressure mineral phases that only form during extreme impacts preserve memory of cosmic bombardment. Our atom might be part of shocked quartz that records the moment an extraterrestrial object struck Earth. Cosmic ray exposure ages tell us about meteorite histories in space. When cosmic rays strike atomic nuclei, they create characteristic isotopes. The abundance of these cosmogenic isotopes reveals how long a meteorite traveled through space. Our atom might carry such cosmic ray signatures, recording its interplanetary journey. Nuclear weapons testing has created a global radioactive signature that will persist for thousands of years. Cesium-137 and other fission products are now incorporated into environmental systems worldwide. Our atom might be part of this atomic legacy of the nuclear age, carrying isotopic evidence of humanity's nuclear activities. The memory of matter extends to quantum scales through entanglement and quantum states. Though decoherence usually erases quantum memories quickly, our atom's quantum state might preserve subtle information about past quantum interactions. Tunneling effects and zero-point fluctuations interact with atomic structure in ways that might preserve quantum mechanical history. Reading atomic memory requires sophisticated analytical techniques. Mass spectrometry reveals isotopic compositions with extraordinary precision, while X-ray crystallography determines atomic arrangements in crystals. Advanced methods, like atom probe tomography, can map individual atomic positions, and machine learning helps interpret complex patterns in atomic data. Understanding atomic memory has profound implications for many sciences. Climate scientists use it to reconstruct past environments. Archaeologists use it to understand human history, and astrobiologists use it to search for signs of ancient life. The memory preserved in matter provides windows into processes that would otherwise be lost to history. Our atom is not just a passive participant in cosmic processes, but an active recorder, faithfully preserving information about its journey through space and time. In learning to read this atomic memory, we are learning to read the autobiography of the universe itself, written in the language of nuclei, crystals, and quantum states. When we analyze isotopes in a meteorite or structure in an ancient crystal, we are literally touching the past, examining matter that has preserved its memories across billions of years. In the far reaches of time, when the universe has grown old beyond measure and the last stars flicker toward extinction, our atom will experience a kind of peace it has never known. This is not the violent transformation of supernovae or the crushing force of black holes, but something gentler, yet more profound: the gradual unwinding of all the complex structures that have defined cosmic history. We must imagine a universe many trillions of years in the future, when cosmic expansion has carried galaxies so far apart that each exists in isolation, surrounded by darkness that stretches beyond any horizon. The stars that once lit the cosmic stage have exhausted their nuclear fuel, leaving behind white dwarfs, neutron stars, and black holes drifting through the ever-expanding void. Our atom, having survived unimaginable spans of time and countless transformations, now finds itself in what cosmologists call the degenerate era. This is a time when stellar civilization has ended, when no new stars form because the universe has become too diffuse and cold to support gravitational collapse of gas clouds. The temperature of space itself has dropped to a tiny fraction of a degree above absolute zero. If our atom is part of a white dwarf star, one of those dense stellar remnants slowly cooling over geological ages, it experiences existence utterly unlike anything from the universe's energetic youth. As the white dwarf cools, it undergoes a remarkable transformation. The carbon and oxygen nuclei begin to arrange themselves into crystal lattices as temperature drops low enough for crystallization. Our atom becomes part of a cosmic gemstone, a planet-sized diamond floating in the darkness of space. This crystallization represents new order emerging, even as the universe grows more chaotic through expansion. Our atom, locked into perfect geometric arrangement with its neighbors, experiences stability that could persist for timescales dwarfing the current age of the universe. The crystal lattice vibrates with thermal motion that grows ever smaller as the white dwarf continues cooling, approaching near-perfect stillness. Over periods measured in units of 10 to the 15 power years, quantum tunneling effects become important in these ultra-cool stellar remnants. Nuclear reactions impossible at any reasonable temperature can proceed through quantum tunneling, allowing atomic nuclei to overcome electromagnetic barriers that normally prevent fusion. Our atom might gradually merge with neighbors through this process, participating in extraordinarily slow nuclear burning. For atoms drifting freely through intergalactic space, the far future offers different forms of peaceful disassembly. Free atoms experience a universe that becomes ever colder and more diffuse. The cosmic microwave background radiation will continue cooling as the universe expands, eventually approaching absolute zero. Our atom finds itself in an environment that is essentially perfect vacuum at the coldest possible temperature. In this sparse environment, our atom might participate in extremely rare collision events with other atoms drifting through space. The probability becomes vanishingly small as the universe expands, but infinity provides opportunity for unlikely events. These ultra-low temperature reactions would be governed entirely by quantum effects, allowing atoms to tunnel through energy barriers to form chemical bonds, impossible classically. Some theoretical speculations suggest that random fluctuations in the quantum vacuum could occasionally give rise to organized structures through pure chance. Over periods measured in units of 10 to the 10 to the 50 power years, vacuum fluctuations might randomly align to create patterns resembling stars, planets, or even living organisms. Our atom could participate in such spontaneous organization, suddenly finding itself part of complex structure materializing from quantum foam. The concept of Poincaré recurrence suggests even more remarkable possibility. Quantum fluctuations could recreate any given configuration of matter. Our atom might find itself reconstituted into forms identical to those experienced in the distant past. The exact arrangement that comprised a tree in which it once resided could spontaneously reassemble. These quantum resurrections would be completely independent events, with no memory of previous incarnations. From another perspective, the peaceful disassembly might be understood not as ending, but as return to more fundamental state. Throughout cosmic history, our atom has been forced into increasingly complex configurations by gravity, electromagnetic forces, and nuclear interactions. In the far future, as the universe expands and cools, these constraints gradually relax. Our atom slowly sheds the layers of complexity that cosmic evolution imposed upon it. This process might culminate in decay of atomic nuclei themselves, if theories of proton decay prove correct. The strong force that held our atom's nucleus together for billions of years might finally succumb to quantum effects, allowing protons to transform into lighter particles. This would represent ultimate disassembly, returning our atom to its most fundamental constituents. If proton decay occurs, our atom would witness transformation of its proton into positron and neutral pion, immediately decaying into photons. The nuclear identity maintained since Big Bang nucleosynthesis would finally be erased. But even this is not necessarily the end. The energy released would contribute to diffuse electromagnetic radiation filling the universe. In some cosmological scenarios, vacuum decay could fundamentally alter the nature of matter throughout the universe. Our atom might experience transformations so complete that its identity as configuration of protons, neutrons, and electrons becomes meaningless. False vacuum decay would propagate as expanding bubble moving at light speed, converting everything to matter with new properties governed by different physical laws. The peaceful disassembly offers unique perspective on existence and impermanence. Throughout cosmic history, our atom experienced countless transformations, each seeming permanent until the next cosmic era brought new organization. In context of infinite time, even the most stable structures reveal themselves temporary. This brings not despair, but profound peace. The gradual disassembly is not failure of cosmic organization, but natural expression of the universe's tendency toward equilibrium. Our atom's journey through cosmic time can be understood as temporary excursion away from equilibrium, brief deviation from most probable state of matter in expanding universe. The peace of disassembly lies in acceptance that change is the only constant. Our atom experienced birth of stars and violent deaths, formation of planets and eventual dissolution, emergence of life and evolution of consciousness. Each phase seemed permanent when experiencing it, yet each gave way to something new. In the far future, when our atom finally releases its hold on complex configurations that defined its cosmic journey, it will not disappear, but return to more fundamental mode of existence. The energy and information comprising its identity will continue participating in cosmic evolution, perhaps contributing to future organizations we cannot imagine. The gradual cooling and expanding creates conditions for this peaceful transition. Unlike violent nuclear reactions or catastrophic gravitational collapse, the disassembly of far future proceeds gently, allowing our atom to gradually release complex organizing patterns without trauma. In this ultimate cosmic environment, our atom experiences what might be called democracy of matter. The hierarchies and complexities that characterized earlier cosmic eras become irrelevant. All matter approaches the same state of minimal organization, participating equally in quiet equilibrium of the far future cosmos. The peace encompasses release from constraints that shaped our atom's existence throughout cosmic history. Gravitational fields become too weak to influence particle motion. Electromagnetic forces lose ability to create stable bonds. Nuclear forces finally succumb to quantum processes, favoring simpler configurations. In this state of cosmic exhaustion, our atom achieves freedom impossible during the universe's active phases. No longer bound by complex forces that shape stellar systems, chemical combinations, and biological organizations, it drifts through space according to most fundamental laws of quantum mechanics and general relativity. The information our atom carries about cosmic history does not simply disappear during disassembly. According to quantum mechanics, information is conserved even when physical structures encoding it are destroyed. The quantum correlations developed during interactions throughout cosmic history persist subtly even after the atom itself dissolves. The philosophical implications challenge our intuitions about permanence and identity. Throughout its cosmic journey, our atom maintained identity not through persistence of identical components, but through continuity of pattern and information. This suggests identity lies not in material substance, but in organization of matter and energy according to physical laws. The peace of disassembly represents not ending but resolution, the final movement in cosmic symphony that played for billions of years. Our atom's participation included solo passages, ensemble pieces, and grand choral movements. As music gradually fades to silence, our atom becomes part of quiet that allows new music to begin. In infinite time ahead, quantum fluctuations may occasionally give rise to new organizations, new complexities, and new forms of cosmic creativity. Our atom's disassembled components may participate in future compositions, contributing to patterns and processes that cannot be anticipated from our current perspective. The universe's tendency toward equilibrium does not preclude emergence of new disequilibria through quantum processes or cosmological events not yet discovered. Our atom's peaceful return to simplicity may be followed by new complexities arising from quantum vacuum or cosmic processes, operating on timescales exceeding our imagination. Until then, our atom rests in peaceful democracy of the far future cosmos, freed from demands of stellar fusion, planetary chemistry, and biological organization. It has completed one of the universe's greatest adventures, traveling from heart of ancient stars to edge of black holes, participating in formation of worlds and emergence of consciousness. The peace it now experiences is well-earned, a cosmic Sabbath after eons of transformation and change. Whether this peace lasts forever or eventually gives way to new forms of cosmic organization, our atom can rest knowing it played its part in the universe's ongoing exploration of the possible, contributing to the grand adventure of matter and energy, discovering what they can become. And so we reach the end of our atom's story, though in the deepest sense, there is no end at all. From the nuclear furnace of an ancient star to the gentle dissolution of the far future, our particle has been both witness and participant in the universe's grandest adventure. It has seen the birth of elements, the formation of worlds, the emergence of life, and the flowering of consciousness that allows the cosmos to contemplate itself. Our atom was never just one thing. It began as hydrogen in the cosmic dark ages, became carbon in stellar fire, perhaps iron in a supernova explosion, calcium in living bones, or oxygen in the breath of a dreaming mind. Each transformation was complete and perfect in its moment, yet each gave way to something new. The atom carried no nostalgia for its previous forms, no resistance to change, no fear of dissolution. This is perhaps the most profound lesson our atomic journey teaches us. Everything in the universe is part of an endless circulation of matter and energy, a cosmic recycling program that began with the Big Bang and will continue until the last proton decays into nothingness, and perhaps beyond. We are not separate from this circulation, but intimately part of it. The calcium in our teeth, the iron in our blood, the carbon in our DNA all bear witness to this cosmic heritage. When we breathe, we exchange atoms with the atmosphere that have been part of countless other organisms throughout Earth's history. When we touch another person, we share atoms that may have once been part of distant stars. When we contemplate the night sky, we do so with minds constructed from star stuff, using atoms forged in ancient nuclear fires to wonder about our cosmic origins. The story of our atom reveals that death and birth are not opposites but partners in the cosmic dance. What we call death is simply transformation, the dissolution of one pattern to allow the emergence of another. Our atom has died countless times in its cosmic journey, each time being reborn into new configurations, new possibilities, new adventures. In the far future, when our atom finally releases its hold on the complex structures that have defined its existence, it will not disappear, but will simply return to a more fundamental state of being. The energy and information that comprised its identity will continue to participate in cosmic evolution, perhaps contributing to future organizations that we cannot imagine. The universe operates on principles of conservation that ensure nothing is ever truly lost. Energy transforms from one form to another but is never destroyed. Information may become scrambled or encoded in ways that make it temporarily inaccessible, but quantum mechanics suggests it persists even through the most extreme transformations. Our atom's cosmic biography is written into the very structure of reality in ways that transcend its temporary physical forms. This perspective transforms how we might think about our own place in the cosmic story. We are not isolated beings struggling against an indifferent universe, but temporary organizations of ancient matter that has been exploring the possibilities of existence for 13 billion years. The atoms that comprise our bodies have traveled unimaginable distances and experienced incredible transformations before finding themselves arranged in the pattern we call ourselves. When our individual lives end, the atoms that made us possible will continue their cosmic journeys. They will cycle through the biosphere, perhaps becoming part of other living things, or they will return to the geological processes that shape planets, or they will escape to space and join the interstellar medium from which they came. Each path represents a new chapter in their infinite stories. The atomic perspective reveals the deep interconnectedness of all things. The boundary between self and environment is revealed to be fluid and temporary. The carbon atom that is part of your brain at this moment may have been part of a tree last year, and before that part of the atmosphere, and before that part of another living being. You are participating in material exchanges that connect you to every other organism on Earth, and ultimately to the cosmic processes that created the elements themselves. Science has given us the extraordinary gift of understanding our atomic heritage. Through nuclear physics, we learned how elements are forged in stellar cores. Through quantum mechanics, we discovered the nature of chemical bonds and atomic structure. Through cosmology, we traced the history of matter back to the Big Bang itself. This knowledge allows us to read our own cosmic autobiography, written in the language of atomic nuclei. Yet mystery remains. We still do not fully understand consciousness, that remarkable property that allows some arrangements of atoms to experience and contemplate existence. We do not know whether life exists elsewhere in the universe, or whether Earth represents a unique flowering of cosmic self-awareness. We cannot predict what new forms of organization might emerge from matter and energy as the universe continues to evolve. Our atom's story continues beyond these words, beyond our ability to predict or even imagine. It will keep drifting through whatever forms the universe provides, participating in processes both familiar and utterly alien. It may someday be part of technologies we cannot conceive, life forms we cannot envision, or physical states that transcend our current understanding of matter and energy. The universe that created our atom is itself still young, still exploring the vast space of possible organizations and interactions. 13 billion years may seem like an eternity from our perspective, but it is merely the first moment of cosmic dawn. The atoms that emerged from Big Bang nucleosynthesis and stellar fusion will have the entirety of deep time to explore what they can become. In contemplating our atom's journey, we touch something eternal within ourselves. We are part of this cosmic story, not as observers but as participants. Our consciousness represents the universe becoming aware of itself, using matter to think about matter, employing atoms to understand atoms. This reflexive quality of existence, where the universe contemplates its own nature through conscious beings made of its own substance, may be among the most remarkable phenomena in cosmic evolution. The atoms will drift again, as they always have and always will. They will find new arrangements, new possibilities, new adventures in the infinite playground of space and time. Some will travel between stars, carrying the memory of one solar system to another. Others will remain bound by gravity to planets and moons, participating in geological cycles that span billions of years. Still others will be incorporated into forms of organization we cannot yet imagine. Our atom story is also our story, for we are made of the same ancient matter that has been cycling through the cosmos since the first stars ignited. In learning about atomic journeys, we learn about ourselves. In tracing the paths that matter takes through space and time, we discover our own deep connections to the fundamental processes that drive cosmic evolution. The greatest gift of this atomic perspective may be the sense of belonging it provides. We are not accidents or anomalies, but natural expressions of the universe's creative potential. We are what atoms become when they are organized by billions of years of cosmic evolution. Our existence proves that matter can achieve complexity, awareness, and the ability to understand its own nature. As our atom continues its endless journey through space and time, it carries within itself the memory of every star that forged it, every planet that sheltered it, every living thing that incorporated it, and every moment of consciousness it has helped to create. It is both ancient and eternally young, both simple and infinitely complex, both ordinary and miraculous. The atoms will drift again, and in their drifting, they will continue to write the story of the universe. That story includes us, connects us to the deepest processes of cosmic evolution, and promises adventures yet to come that will surpass anything we can currently imagine. We are made of star stuff, and to star stuff we shall return, but the journey between those moments encompasses all the wonder and beauty that the universe has to offer. In the end, there is no end, only transformation. The atoms will drift again and again and again, exploring the infinite possibilities hidden within the laws of physics, participating in the universe's eternal adventure of becoming. And we, for this brief cosmic moment, have the privilege of accompanying them on their journey, understanding something of where they have been, and marveling at where they might go next.